Can we have one more round of applause for Sir? May I request everyone to please be seated? May I have everyone's attention? The next revolution won't be seen, it will be computed. Good morning, everyone. I am Srishti Gusai from BTech Computer Science and Business Systems, and along with my co-host Sneha Rawat from BTech Information Technology, we warmly welcome you to the symposium on recent advancements in quantum science and technology hosted by Amity Science Technology and Innovation Foundation at Amity School of Engineering and Technology. The symposium brings together the curious, the creators, and the code breakers of tomorrow, centered on emerging breakthroughs, global strategies, and the evolving quantum pipeline. The event explores how quantum principles are reshaping computation, communication, and problem solving. It creates a shared space where academia, research, and industry intersect to decode the future. At its heart, the symposium celebrates innovation powered by the smallest building blocks of reality. By aligning national ambitions with global advancements, the event strengthens India's role in the quantum revolution.
A very good morning, everyone. I request you all to please put your hands together for all our guests here who have joined us this morning. Can we have a louder round of applause, dear students? Can we show us? Can we show them the amity energy? Everybody, a huge round of applause. Thank you. Thank you so much.
Shubham Karoti Kalyanam, Arogyam Dhan Sampada, Shatru Buddhi Vinashaya, Deepa Jyotir Namastute. The sacred act of lamplighting symbolizes of knowledge, the removal of ignorance, and the pursuit of wisdom and excellence. As we seek divine blessings for the symposium, I kindly invite the esteemed dignitaries to please step forward for the lamplighting ceremony.
ॐ भूर्भुवस्वः तत्सवितुर्वरेण्यं भर्गो देवस्य धीमहि धियो यो न प्रचोदयात्.
हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। तू स्वर की देवी है, संगीत तुझसे, हर शब्द तेरा है, हर गीत तुझसे। तू स्वर की देवी है, संगीत तुझसे, हर शब्द तेरा है, हर गीत तुझसे। हम हैं अकेले, हम हैं अधूरे, तेरी शरण में हमें प्यार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें प्यार दे माँ। अज्ञानता से हमें प्यार दे माँ। अज्ञानता से हमें प्यार दे माँ।
Thank you, sir and ma'am. I thank Divyani, Replika, and Anshpreet for the harmonious Vandana. I now request all the esteemed dignitaries to kindly take their seats as we proceed.
It is with immense honor that we welcome Dr. Selva Murthy, sir, a distinguished figure within Amity University. Sir serves in various capacities, including President of the Amity Science, Technology and Innovation Foundation, Director General of the Amity Directorate of Science and Innovation, and Chancellor of Amity University, Chhattisgarh. His remarkable career boasts over 4 decades of dedicated service to the Defense Research and Development Organization, DRDO, under the Government of India. He's been a key figure in shaping research and innovation at Amity University. May I now request Sir to deliver the opening remarks. Let's have a huge round of applause for him.
Good morning to every one of you. Good morning. Very nice. Honorable Founder President, Dr. Ashok Chauhan ji, who has created this whole Amity universe today with 12 universities in India, 18 campuses abroad, 28 schools, 250,000 students, 10,000 faculties, 5,000 PhD scholars. So he has created this Amity universe with only one aim, that how do we create a happy, healthy, peaceful, prosperous world. So that is his only aim with which he has started. And now these institutions have churned out 800,000 alumni across the globe. And they are in different parts. And this number, imagine in next 10 years, what will be the number? With still Amity growing horizontally, vertically. So let's give a big clap to our founder president, Dr. Ashok Chauhan, who is a great visionary and who would like to see India as a not only a knowledge superpower, but a global superpower. So this is the mission, and we are creating the future global citizens who are sitting here from our international schools, Amity International Schools. We are our students from Amity University. So all of them are here. They are the future global citizens who are endowed with knowledge, including spiritual knowledge, skills including soft skills, good behavior, sanskar, values, resilience to face challenges in one's life. This is what is Amity's mission. Amity's mission. We also promote creativity, innovation, problem-solving ability among our children. So this is the Amity Education Group philosophy, and we are so happy to have very distinguished guests here. So on behalf of Founder President Dr. Ashok Chauhan ji, our Chancellor, Dr. Atul Chauhan ji, in fact, he was very keen to come today to this function in person, but he has joined us online because he came back from US only day before yesterday, late in the night. And then he suddenly has the engagement today. that which could not be avoided. He wanted to reschedule this appointment, but unfortunately, that is such a very critical one where his presence is very essential. So he will address us online, and he's seeing right from the beginning. He's with us. Yesterday, in fact, I met him in his residence at the AKC House. Spent a long time, and he said, yes, I will come in person. But such a vital engagement which he told me just a few minutes ago. Thank you, Chancellor sir, for all your support. You have launched this quantum mission, Amity Quantum Mission, and this is under the aegis of your Amity Quantum Mission that this symposium is being held, the quantum science and technology. So let's welcome our Chancellor, Dr. Atul Chauhan, and he is a product of London School of Economics at the University College of London. So he has an engineering degree as well as a management degree. So you see the type of people who govern this organization, who are highly educated. Our founder himself is a PhD in the chemical engineering from Germany. And Dr. Mrs. Amita Chauhan, who looks after our schools, Amity International School, we have representative in the symposium. She has 28 schools, and she is churning out the future global citizen from our schools and preschools. So Dr. Mrs. Amita Chauhan and Dr. Asim Chauhan is a product of Wharton Business School. Yesterday I had a meeting with him. We are developing a Amity Global Research Hub in the Long Islands of New York, 170 acres and with 11 buildings already constructed. So we are creating a global research hub. Maybe your IBM, Qubit, Force, everybody can have an office there. So he has created a Amity Global Research Hub. Yesterday we had strategic discussion in the AKC House, our founder president's house. So such people govern this, and Mr. Amol Chauhan is a product of Harvard. So why I am telling to the guests who are here that this is what Amity is. We are governed by the people who commit themselves, hopping from one country to the other, hopping from one meeting to the other. So this Amity Quantum Mission, launched by our Chancellor, Dr. Atul Chauhan, who is also the president of Rikhanand Balbed Education Foundation, and he will address. And so his vision is that India in deep techs, Amity University should make an impression, great impression. So he has established Artificial Intelligence Center. Dr. M.K. Datta. Dr. M.K. Datta is here. Let's give a big clap to Dr. M.K. Datta, who is also one of the pro-vice chancellors. And he is now having a 10 petaflop computing capability today, NVIDIA A100 system, and he is upgrading it. He's educating all of us, including faculty, students. So this mission was launched by Chancellor, Dr. Atul Chauhan, AI mission. Dr. Atul Chauhan wants every student, every faculty to be educated in AI. So that is why the center has been established. And this is one mission, AI mission. Second mission is the Amity Quantum Mission. Third mission he is launching is the Semiconductor Mission. So these are the three important missions in deep tech area. So thank you, Chancellor sir, for your visionary approach to create these centers. And he has created a wonderful design center here. Because the design culture is important. If India has to become Atmanirbhar Bharat, if India has to become Viksit Bharat, which is the vision of our Honorable Prime Minister Shri Narendra Modi ji, design concept is necessary. System engineering concept is essential. This is what Amity is doing. This is what is our chancellors, our founder president is driving. So I welcome on behalf of founder president, the chancellor, and our vice chancellor is actually going to function in the Indian Space Association. ISPA is hosting. In fact, I was also to be there, but we are hosting this. So today we are receiving an award, the Excellence Award for Research and Innovation from ISPA. Let's give a big clap to all those space scientists, Professor M.S. Prasad, Shivani, and they are driving the space science and technology. And we are fortunate to have Dr. Khatri, who is our the Pro-Vice Chancellor Academics. Let's give a big clap to, because he is launching an MTech Defense Technology program. And so as a Dean, the Pro-Vice Chancellor Academics, he is driving that. So we have all those people. On behalf of them, I welcome you all, particularly Dr. Purnendo Chaturvedi. Purnendo Chaturvedi, who is just sitting here, and just raise your hand. So he is scientist G, which is one of these very senior position in DRDO. And in fact, I know him. He's growing in DRDO. I have closely interacted with him. So we are very fortunate to have him. And he is driving the mission, Amity, the DRDO mission in quantum technology in the DRDO. So we are very fortunate to have him, Dr. Fernando Chaturvedi. Then we have yet another stalwart, Dr. Venkata Subramanian. Dr. Venkata Subramanian, he was earlier in he was in IBM for almost 27 years. He was in IBM, one of the strongest in the IT sector and the computers. So he was with that. Now he has started a big startup. And this startup has made, he just showed me his video of the whole facility inaugurated by the Chief Minister of the Andhra Pradesh, Dr. Chandrababu Naidu. And he is launching a big quantum computing mission in the country to contribute to national quantum mission. And this Venkata Subramaniam, he is now the CEO of the Qubit Force. That is the startup name of the startup. So we were discussing how we can partner with him. We want a facility to be created here, the quantum computing facility to be created. Already 100 plus qubit facility he has created, capacity he has created. He is giving this supply, he is developing it for some of the universities and IITs. So I have also put in a word that we will sit together to see how we can have a quantum computing facility here. And Chancellor has already earmarked some amount and some amount only for quantum technologies, about 30 crores. He has initially put a seed money there. So we will develop these facilities. So welcome Dr. Venkata Subramaniam. Let's welcome Dr. Venkata Subramaniam. Then we have the head and of the Center of Excellence in Quantum Technology in CDOT, Dr. Atul Kumar Gupta. Dr. Atul Kumar Gupta from CDOT, all the telecommunication and in which they are looking at secure communications and quantum communication. So he is driving this in quantum technology in CDOT, Dr. Atul Kumar Gupta. Then we have Director of DRDO Young Scientist Laboratory, the Quantum Technology DRDO, who has joined online. He is Dr. Santu Sardar. Dr. Santu Sardar, welcome. Let's give a big clap to Dr. Santu Sardar. DRDO has created a new concept. The labs are headed by scientists below the age of 35 years. You pick them young, groom them as leaders. So we have established about 6 laboratories there. One of them is headed by Dr. Santu Sardar. And so he is the director at the age of 35, below 35. And now he is going to address us, and he is driving this particular center is totally dedicated for quantum technology. So we are fortunate to share the vision. We have 2 people from DRDO, Dr. Fernando Chaturvedi, as well as Dr. Santu Sardar from the Young Scientist Laboratory. Then we have a representative from CDAC. CDAC and our Dr. Abhishek Tiwari is from, she is very senior scientist there, and he is the associate director there at the CDAC driving the quantum mission. Then we have Preeti from SSPL, who is driving the mission in solid state physics laboratory in Delhi. So I have very senior people sitting here. So welcome to each and every one of you. And this mission is very, very important for us. We want to work with you. Now, coming to some of these other people who will be joining IIT Delhi, and we have NXP Semiconductors who are joining, who are already here, and then the QNew Labs, TAQ Bit, IBM Quantum, Jamia Millia Islamia, IIT Delhi, Bosch Global, all these representatives. I'm not naming them by the names, but then they are all here. Welcome to each and every one of you. Now coming to the students, we have Amity International School students. Let's give a big clap. All students get up. Amity School students. Dr. Mrs. Samita Chauhan, I'm so grateful to you that you have sent brilliant students and also the teachers who have accompanied them. Welcome. You are the future. And also our own students from Amity Universities. Get up, all of you get up. We want to salute you. We want to celebrate you. Very nice. So now coming to the theme of this, see today, quantum science and technology is a sunrise area. It's very fertile. The whole globe is racing towards US, China, European countries. Everyone is racing towards quantum, which is still fertile, much to be done, much to be explored in so many verticals: quantum computing, quantum sensing, quantum communication, and with quantum materials and quantum metrology. You name everything. There's a very beautiful area to work with, and which is high risk and high rewarding areas. So that is why, students, please listen to every one of the words spoken by our experts and then assimilate, then ruminate, generate, churn out new ideas, innovative thought, disruptive technologies. It all should come from India. So India wants to assume leadership role in quantum technology. That is why National Quantum Mission has been announced by our Honorable Prime Minister. So that is why Amity, together with all the experts here, have to play a big role. That is why Amity Quantum Mission. So I welcome every one of you for this. Now coming to what is the market value today for quantum technology? It is only a very small, 1 to 1.5 billion dollars, $1.5 billion, but which is growing at the rate of almost 20 to 40% is a CAGR is the growth rate for this. So that is why this is a very fertile area. Very little has been done in terms of deliverable coming into this. It's still growing. So that is why we have to launch this. It's a high risk, high reward area. Then Indian scenario, we have very strong IT and software capability, which is very essential. We have very strong physics capability, which is again essential for quantum. So material, we have very strong materials group. So all these are our strengths. Then we also have startup ecosystem. We want youngsters, like he has made a startup, Venkat has made a startup. So even though he worked in IBM for 27 years, he has made a startup. So this startup ecosystem, including our Amity International School students have startup. So this is what is the opportunity available. So now the qubits, when you talk of quantum computing, superposition and entanglement, that is what we are trying to exploit in Amity as well as in the whole system. Now, a few more words about what Amity is doing. See, we have almost about 80 faculties across our Amity group working primarily in quantum areas. So that's a big workforce because 80 faculties, PhDs, all of them are PhDs. And then we have started a MTech Quantum Science and Technology program. We have already launched it in Amity, and now we are admitting students in this area. So that is where we had all the faculties sitting together, looking at the model, national model, best of the global model in education. We have started a Amity MTech program in quantum technology. Then we also have started a minor track, then domain electives. So we have started the academic activities because we need human resource to work. Today, very handful of people are there who are actually in the field of quantum. So we are training our faculties in quantum, bringing new faculties. So if there are some good faculties, please let us know. We have position for you people. So then quantum in space. In fact, both Dr. Professor Prasad and Shivani, they are working on quantum technology application in space. And here they will be talking about it in the panel discussion. Then Dr. M.K. Datta is now combining quantum and AI together. AI quantum combination is a powerful combination. So that is being done by them. So like this, Amity is in a very, very vibrant place. We have filed 2,860 patents. So that is Amity, 2,860 patents. Granted are more than 500. And then we have transferred 35 technologies through our Technology Enabling Center and also DITT, which is Innovation and Technology Transfer. We have incubated more than 1,200 startups in our incubator. We have industry. So Amity has all the ecosystem required to churn out the new innovation. So I'm sure this Amity Quantum Mission will lead to that. But 3 missions are very important to achieve the objective. One is Mission Connect. We want to connect with all the experts who have come from academia, industry, corporate, government, and government laboratories. So we want to connect to bring synergy to your mission and also synergy to our mission, Amity Quantum Mission. Then we also want to bring outcome, fruitful outcome through this collaboration synergy, that there must be a fruitful outcome for you as well as for us as a country. So that is the mission. So the ultimate aim is India should assume the leadership role in quantum science and technology. That is the aim of all of us here. So So I welcome each and every one of you. Thank you so much for being with us. Let's have a fruitful interaction and come out with. We are also fortunate to have Harish Sahu. Let's clap for Harish. Yes, Harish, sorry, I missed you. He is from our one of the DRDO lab, a very important lab, Scientific Analysis Group, SAG, which is a very important lab. Before any system programs are launched, this is the lab which gives what will be the requirement, what is the strategic requirement for the country in terms of the national security. So I welcome Dr. Harish Sahu, and also we are working with them. So we would like to expand this collaboration. Particularly, I want to announce one thing. We are already started 2 projects with the DRDO. One of them is with him and JCB together. That is on quantum key distribution. See, normally secure communication for data or for any secure communication, you need security, cyber security, cryptography. So in which Amity is working in this critical area, where we have already developed the algorithm for post-quantum cryptography as well as for the cyber security and the quantum key distribution, using that for key development, which is the main mandate of these 2 labs, SAG as well as JCB. So we are doing project with them. We are doing a number of them. We will tell it during the deliberation. So this is Amity. Welcome to each and every one of you. Thank you.
Thank you, sir, for your enlightening words. Your insights have truly enriched us with knowledge and values. We are deeply honored to have blessings of Professor Dr. Balvinder Shukla Ma'am, the Honorable Vice Chancellor of Amity University, Uttar Pradesh. Ma'am is a remarkable leader and visionary strategist who has played a pivotal role in shaping the university's remarkable achievements. Her dedication and insightful guidance have provided countless opportunities for students to explore their talents and cultivate innovative thinking on a global scale.
We now move forward to hear from our first guest of honor for the symposium. As a high-ranking official within India's premier defense R&D body, Dr. Purnendu Chaturvedi sir plays a pivotal role in strategic, technical leadership and the oversight.
Hello, good morning, everyone. I hope it is working. So I have got only 10 minutes. So let's not waste time in that. यहाँ पे स्टूडेंट कौन कौन है? हिंदी तो समझ में आती है ना? हिंदी सबको समझ में आती है ना? स्टूडेंट्स कौन कौन है भाई? ओके गुड. और बाकी फैकल्टी, गेस्ट, इंडस्ट्री सब कुछ. तो 10 मिनट. क्वांटम टेक्नोलॉजी किस किसने पढ़ी है भाई? कुछ क्वांटम टेक्नोलॉजी, क्वांटम साइंस, क्वांटम फिजिक्स कुछ पढ़ा है इससे रिलेटेड किसी ने? कोई भी स्टूडेंट्स में से? फिजिक्स, तो फिजिक्स में क्वांटम फिजिक्स आया होगा, कुछ पार्ट तो आया होगा यार. फिजिक्स तो फर्स्ट ईयर पढ़ा है, तो फर्स्ट ईयर तो कंप्लीट हो गया ना मैम. किसी ने पढ़ा है? रेज योर हैंड्स भाई. किसी ने नहीं? किसी ने क्वांटम फिजिक्स सुना है यार? इस पे तो हाथ उठाना पड़ेगा, मतलब इतना लेजी नहीं होते. क्वांटम फिजिक्स किसी ने भी सुना है? बिल्कुल नहीं.
Student, we interacted with him. He is asking you know about quantum.
अच्छा, मोबाइल किस किस के पास है? बस एक. कोई तो मतलब किसी को तो हाथ उठाना पड़ेगा. बाकी के पास मोबाइल नहीं है? ओके गुड. ओके गुड. तो मुझे जनरल लेवल ऑफ इंटरेस्ट समझ में आ गया है कि कितना तुम लोगों का इंटरेस्ट है. तो जब तुमने क्वांटम फिजिक्स सुना ही नहीं है, क्वांटम टेक्नोलॉजी पढ़ा ही नहीं है, तो 10 मिनट में मैं क्या ही पढ़ा दूंगा ना. तो लाइफ स्किल्स सीखते हैं. किसी को सिचुएशनशिप के बारे में पता है? सिचुएशनशिप या कोई जेन जी का है क्या, या सारे बूढ़े बैठे हैं? एनीवन फ्रॉम जेन जी कैन एक्सप्लेन? So anyone can they explain what is situationship? यार ये तो तुम लोगों का फेवरेट टॉपिक है, इसमें भी नहीं बोलोगे तो कैसे चलेगा? सिचुएशनशिप कोई? हाँ, ये नहीं पूछ रहे कौन सिचुएशनशिप में है, दैट इज नॉट द क्वेश्चन, सॉरी। जस्ट व्हाट इज सिचुएशनशिप, कोई एक्सप्लेन कर सकते? पॉपुलर डिमांड।
तो सिचुएशनशिप में जब आप किसी से कमिट नहीं करना चाहते पर उसके साथ रहना चाहते हो, और बट फिर भी आप फुली कमिट नहीं करना चाहते हो, नहीं हो बट आप होना चाहते हो बट नहीं होना चाहते।
बट
रिलेशनशिप तो होता है सर जब आप स्टेज में हो और आप हो रहे हो, बट आप उसको बट आप अपने पार्टनर को आप कमिटमेंट आप नहीं आप दे रहे हो, आप मतलब
हो भी नहीं भी हो, मतलब कुछ क्लियर नहीं है।
सर
आगे भी क्या होगा ये भी नहीं पता है।
पता है सर, ना सामने वाला चाहता है ना हम चाहते हैं,
फिर भी कुछ है।
फिर भी कुछ है।
ओ, ठीक है,
वो सर एक पार्क है हम दोनों के बीच पर।
पार्क है। ओ गुड गुड, पार्क है। अच्छा, थैंक यू थैंक यू थैंक यू। डिफिकल्टी लेवल बढ़ाते हैं। रेंट फ्री, रेंट फ्री, इफ यू आर लिविंग इन समवन दैट रेंट फ्री, इसका क्या मतलब है? अदर एक्सट्रीम, रेंट फ्री मतलब अमेठी का इतना बेकार रिस्पॉन्स। रेंट फ्री किसको पता है? नहीं, ट्विन फ्लेम, रेंट फ्री। कोई भी भाई एक्सपर्ट बताओ, कौन है एक्सपर्ट? सिद्धार्थ बताएगा मुझे।
सर नहीं पता।
हाँ, ये फर्जी एक्सपर्ट है ये।
Hi, sir. Hi, sir.
प्लीज क्लैप पहले।
Sir, I think living in somebody's mind and you are thinking about that person 24/7, and you just think about them all the time. Like, you might be doing something else, but you're thinking about them. I think that's living rent free.
आप असली क्लैप भाई, किसी ने अच्छे से एक्सप्लेन किया, वेरी गुड। So you are constantly connected 24/7. तो अब इसका हमारे लेक्चर से क्या रिलेशन है? सिचुएशनशिप इज नथिंग बट सुपरपोजिशन। यू आर इन 0, 1, बोथ, हो नहीं हो किसी को क्लियर नहीं है। दैट इज व्हाट क्वांटम फिजिक्स इज। व्हेन इलेक्ट्रॉन्स और प्रोटॉन्स दे आर इन अ सिचुएशनशिप, इट मींस दे आर सुपरइम्पोज्ड इन सेवरल डिफरेंट स्टेट्स। और वो जो मैम ने एक्सप्लेन किया, लिविंग रेंट फ्री इज नथिंग बट entanglement. When two photons or two electrons, they are entangled with each other 24/7, कहीं भी जाए बस एक दूसरे के बारे में सोचते हैं, that is entanglement. So very simple concept, entanglement and is equivalent to living rent free, and situationship is nothing but superposition. तो 10 मिनट में तो इतना ही समझाया जा सकता है भाई, अगर बोलोगे तो लेक्चर भी बनाया वो भी बोल ही देंगे। Okay, so let me start. So quantum is not one field, but there are so many different fields in it. There are some slides to बोलना तो है. There are different domains. They are working at different speeds. Whether it is quantum computing, जो इतने सारे words आपने सुने, quantum communication, MET has started playing a role in this, or quantum sensors, quantum materials, graphene, तुम लोगों ने सुना होगा, वो भी is part of that. So there are so many things happening here. What we see is the power of quantum computing is coming from what we learned just now, situationship. That is the superposition. So when there are so many qubits, that qubit can be in several different states, 2 to power, so some billions or trillions or even very large numbers of states with a very simple, very small system, like the one being built here in India. We are thankful to his startup who has set up. I believe you would have seen the news alert, the videos. Amazing thing has been done in India, and I believe this will grow exponentially. Similarly, but when we are doing into that domain, there are still certain limitations. That's what I would like you to understand. There are quantum computing, quantum sensors, quantum communication. So many things have done. There's so much hype, but there are still some problems to solve. तो जो पीछे वाली रो है ना, जहाँ जो भी इंटरेक्ट कर रही थी, ये तुम्हारे लिए प्रॉब्लम्स हैं. जो यहाँ इन गोल गोल टेबल पे बैठे हैं, ये अब ज्यादा काम के नहीं है, और जो और भी ऊपर आ गए हैं वो तो अब बिल्कुल भी काम के नहीं है. अब जो आगे करना है वो तुम लोगों को ही करना है. तो ये जो प्रॉब्लम्स है आगे की क्वांटम कंप्यूटिंग की या क्वांटम कम्युनिकेशन की या क्वांटम सेंसिंग की, योर जनरेशन हैज टू सॉल्व एंड सॉल्व इट वेरी वेल, क्योंकि उसके बाद ही आप आगे बढ़ सकते हो. देयर आर लॉट ऑफ पोटेंशियल. आई विल जस्ट हाईलाइट सम ऑफ दोज प्रॉब्लम्स. क्वांटम कंप्यूटिंग, जैसे हमने कहा, सुपरपोजिशन की स्टेट में डिजिटल, कुछ इलेक्ट्रॉनिक वाले आई बिलीव होंगे, डिजिटल एनालॉग, यू नो, डिजिटल 0 and 1, एनालॉग, सारे डिफरेंट स्टेट पॉसिबल. बट क्यूबिट्स वन स्टेप अहेड, उसमें फेज भी इंपॉर्टेंट हो जाता है. So there are so many superpositions possible, but it becomes very susceptible to noise also. थोड़ा भी कुछ हुआ, environmental influence हुए, environmental factor किसी ने भी affect किया, qubit state changes, information that you are trying to find out is lost. और अभी तो quantum computer जो बने हैं, उनके काफी सारे limitation है. They sometimes they are very big claims, but they are not able to solve practical real world problems. They are good startings. some नए chemical simulations भी हुए हैं, but they are just the beginning. But things will change drastically in next 10 years thanks to this Gen Z. So Shor's algorithm में अगर हम जाएं, Shor's algorithm is nothing but algorithm by which you can crack almost everything. कुछ भी secure नहीं रहेगा, जो भी पासवर्ड वक्त बनाए कोई फायदा नहीं है उसका, सब क्रैक होने वाला है. तो वो करने का एक स्टेप है Shor's algorithm. बट ये algorithm को implement करने के लिए जैसे quantum computer चाहिए, वो भी बन रहे हैं. There are still work, lot of work has to be done to solve real world problems. Similarly, logical qubit people talk about, you will hear from other speakers. There are certain physical qubits, but physical qubits जैसा हमने देखा, they are very error prone. तो वो error से उनको बचाने के लिए normal case में हम उन्हें क्या करते हैं, एक the roadmap is there to convert them into logical qubits, so that लंबे operations हम लगा पाए. तुम लोगों ने कभी कुछ अपने programs run किए होंगे, they run for sometimes minutes, or even if कोई बहुत ही complicated simulations किए होंगे, they might run for even hours. But quantum computer में we are still sub-second regime में, जो कुछ करना है few millisecond में करो, खत्म करो, क्योंकि क्यूबिट उसके बाद बचेगी ही नहीं. तो केवल हम यही सबसे बड़ी लिमिटेशन है, हम जो भी कुछ कंप्यूटेशन करना चाहते हैं, इट शुड एंड विद इन फ्यू मिली सेकेंड. उसके ज्यादा कितना भी बड़ा क्वांटम कंप्यूटर बना लो, अगर जब तक लॉजिकल क्यूबिट्स नहीं है, तब तक आपको अपना प्रोग्राम उतने टाइम के अंदर ही सॉल्व करना होगा, खत्म करना होगा. तो इसलिए रियल वर्ल्ड कॉम्प्लिकेटेड प्रॉब्लम्स सॉल्व करने में अभी लिमिटेशंस हैं. सिमुलेशंस तो फैनमैन का ड्रीम था कि हम, क्योंकि क्वांटम हमारे जितने भी सारे फिजिकल सिस्टम्स हैं जिनको हम बात कर रहे हैं, वो उनको सिमुलेट हम क्लासिकल कंप्यूटर पे कर रहे हैं, उसकी जगह हम क्वांटम सिस्टम पे ही अदर क्वांटम सिस्टम को सिमुलेट कर सकें. दैट इज द बेस्ट वर्ल्ड, बट हाउ टू कोड दैट प्रॉब्लम, दैट इज अ चैलेंज. इंटैंगलमेंट, तो आई बिलीव थैंक्स टू दैट लेडी, शी हैज एक्सप्लेन्ड वेरी वेल कि दिस इज व्हाट इंटैंगलमेंट इज. एंड इंटैंगलमेंट के कारण देयर आर मेनी न्यू थिंग्स व्हिच आर इमर्जिंग, नॉट जस्ट communicating at long distance, but even finding out something which is not visible. जो अभी recent आपने wars में देखा, US was just able to enter Iran, सब कुछ भी, it was one way domination, पूरा domination था, at least as far as air force was concerned. But if we can develop certain radars which are not invisible, so stealth aeroplanes are also would not no longer remain stealthy. So that is one of the possibilities of quantum technology. Then quantum repeaters, how to copy or exactly clone a quantum device or quantum system without affecting itself. I am rushing through these slides because you know the time, I have only few minutes. So you can ask questions or you can even mail me. There are other speakers who will be delving on these topics. Then QKD is one such scenario on which here also work has started. DRDO, we are working. My colleague Santu will explain in detail what all DRDO is working in all these domains, whether this is quantum computing, quantum sensing, or quantum communication. There are limitations on quantum key distribution also. And then atomic clocks. So, how many of you have used the atomic clock? Atomic clock किसी ने use करी है? नहीं? नहीं, सबको ऐसा लगता है? लो कि तुम सब लोग ही यूज कर रहे हो एटॉमिक क्लॉक एवरी डे, क्योंकि द मोबाइल टाइम व्हेन यू सी दैट इज कमिंग फ्रॉम एटॉमिक क्लॉक, इसीलिए सबका टाइम सिंक्रोनाइज्ड है. सो यू एवरी डे यूज एटॉमिक क्लॉक्स several times on a daily basis. So quantum technology is not just far-fetched, जैसे quantum computing और quantum communication वाली बात है, but every day you are using atomic clocks, quantum sensors in your daily lives. इसी कारण से डेट पे ऑल्दो सभी अभी भी लेट होते हैं, बट जो टाइम से आप लोग पहुंच पा रहे हो या क्लास में भी जो पहुंचने की कोशिश कर रहे हो इज बिकॉज ऑफ दैट एटॉमिक क्लॉक ओनली. पोर्टेबल ऑप्टिकल क्लॉक, इनको कॉम्पैक्ट बनाना, दीज आर सम ऑफ द चैलेंजेस. सिमिलरली मैग्नेटोमीटर्स, सच पोर्टेबल मैग्नेटोमीटर्स आर बिल्ड. मे बी नेक्स्ट पर्सन, अभी एक दूसरे के बारे में भी तो बहुत हंस के बात कर रहे हैं, एक्चुअली कोई क्या सोच रहा है दैट विल बी एबल टू फाइंड आउट. दैट इज नॉट वेरी फार फेच्ड. At least intentions you will be able to find out, not exactly line of thought, line by line तो dictate नहीं कर पाओगे, but intentions you will be able to find out very soon by mapping the magnetic lines of forces at very high resolution. Then inertial sensors, अभी भी कई जो flights जा रही हैं, ये जो Gulf war है, ईरान यूएस वॉर में, the flights when they are going near to Iran, हमारे rescue missions भी हुए, some of my friends they are pilots, so when they are landing GPS is not available. So they are actually looking out of the window and trying to identify which building, which path, which turn, which corner to land the aircraft. So this is the situation. So we need inertial navigation sensors to come out of that situation. So even when GPS is not available, you are able to safely land your aircraft, even communicate. But our limitations are SWAP-C, size, weight, power, and cost. How to reduce that? That is the main bottleneck. Gravimetry is another such thing. You need very precisely, you can measure how the gravity is varying. Even underground tunnels, जो हमारे ये कई सारे attacks भी हुए हैं, people have used underground tunnels at the border to cross into India. Drones तो एक ऊपर का route है ही, but there are underground tunnels also with a very sensitive gravimeter. Even 10 meter, 20 meter buried tunnels, they lead to small changes in gravity in the nearby area that you can sense and find out. But the limitations are again speed and vibration. So because this is a very sensitive system, anything happening in the environment can influence the outcome, and you have to find out what was the real measurement. So this is more of a engineering problem that we have to overcome, or rather you have to overcome. Then topological insulators and very new materials are coming. Pure crystals, they are a new class of materials, not enough time to explain them. One example is this graphene. This magic angle graphene. So if you have two graphene sheets, just if the two layers are rotated by 1.1 degree, it may behave as even superconductor. So these are very new properties, exciting new materials that people have found out with the help of quantum technology, and hopefully they would be realized. But once again, raising them or growing them in large scale, reproducible manner, those are the bigger challenges. So physics wise it's fine, but engineering wise or technologically wise, it's the bottleneck. Similarly, quantum dots, this is one thing which has matured very well. Even these displays or the projector, these TV screens, some form of quantum dots or quantum technology is already being used. Even in your mobile screens, OLED screens that you see, there are lot of quantum built into your systems. But once again, several of these systems are based on heavy metals. So those things we have to control and develop alternate eco-friendly solutions. So this is basically the outline is or summary of my talk. So there are different technologies at different TRL levels. Some are mature, some are just evolving. But physics wise, there is nothing stopping quantum technology. But technologically wise, there are still many bottlenecks which you have to overcome. So engineering problems have to be solved. There's a lot of hype. Be cautious when you hear. You will hear very good, exciting things. but all of them may not be true or may not turn out to be true in future. So be grounded and stay invested in QT. Thank you.
Thank you, sir, for the Gen Z app explanation of such a heavy topic with ease. Our next speaker is a pioneer in India's quantum computing landscape. Dr. L. Venkata Subramaniam, CEO of Qubit Force and former IBM Quantum India lead, is a PhD graduate from IIT Delhi and an IBM master inventor. With nearly 40 patents and over 150 research papers to his name, he is also the author of the best selling book Quantum Nation, outlining India's roadmap in quantum technology. His expertise bridges deep tech innovation and national policy, making him a central force in India's high tech evolution. I would now like to invite Sir to kindly come forward and share his valuable insights with us.
Hi, good morning. It's a pleasure to be here. So I'm going to start with one question, okay, and the answer to that is very important for all of us. Which country has the maximum number of quantum scientists? Those who think that it is US. Anybody thinks US has the maximum number of quantum scientists? China? Japan? No raising of hands. No.
Just raise whichever is asking now.
Yeah, so those who think it's Germany, France, UK, India. Okay, I see some hands there.
India, just raise your hand.
Okay, so this is a very important question, and the answer to this is what we are going to discuss in the next 10 minutes. Okay. So, all of you know this mobile phone. 5 countries control the supply chain of this: China, Japan, US, South Korea, Taiwan. Where is India in this? Does India make any of these components in this mobile phone, this laptop? Actually, we don't make any of the products that go into this, but Indian scientists are the ones who do all the designing of the chips, all the buses, all the software, everything which goes in here is made by Indians, majority of that. But unfortunately, we control zero of this supply chain. We control zero of this supply chain. So, I asked you the question, where is the quantum talent? The quantum talent is actually in India. India has the maximum talent in quantum technologies. 2 months back, NPTEL, anybody knows what is NPTEL? Okay, NPTEL is India's online program where courses are offered by leading professors. A course in quantum technologies was offered, 2 lakh students registered from India. Before that, Washington Institute of STEM Education and Research launched a course, online course in India. 70,000 students registered. In their whole lifetime of I don't know how many years, 5 years, 7 years in the US, they have only trained maybe 10,000 students. But in one shot in India, they got 70,000. These kind of numbers are unmatched anywhere in the world. No other country is able to do this. No other country is able to create the kind of talent that we are creating, all the young people back there. I mean, you all gave answers to what is superposition, entanglement, all of that. So this kind of talent no other country has, okay, no other country. It doesn't exist on planet Earth, doesn't exist. You are that talent which is sitting here, and India already has the largest talent pool. But what are we lacking in? Products. All of us go and work for multinationals and all of those who use the talent, but the product is never ours. It is somebody else's product. The talent is ours, but the product is somebody else's. So we don't control any of this supply chain. In quantum, there is a national quantum mission. The goal of the national quantum mission is to control the supply chain of quantum computers out of India. Today there are 34 countries with national quantum missions of their own. No other technology, AI, cloud, blockchain, you pick it. There is no other technology which has so many national quantum missions. Only quantum has so many countries with this mission. Why? The reason is that quantum technologies, all the advisors, the strategic politicians, the scientists have been telling everyone that the country that takes the lead in quantum technologies is going to have dominance over Earth for several decades. Do we as a country want that dominance or do we not? That's the question to all of us. And the answer is we do. And that's why there is a national quantum mission. That's why there is a quantum mission in Amity University and several universities across India. That's the goal, to make sure that that talent which is there in the back rows today is building technology out of here, startups, Indian companies, all of that. And to enable this, there is a lot of funding which is coming in. Okay, so today you can actually open a startup and for the first time up to 25 crores, the government is willing to fund. There were no, government was earlier funding 50 lakhs, 60 lakhs, 70 lakhs. For the first time, 25 crores. You can, if you have a good idea, you can get 25 crores. And a lot of the people who are getting those 25 crore kind of funding today are young people like you. Okay. People under the age of 25, under the age of 30. So very young people are now coming up with these ideas and they are building technology because why? We want to control the supply chain of quantum computers right out of India, and you have to take that lead. And that's why Amity University has started this program. I was very happy to hear where you're building, a quantum program where you're enabling youngsters, where you're inviting startups and industry to come and set up offices here. And the goal is that this talent should not go anywhere else. It should sit here in India and build technologies. So to enable this, 2 weeks ago, we did something very special. For the first time in the world, we built quantum computers right in the open. Till now, people used to hide in rooms, build their quantum computers and bring it out and say, here, quantum computer, please don't open it, use it over the cloud. What did we do? We said the talent is here. Hundreds of students have already visited Amravati, those two quantum computers, and they were actually built by the students joining us. Several of the students from the local universities came and they joined us in building dilution bridges in India for the first time. We built We have gone down to 10 millikelvin temperature for the first time. It had not happened. We also, Dr. Santu Sardar is here. He built the control electronics for it. The qubits, you just heard, they have superposition and entanglement. They sit in that 10 millikelvin, 0 Kelvin temperature, close to that. How do they get controlled? Through room temperature electronics, which Dr. Santu Sardar and his team built in DRDO. The processors were made in India, ISC and TIFR. The flex wires were made in IIT Bombay. So, for the first time, a full quantum computer made in India, and very few countries have been able to do this. Okay, so our talent is on the move, and you people at the back, I hope you have used a quantum computer. Anybody who has not, who has used a quantum computer? Please go and type quantum computer online. There are several free quantum computers you can use. There is Quniverse from CDAC. There is IBM's System 2, which is also online. There are many. You can just type quantum computer and go and write a hello world program right now. And tomorrow, if I ask you this question, have you used a quantum computer? Please say yes, because it's very easy to use. It's free to use. You can just go online, type quantum computer there, use quantum computer, and you can use it. Okay, and remember, as I said, India is where all the talent is. In fact, the first time we offered this NPTEL course, 15,000 students registered. That was in 2021. Out of those 15,000, half the students were 12th class. 12th class kids had registered from India. It doesn't happen anywhere in the world. It only happens in India. This is special magic that happens only in India. And be part of this magic. So, thank you so much.
Thank you, sir, for that truly enlightening address and for offering us a glimpse into the exciting future of quantum technologies. Our next speaker is a key strategist in securing India's telecommunications infrastructure against future threats, Mr. Atul Gupta, sir, Scientist G and Head of Center of Excellence Quantum Technologies at CDOT. He has led significant advancements in quantum key distribution and post-quantum cryptography. His work is instrumental in building indigenous quantum safe communication protocols and ensuring the resilience of India's digital backbone in the quantum era. May I now invite Sir to address the gathering. Let's have a huge round of applause for him.
Very good morning to everyone. Very difficult to speak after Dr. Purnendu and Dr. Venkat. They are so prolific speakers, but I will try my best. First of all, many thanks to MIT University for this opportunity and all the logistic support it has extended. Really appreciate it. I will briefly cover what we are doing at CDOT in the area of quantum safe communication. I think a lot of background is already given by Dr. Purnendu and Dr. Venkat also, and I'm sure it will be covered in more detail by Dr. Santu Sardar. So just to start with what has happened so far, quantum sciences is exactly not a new thing. It has been there since a long time. In fact, it started in year 1900. And subsequently, the initial years in that century were very instrumental in formulating the concepts which we are now using. So if you see, it is more than 100 years back that real thing actually happened. And if we see the discovery of or the invention of transistors, lasers, etc., that is also based on the phenomena of quantum only. So that is in fact the first quantum revolution. However, it was in 1980s that Richard Feynman proposed the idea of using the quantum phenomena for computing, for speeding up the computing. And then many of you may be surprised to know that we talk about quantum key distribution. The first protocol for quantum key distribution, that is called DB84, based on the two scientists who worked on that, who developed that. It was actually presented in a conference in Bengaluru, probably in 1984 or 85. So these are the things which have happened in the past, few decades back. Subsequently, the important thing which happened in the 90s is the coming up of Shor's algorithm and Grover's algorithm, which tried to make things difficult from the perspective of securing the communication network. So I will try to briefly tell about that. So if we see the first quantum revolution in the 1940s has a very, very significant impact on the way we are actually working today, on the way we are communicating today, are all the devices that we are using. It is the transistors, lasers, MRE machines, everything is actually based on the phenomena of quantum physics only. So that was the first quantum revolution. Now we are entering into what is now being called as the second quantum revolution, where these things, the quantum phenomena, is now going to help us do certain things which are not possible with classical computers. So, and it has applications all across domains, different domains like the computing, communication, sensing, materials. I will specifically cover the communication part, but the impact, as the previous speakers already mentioned, spreads across all domains. And the reason why it took so long for the second quantum revolution is now we are in a position, the technology is now in a position where we can actually harness the potential that is offered by quantum phenomena. So earlier it was not possible because of the lack of the practical devices. So as I mentioned earlier, why there is a sudden quantum boom? Everybody is talking about quantum nowadays, and in fact last year was declared as the International Year of Quantum Science and Technology by UN. And equally important is that the Turing Award for 2025 was awarded to those two scientists who came out with the first protocol for quantum key distribution. So that is also a significant event because they actually came out with this idea more than 40 years back, but now that has got the recognition it deserves. Similarly, 2026 is the year of quantum security by Quantum Insider. So why that is all that is happening is also explained earlier by Dr. Venkat, that we are now in a position to move very quickly in coming out with what are known as cryptographically relevant quantum computers. So those computers which can threaten the security of the data that is flowing out the communication network. So that is where these are actually going to make a significant impact. So, and coupled with that, all major economies across the world, they are investing heavily in quantum. As mentioned, that India has its own national quantum mission, but all major economies, including US, China, European Union, Japan, Singapore, they are investing heavily. The advancement in AI coupled with quantum technology, coupled with quantum phenomena, is also having a significant effect in speeding up the thing. So these are the reasons why all of a sudden there is a too much of attention on the quantum phenomenon. Coming to the why there are what is the problem that quantum brings as far as the communication networks is concerned? As I mentioned earlier, that Shor came up with an algorithm in 1994, which is again known by his name only, Shor's algorithm, Peter Shor. So what it can do is that if given a sufficiently sized quantum computer, it can break the algorithms which secure the communication network that we use today. So that means whenever we are doing any transaction over the internet, let's say doing a financial transaction, there is certain algorithms which are in place to secure the information from anyone who is not a legitimate recipient. Now, if that algorithm gets broken, then it is very easy for anyone else to find out what type of transactions are happening, and that is certainly not advisable from an individual perspective and from country's perspective, where state secrets, defense secrets, etc. may be in transit. So Shore's algorithm does that, Grover's algorithm came up subsequently. And finally, we have what is known as harvest now defibrillator, that even if you don't have a sufficiently sized quantum computer now, what you can do is that you can store the data and maybe decrypt it after 2 years, 3 years, whenever the quantum computers become available. Because a lot of data that, particularly the organization data, is sensitive for over a large period of time. So we need to keep it secure. Now, what are the recent developments? Again, Google, you must have seen in the news also that they came up with this Willow chip, and which showed verifiable quantum advantage. That means it promised to actually speed up compared to classical computer, and that happened in last year. And they also announced a plan to secure their systems against quantum computers by 2020. Now all countries are coming up with deadlines by which they want to migrate to post-quantum scenario in their communication network, so that the data that is in transit remains secure against quantum computers. And they have set different deadlines. Like US has come out with 2035, but Google advanced it by 6 years. So that shows that there are a lot of things which are happening, which are making such steps important. Then another company, IonQ, they have their roadmap. They claim to come out with a quantum computer which can break such type of algorithms which are used in securing networks by 2028. So that's not very far away. And similarly, AI is also accelerating the quantum day. So these are the threats which quantum computing particularly brings to the communication networks. Now we have two approaches which we conventionally talk about. I'm sure must have heard about these. One is the approach which tries to make the algorithms harder even for the quantum computer to break. So it is a mathematics based approach, and come out with quantum resistant algorithms. So this is what is known as post quantum cryptography. You can go to NIST website. NIST is a US agency, NIST. And they have come out with standard for post-quantum cryptography. So this is one aspect through which we can secure our communication. So herein, I just want to clarify, here in this post-quantum cryptography, there is actually nothing quantum as such. It is based on mathematics. But since it secures against quantum computers, so the name has been given as post-quantum cryptography. The other approach is actually uses the phenomena of quantum physics, is called as quantum key distribution. And this is the another approach which can provide actually information theoretic security. That means security is not based on any assumption. So certain strategies are in place for migration to post-quantum. We can have post-quantum cryptography with the classical crypto that we currently use to make it's a hybrid approach, which is good for large-scale deployment, and we can club PQC as well as PPD post-quantum as well as quantum key distribution. So provide the highest level of security, because implementation of any of these systems invariably introduces certain weaknesses, vulnerabilities which can be exploited. So a hybrid approach is something which keeps the thing secure. Coming to CDOT, what we are doing in the area of quantum key distribution, we have developed solutions, deployed it at many places across India. Our approach is to come out with cost-effective field deployable systems which can be used in actual field, in laboratories for carrying out experimentation that I will show you. Besides this, we are also working on devices like single photon detectors. So these are very important devices because they are used across different verticals of quantum technologies. So our motivation of developing such devices is to reduce the cost of quantum key distribution. So these have been indigenously developed at CDOT, and these are, I will show you that at different places where they are already installed. Similarly, we also have a portfolio of post-quantum cryptography encryptors which support post-quantum algorithms. So they are based on layer 1, layer 2, different layers of which are used in the network. And we have solutions through which we can make wireless links, point-to-point or the hotspots quantum secure. Similarly, there are solutions to make the voice communication secure against quantum threats. So these are so we are essentially in the area of product development, coming out with indigenous solutions in the area of QKD and PQC. Now, just to illustrate, since this work began a few years back at CDOT, we have done a number of trials in various networks in defense. And more importantly, we actually commissioned the link between our parent ministry, which is the Department of Telecommunications, which is located in the Sanchar Bhavan, and they are getting all their connectivity from NIC, which is around 16 kilometers away from that office. So they wanted to secure that link against any potential quantum threat. So that solution was deployed in February 2023, more than 2 years back, and it's operational since then. So the objective is to actually carry out the testing in the real world environment. Then these are certain commercial deployments which have taken place in various academic institutes. The most recent one is at the Mahindra University, which happened last week, and we deployed because they wanted to set up a quantum communication laboratory. Similarly, we have installations at NSUT Delhi. We have at B.Y. Patil University, Mumbai, JIT Noida, ARNET India, as well as a couple of links we have deployed in DRDO labs as well through a content. So I'm sure MSc will also consider a solution, and probably by next year we have this type of system. Certain awards that have been won at various events. So just to conclude, as already mentioned, National Quantum Mission is already here. It is actively supporting academia, industry, startups, government R&D labs in coming out with high TRL products, mature products which are field deployable, starting from the basic R&D. And equally important is that the curriculum has been finalized by AICT in consultation with DSC. That has also been released for UG and PG. I think some mentioned earlier that MIT has already taken steps in having a program in that direction. And as CDOT, we are ready to partner with all academia, industry, startups for furthering the cause, because what I believe is that quantum technologies require multidisciplinary skill. So it's not that only a person with quantum physics background can come out with a solution. They are essential, but they are necessary but not sufficient. So we need people with different background, diverse background, computer science, electronics, material science, thermal engineering, etc., to come out with products and solutions. If we need to actually sustain the actual objective of the National Quantum Mission nurture rate, then we need to come out with the products, not leave it at a TRL 4, TRL 5. So that will not really help anybody. So that's my limited submission. Thank you for your help.
Thank you, sir, for your insightful address. Our next speaker plays a vital role in the National Supercomputing Mission, Dr. Abhishek Tiwari, sir. Associate Director and Scientist F at CDAC Noida, focuses on the intersection of high-performance computing and emerging software frameworks. His work involves developing scalable computational models and software ecosystems that support complex scientific simulations, laying the groundwork for integrating classical supercomputing with future quantum accelerators. May I now invite sir to please share his insights with us.
Have a huge round of applause for sir.
Can you share the PPT? Yeah, hello all. First of all, I just want to thank Dr. Chandramurthy sir for inviting this, because it is always very good to face the students, and I have seen one of the biggest crowd of quantum computing. What I like in many workshops, I regularly go to many workshop conferences, but this seems to be a very good number with respect to quantum computing, what I saw. So you means earlier, sir, sir, and Atul ji, and even our very Venkat, he have shared a very good glimpse of what kind of solutions, facilities, and all have, and how students can be benefited. So I'm not going to repeat those things, because those are already the building block on which we all are working. I just want to explain the solutions on which exactly we are working, how it is going to help, because there are a couple of solutions which CDAC Noida is working, and this doesn't require in the day one itself accessing a quantum computer. Because see, with our PCs also, we can start coding for quantum computing. What we need is a basic Python language and a basic knowledge of quantum mechanics. So just to tell you, quantum computer or quantum computing applications, whether it is acceleration, this all solutions comes is a hybrid in nature. So it is not means right if I say that only a specific quantum computer is required to run your applications. Finally, it is hybrid. So somewhere it has to connect to our general PCs, supercomputers, and only the accelerated kind of application has to be ported to the QPU. So hope I am able to understand. Like at present, what we have is, we have IBM Qiskit, we have Penny Lane, we have Rigetti. Before building a quantum computer, long back, they have already made their software platform. A simulation platform by all these companies has been very long back made, and I think since means 8 to 10 years, many people has been using it. Many students have been using it. I am not sure whether Amity student has started using or not. So these frameworks are already there, and that is actually the one of the best start of entering into the quantum domain. So means any CSC student, any AI student, and any VLSI or EEC student can also start working on quantum. So myself, yeah, means again is a VLSI, background. So I choose to use FPGAs for implementing quantum algorithms. So GPUs nowadays has been very much in sale. The cost of GPUs has also increased. One of the reason of this is all the quantum algorithms, whether it is simulation or what, is being run on GPUs because they have the more memory, computation power, tensor networks and all, which actually is required to run this high computational tasks. But once we go on GPUs, a lot of built-in libraries, means NVIDIA gives, whether it is in the name of CU Quantum or it is the name of CUDA. So these built-in libraries comes as a part and parcel of their simulation platform, where student gets only a top UI view where they can use the libraries, make their circuit and simulate. So finally, what we lose there. So for starting, CPUs and GPUs are fine because once we start, we should know how the things actually happen. What change will happen if I am going to use a FPGA? We have to build that full kernel, the full stack which NVIDIA has made by using CU Quantum, CUDA Quantum. That has to be self-made because everyone knows FPGA is a very bare fabric. It is just a sea of gates without any operating system. It is a bare metal hardware. So simulating any quantum platforms on any reconfigurable actually requires building the full stack. So that is one of the accelerator cards which we have used. We have used the off-the-shelf Xilinx LVO accelerator card, which is actually, you can say, a counterpart of any GPU cards, but it is much cheap than that. So normally 4 to 5 lakh this card is there, and it has HBM memory, which is actually one of the core requirements. Once we go up simulating any quantum circuit, memory is one of the core requirements because every quantum circuit comes in the form of matrices. Storing matrices requires high memory. So we have a memory, we have a ultra scale plus reconfigurable FPGA hardware bare fabric. So this is one of the work which AUUP Noida has taken up. We have completed it successfully, filed a patent also onto that. So in this single card, 30 qubits of state vector simulation and 12 qubits of noisy circuits we have simulated. So it is very much equivalent to any GPU card. So before explaining this, what actually I want to tell that any student can start with their PC itself. Python is the top level, high level language in which any quantum algorithms can be developed, simulated, and do. We should not wait for a quantum computer to actually start this work. That quantum computer access is sooner or later is going to come. Dr. Venkat is very actively involved in this to actually fill this gap. But before we get it, we should be ready because the algorithms has to be ready. We are doing like that only. So like this platforms are there. I'll just explain one by one. The main objective on this platform is we have built a simulator on FPGA. So this simulator and the full framework we have already installed at two places. So Sharda University, CDEC Noida is actively involved in consulting them to build a center of excellence in quantum computing. So when we talk on quantum computing, everyone should know there are two separate domains. One is quantum computing and one is quantum communication. When we talk of quantum communication, QKD, PQC, these all things come. Once we talk of quantum computing, we should see how quantum algorithms can help to be a use case to accelerate the application. So at present, the algorithms which we are implementing on GPUs or which we are optimizing using our high performance computers, what CDEC gives in the name of super computers, where supercomputers takes a lot of time to simulate. If a QPU is there, how much time it takes? So it is one of the core requirement how quantum computing and quantum machine learning can help to optimize this. So that is one domain which is a bit easy to tap because only a PC or some accelerator card is required to start with. And we need to find out the good use cases where actually quantum computing fits. That is one of the things which we need to find out. Many good use cases of computational fluid dynamics are there, weather and climate modeling is there, which at present we are doing on our high performance computers, which CDEC is also thinking to, off the shelf to a quantum QPU where a very less time is being taken. Couple of use cases we have tested and we are on the path to change this from a supercomputer to a QPU. So in this, what actually is required, where actually we are hitting the wall. So once we go for a quantum computer, if you see, if I am simulating a 30 qubit system, we need 1 billion complex, means amplitude, exponential amplitude, matrices size is required to simulate it. So, and access of real quantum hardware still is a bit far. So we can take these accelerator cards, whether it is a GPU or it is FPGA, start simulating. The day we get the quantum access, we can directly port it. What difference will come is of the noise. Coherence noise is one of the things which we need to see. This also we have to simulate. So these simulators which are developed on GPUs or FPGAs, they have built-in inputs for adding noise to make it very near to a quantum computer the day we are going to port it. So main core of any simulator is we need to have a state vector formalism. So if basics of quantum computing someone is going to start, they should understand there is a circuit which is not having any noise. So that everyone can do in their PCs, in their GPUs. But that surely is not directly going to be ported on any quantum computer because every quantum computer, whether it is a superconducting qubits or ion trap, it will have a built-in noise with respect to their decode coherence and stability. So for that, density matrix and noise simulation is also required. Now there are multiple kinds of noise which has to be simulated. It may be a bit flip, it may be a phase flip. So that once we study, we'll know. To take care of that noise, one more framework is there of quantum error correction. So means as told, these qubits are very short-lived, So we need to see that out of physical qubits, how much logical qubits we are going to take. To actually take that out, QEC, quantum error correction is required. And these algorithms also can be very easily implemented on any classical kind of hardware. So the day we go for get a quantum computer, we will be ready with a simulated platform which can be very easily ported on that. So I'll just jump some of the things. I just want to show top level architecture how this hybrid classical quantum infrastructure is there. If you see here, we have a super computing infrastructure that is connected to a GPU node, a vector node and a FPGA node. So a GPU takes care of if someone wants to simulate a quantum circuit on GPU, he can use that GPU node. If there is some specialized which needs vector calculation, vector node can be used. And if there is a VLSI domain, students are there and who want to build the full circuit from scratch, so FPGA node can be used. So this platform, I think every college should have, because this will make them ready to simulate, understand the full flow, and that is not very costly also to actually have. So finally, a full stack to superconducting quantum computer looks like this. If we see from the lower level, we have a QPU which may not be visible to us. On the top of that, we will have a control stack. On the top of that, we will have a interface which will have some proprietary instructions in relation to that. And from there, it will be a high level language of quantum algorithms. It may be in the form of Python, which has noise built in, or which has the capability to handle the noise. The full infrastructure is, when we talk of acceleration, means we are using classical supercomputers to do the management related tasks, whichever is a compute intensive, that can be offloaded to a QPU. So that way this infrastructure takes care. So for that we have a quantum computer, we have a dilution refrigerator. This full interconnect can be connected via any high speed interface, and we can do that. So full integration of quantum circuit, if you see that left hand side, HPC and QC are there. HPC will have multi-core CPUs. It can be connected to a quantum computer, and the task can be offloaded based on that. So this is one of the basic framework or a real framework which actually we are going to face. So at present, in case we are not having this QC, what I am telling, the accelerator card for now can be used as a QC. That is what we are working, and it has been fully proved. So this is one of the framework on which CDEC is very actively working. We have our supercomputer, and which is connected to QPU, and this full interface finally will be like this. So a complete infrastructure for a hybrid quantum HPC computation will look something like this, which I am telling at present to replace this via accelerator card till we have this access. So QML also is one of a very core domain. So one of the use cases which has been funded by MIT, and we have proved weather and climate modeling, getting a data from satellites, forecasting was a use case which supercomputers used to take a lot of time to predict. This we have proved using quantum computing, and it takes a very less time now. So it takes in microseconds. So this is one of the use case which has been proved by quantum computing, can be one of the areas which actually is going to fit for a quantum applications. So this I am just telling the block how it is going to be divided. We have a classical processor and hybrid quantum training with encoding and all will be implemented on quantum computer. And this has been proved. We are working with NCMR, WF, National Science Center for Medium Forecasting, and Indian Meteorological Department also. So just want to tell, it is like, it is not theoretical. It is actually in real time, everything is going to work, but we need to start coding, and that can be very easily enabled from our PC itself. Okay. Thank you, sir.
Thank you so much, sir, for your inspiring words. Our next speaker is leading a dynamic team of young researchers, Dr. Santu Sardar, sir, Director DYSLQT at DRDO. He is at the forefront of applying quantum mechanics in defense to areas such as quantum computing, communication, and sensing. His lab has achieved critical milestones, including the development of indigenous quantum random number generators, while fostering a startup-like innovation culture within the government framework. We are honored to have Sir join us virtually. May I request him to kindly address the gathering? Over to you, sir. Let's have a huge round of applause for him.
Yeah, hello. Yeah, am I audible properly?
Yes, sir.
Yeah. Good morning, everyone, and thank you very much for inviting me in this event. It's a delight, but sorry I couldn't attend in person. So, after the excellent talks from the previous speakers, I would like to complement with some additional information on what DRDO is doing on quantum. So, as our Selvamurthy sir suggested or told that we have to be Atmanirbhar in this critical technology. Yeah. So, what has been DRDO's efforts towards it, and then how we are working and planning our future activities towards that. So that I will be briefly highlighting as the time is short. So whenever I am talking about DRDO, it means DRDO in collaboration with academia and industry. So please keep that in mind. So as we know, globally, there has been good amount of investments on quantum technology. So various countries like China, US, and there are many other countries who are running on their own quantum missions. EU have their own flagship programs, and India also recently launched National Quantum Mission. But now there is a critical aspect here, which is export control. So Atmanirbhar, we have to be Atmanirbhar to avoid the export controls on quantum technology, which is already started. And also we have to be a sovereign country and keep our technological edge both in battlefield as well as various other scenarios, civilian applications. So in those directions, the approach of DRDO has been twofold. So we are working on different aspects of quantum technologies, both quantum computing, quantum communications, sensing, metrology, and there are various other supporting technologies which is actually helpful for quantum. So basically, when you are talking about a system level implementations and solutions, it's a multidisciplinary approach. So DRDO is working on two different fronts. So one parallel approach is building the expertise in-house towards the product to leapfrog on the usage. And on the other end, we are developing how to make indigenous support solutions and ecosystems towards it. So basically building technologies to have its own important import substitutions to avoid the export controls. So towards that, DRDO is closely working with various industries and academia and in coordination with our National Quantum Mission. And we have various facilities. So our lab, which is DOSL-QT, this is specifically dedicated to work on quantum technologies. And also we have various other facilities like QTRC, then how we are enhancing the capabilities of our academias and students specifically to build up good human resources in India. So we'll be describing that. DRDO had its own quantum roadmap in early in 2019, which was approved by our Secretary DDR and Chairman DRDO. So these are some of the major focus areas in our national quantum, in our own quantum roadmap. So in communications, we are focusing both in fiber-based as well as free space quantum communications for long ranges. Then we are recently exploring quantum networks, memories and repeaters, what Purnendu sir was mentioning. For MDI QKD and future QKD systems, we are planning how to make a chip-based solutions towards it. And also high altitude platform-based QKD, how to, what are the different aspects of it. In quantum computing, our idea is to make complete ecosystems. So till now, we are exploring in two different approaches. One is superconducting circuit-based approach and another one is quantum dot-based approach. Both are in collaboration with academia. Quantum algorithms for cryptanalysis and various other defense applications. And in future, we are also planning to work on cryogenic controls and quantum error correction. In sensing, our major focus is on magnetometers, atomic clocks, navigations, imagings, and radar and seeker technologies. And to support all these three branches, we need various basic research support. So for that also, a good amount of work has been already initiated. And also, there is a good thrust in DRDO towards post-quantum cryptography. So there are various labs in DRDO who are working towards it. So one lab is our lab. This is DOSL-QT. We have other labs like SSPL, RCI in Hyderabad, SAG, JCB in Delhi. CARE, they are working on PQC, and NPL, they are working on various application aspects of naval sensors, mainly magnetometers and other things. So just to brief about our lab, so DOSL-QT, it was basically a brainchild of our honorable PM. So his idea was that let young people give challenging opportunities and flourish towards cutting edge technologies. So with that, actually, our lab started very recently in 2019, and we are currently 11 scientists strong, and we are working on 4 different aspects: quantum computer implementations, magnetometers, quantum random number generators, and QKD. QKD is a multi-lab effort. So, but along with that, there are various other efforts in DRDO. I will briefly highlight. So in quantum random number generator, our approach was to first demonstrate it on a lab and then making a portable prototype, and that we have achieved, and then we have given TOT to a private industry. And it was also tested in army setup as well in Delhi in Anand Parbat military stations. Currently, we have 4 different flavors of QRNGs at different speeds, and they have different advantages. So one is BPL based, branch path logic, then TOA based, time of arrival based, vacuum fluctuations based, and quantum phase noise based. So all these approaches are different approaches having their own different advantages and application domains. And these are tapping different random phenomena that is available in quantum domain. Another approach is our multi-lab approach towards QKD, both fiber and free space. So DRDO early in February 2022, we have demonstrated outdoor QKD for more than around 100 kilometers in between Prayagraj and Vindhyachal. That was one of the first field demo in India. So then we take up that proof of concept demonstrations, and very recently we have made certified prototype solutions in collaboration with an industry to so that it can be readily deployable and can be interfaced with crypto subsystems. That also our multiple field testings has been done, demonstrations. Our work on MDI QKD is on chip scale solution for MDI QKD demonstrations. So on that we are collaborating with IISc. And in free space, major collaboration is with IIT Delhi. So they are building to building around for more than around 1 kilometer demonstration that has been recently done in mid last year. And we are working on various aspects of free space QKD, how to enhance the distance further, now how to make multiple components and subsystems indigenously made in collaboration with academia and industry. Another work that our lab is working on is superconducting circuit-based quantum computer development. So on that, this is the complete structure that we have worked on. So basically, at the heart of the quantum computer is our quantum processing unit. Quantum processing unit, QPU. So this QPU design and fabrication was done in TIFR Mumbai facility. This is inside a cryogenic setup. Our main focus was towards the control and measurement electronics, then automated calibration softwares for these QPUs, and the software layers, so that user, when they apply target their quantum algorithms or circuits, quantum gate operation, they need not bother about the internal hardware that is required. So they will have a IBM Qiskit like environment, and they can readily use our system. So for that we had cloud access facility also, which was developed by TCS. So our approach was twofold here. So first we tried to demonstrate using the quartz-based solutions for the control and measurement circuits, and then this is the overall setup. This is the qubit, this is the qubit structures, and this is one snapshot of our complete quantum computer setup. In parallel, what we have done, this complete controlled electronic solutions, we have converted into a single FPGA-based solutions. So the advantages are multifold. First of all, we have our indigenous solutions for this control electronics. And basically, when I'm talking about control electronics, it means it can perform automated calibrations, control, and measurements, all the 3 operations simultaneously. So it's indigenous solutions with very low form factor, as we can see, and the cost is also reduces multifold. And at the same time, the design is such a manner that it addresses the scalability also. So when we require more than hundreds and thousands of qubits, so basically multiple FPGA boards we can stack in daisy chain manner to address the scalability issue. So this also we are giving TOTs to private industries, and one of the TOT partners in discussion with us is Qubit Force. Venkat sir is also here. And as Venkat sir was also mentioned that very recently, Honorable APCM Chandrababu Naidu sir, he has inaugurated the Open Quantum Systems, where our country electronics board was one of the major component there. It's very recently in 14th April. So this we would like to take it forward towards scalability of the country electronic solutions, and in future maybe we'll work on cryogenic country electronic solutions in collaboration with Qubit Force. Another activity that we and other labs in DRDO jointly were working on is atomic magnetometer. So as you know, magnetometer has various applications, as Purnendu sir also correctly pointed out. And but currently in India we don't have any indigenous solutions. So we are working on quantum principle enabled magnetometer, atomic magnetometer using atomic vapors at room temperature, which have a very high sensitivity. So there are very few global OEMs also, but there are also lots of export controls are there, whereas we have developed a performance which is almost at par with them. Now, with TFR Hyderabad, we have made a lab solutions, lab-based demonstration, and then we have made lots of engineering challenges and changes in it addressed so that we can make a portable solution. So currently, portable solutions is made, and then we are performing lots of outdoor tests. And very recently, we will go for TOT for this atomic magnetometer also. In DRDO, there are various other labs, as you were saying, were working on various other aspects like RCI, SSPL. So they are working on our cold atom interferometer based sensors like gravimeters, accelerometers, gyroscopes, co-magnetometer based gyroscopes, then Rydberg atom based sensors, atomic clocks. So all these aspects we are working on from our defense applications point of view, but there are various, these are dual use technologies. Some of the other activities in DRDO is on quantum algorithms. So here cryptanalysis related exploration is already ongoing jointly with IISc Bangalore. And we are also exploring various other applications like aerodynamic structure design, real-time path planning, mission allocations, predictive mission analysis, material discovery. So on this also we are thinking of exploring in a big way with academia. So good amount of discussions and work initiation has been started. PQC also is a good work activity is also going good. So nodal lab is care and good amount of collaborations is already there with various academia and industry. SSPL lab being a device physics lab, they have also demonstrated vertical cavity surface emitting lasers, VCSEL lasers. And these lasers were actually tested with our magnetometer setup in our lab in DSL QT. And in future, we plan to use VCSELs for our magnetometer to make the form factor even smaller. There are other various defense sectors initiatives like Army, they have set up one center in MHO. There are IDEX challenges and various other demonstrations to RM and other dignitaries. Just to summarize, so DRDO, they have started activity way back in 2016 with the start of cold atom project in RCI. Then in 2018, our QKD activity started, our lab started in 2019, and after that, good amount of steady developments and growth was there. Very recently, in the last year, we have demonstrated our magnetometer in an outdoor naval environment in a lake. And last year, we have developed our QRNGs, those were also independently evaluated, and then our custom boards for quantum communications, and of course, quantum electronic solutions. So, in the National Quantum Mission also, DRDO has committed for around 700 crores in the National Quantum NQM budget. And we are closely working with National Quantum Missions, and we are trying to complement the efforts of National Quantum Mission with our own roadmap, which is started way back in 2019. So now, with this brief highlight, I would like to focus on aspects of what are the collaboration opportunities in DRDO, which will be very helpful for academia, startups, and also the students who are available here. So for academia, DRDO have various approaches like contract for research services, CARS. For low TRL level activities, we have ERIPR, and DRDO have various COEs, Center of Excellences. Almost 16 of them are there. So among them, multiple such centers have quantum technology as their own technology verticals. So through that, we can work towards granting net projects, and these projects can be taken up jointly with industry also by the academia. For the students, we have recently introduced paid internships. We have GRFRA positions, and DRDO recently have a plan to recruit steadily every year for a good amount of students from Indian academia. So I will request students to keep looking the RAC website, Recruitment and Assessment Center, rac.drdo.in. For startups, we have various approaches, and currently DRDO is very keen to support our startups and industries in a very big way. So there is technology development fund where almost 50 crores is the amount that DRDO is willing to invest together with the industry for a particular technology with sufficient TRL levels, or even for deep tech also there is provisions. We have options called development come production partners with DRDO, so that industries can be involved from the beginning of the technology itself. We have development contracts through Grantinet also, industry can be involved. We have Dare to Dream for various startups, industries, or even individuals also can apply. And if they are properly, if they have sufficient merit, they can be funded through TDF as well. And from our side also, we are very much keen towards transfer of technologies as various activities. So as I was saying, for our activities like QRNGs and quantum computing, we have already started giving TOTs. For magnetometers and QKD also, we have initiated the efforts. So these are some of the opportunities that our academia, students, and industry can tap to jointly work with us. And just to conclude, as Selvamurthy sir suggested, we have to be very much Atmanirbhar for Vikshit Bharat, and quantum technology being a kind of new technology frontier, we have to be moving very fast, and instead of incremental advantage, we have to go towards leapfrogging. So for that, we need strong collaborations, mainly from various national agencies, but also international, maybe at a later stage. We need a very smart planning and parallel initiatives. So in that, I'm very much happy that Amity also have their own quantum missions, and maybe we'll discuss further about how we can complement each other. So with our various startups like Qubit Force coming up, I think we are going in a very good directions towards making a self-sustainable ecosystems in future, so that academia can develop the manpowers and then they are absorbed in our Indian industry, so that we can avoid brain drains and progress faster towards quantum technology self-reliance. So I am happy to take any suggestions or inputs from anyone. So this is my email ID. So feel free to please contact me. So with this, I would like to conclude, and sorry if I have overshoot my time. So best wishes for this event. Thank you.
Thank you, Dr. Santo. Well, best wishes, congratulations for the excellent work that you are doing in this life sciences lab.
Thank you, sir.
Our blessings to you, and I'm sure with all the contributions you are making in this area, Amity would like to also look at how do we partner and contribute to your endeavors in DRDO. And I have 3, 4, I think I got 6 senior scientists from DRDO sitting here. We would like to make a significant contribution. Please visit us sometime when you are here, when you visit Delhi NCR next time.
Of course, sir. Of course, I will do. Sorry, I couldn't be there today due to some other engagement, but I will surely be in touch and try to visit. Would like to see how we can jointly work. Thank you very much.
Let's give a big clap to that country.
Thank you, sir.
Thank you, sir, for your inspiring words.
Now, back to our Chancellor will address now. Please, I will request you. Let's clap for our Chancellor, Dr. Atul Chauhan, who has joined us today. Thank you so much, Chancellor, sir. And I know that you just came back only day before yesterday, and you were You still with so many engagements, you have still found time to be with us and then enrich our game. And you have launched quantum missions and you heard all these experts, they are all willing to work with us and we need your blessings and go to the chancellor for this effort.
Dr. Sarmurthy, thank you so much. I had committed to you I would be there in person, but something very urgent came up. But I'm so happy that for a few minutes I am able to come online and be with all of you at this most important symposium that you have organized on advances in quantum science and technology. Um, for all the young students who are sitting here in the audience, I'm told that they are students of Amity schools, are brilliant students, and Amity University. Dr. Selvamurthy is one of the most dynamic, hardworking, impactful people I have met in my life. And as young people, you should always look up to leaders. Even at this young age, the energy that Dr. Selvamurthy has, very few people have. But what is most important in him, and this is something that our honorable founder president, Dr. Ashok Chauhanji, tells all students for the last 30 years, that in life to be successful, your technical knowledge, your degree will only take you 20%. But 80% of success is on behavioral science. How you take care of others, how you interact. And that is where Dr. Selvamurthy is an absolute master. Over the last, Dr. Selvamurthy, it's been 15 years now that we have been together, that you took over this leadership position to ensure that the Amity system goes ahead in the field of science, technology, and innovation. But I've always seen, Dr. Selvamurthy, that wherever you go, any organization, especially in the DRDO where you were there for 30, 40 years, the amount of respect, the amount of love that Dr. Selvamurthy gets is absolutely unparalleled. And that is because you have always taken care of people around you, Dr. Selvamurthy. We are so privileged and so honored to have you as part of the family for so many years. So thank you, Dr. Selvamurthy, for that.
Thank you.
And students, this is the inspiration that I want you to take, having listened to Dr. Selvamurthy by all of you. And today I was told a lot of very senior members of leadership of Amity are here. I will not name all of them. I can see many of them. I am absolutely so proud of what everyone contributes to the growth of Amity. I'm told for this specific event, Dr. Gopal Bhushan, Dr. Sneha, Dr. Vaibhav, Dr. Nitasha Hastir, Dr. Monica Kaushik, Dr. Anuranjana, Dr. Vengmay, Dr. Ashish Mani, all of you have worked very hard for that. I congratulate you. It is quantum science and quantum technology, as all of you know, is very, very close to our heart. Last year, we launched the Amity Quantum Mission. And this is really because of multiple factors. The main reason is because when our founder, Dr. Chauhan, established the Amity system so many decades ago, now 3 decades ago, with the Amity schools and the Amity universities, Dr. Chauhan's main desire and mission was that how can we nurture most brilliant youth that will contribute to taking our nation forward. Now, today, anywhere you go in the world, everyone speaks that India is one of the great nations of this planet. Dr. Chauhan's deepest desire always was and is that Amity should be at the forefront in leading India to becoming one of the greatest superpowers of this world. And that is why he put Amity on this mission of having a deep responsibility of inculcating a passion for innovation, for science, for development in our young students. And today, if we look at India, if we look at our country, and some of the speakers today had touched upon that, what we need to achieve is to become a product nation. To all the young students who are there, you would have heard our Honorable Prime Minister and many of the leaders of our country speak about that. We Indians, and I travel all over the world, and everyone accepts this in the world, that we Indians have the best brains in the world. If you look anywhere in the world, any product, whether it is software, components, hardware, there is definitely an Indian brain behind that. But what we need to now look at as a nation is, how much does that belong to our country, India? How many products are coming out of our nation, are being used in our country, are being taken outside of our country? And that is what we have to work on, because if we do not become a product nation, we cannot become a superpower of the world. And at Amity, this is what we are passionate about. We are now working with some of the leading universities in the world to work on how to inculcate the right way to innovate. And we had many faculty from top universities like Stanford, from Rice University, and we're now partnering with many more on need-based analysis for innovation. In our country and many places, it happens that scientists are working on research areas, and by the time they complete and conclude their research, what is the applicability, what is the use for society of the research that they're doing? So we are wanting to bring this need-based analysis before you start. And every one of our scientists will be doing this, and we will be training our students in this philosophy that even before you start innovating, even before you start research, you undergo this very scientific process of doing a need analysis of what you want. And that, we are convinced, will transform the way innovation happens in our country, and it will transform the way we as a nation can come out with products that we can proudly say belong to our country, belong to organizations, belong to individuals in our country who are part of our country. And that is why I was delighted today that Dr. Selmurthy and all the organizers, that such brilliant leaders in the field of quantum technology have come on campus today and have spoken to our students. I'm grateful to Dr. Chaturvedi, Dr. Subramaniam, Dr. Gupta, Dr. Tiwari, Dr. Sadar, who was online, we just heard. All of you are doing tremendous work. You are such great leaders in the respective fields, but the fact that you have taken time to come today, motivate the youth of the future, we are extremely grateful. And Dr. Salmurthy, I'm sure we will have many more future interactions with everyone who has come here today, because we have a very clear vision that whatever is required for our nation to become a superpower in this world, Amity will be doing. And this Amity quantum mission is a really important step towards this vision that our founder, Dr. Chauhan, has set us on. Certainly with that, I will just conclude, but to all the young university students and also our brilliant school students, I'm always so amazed, and I'm told Dr. Lalit is also there, who's helping our chairperson inculcate the sense of innovation, that hundreds of our school students at the age of 13, 14, 15 have filed patents. This is the passion of our chairperson, Dr. Mrs. Amita Chauhan. Over the last few days, there is this most amazing program called Virons happening on campus, which is, I think, young researchers in natural sciences, where we have students from dozens of countries who have come I think in between the ages of 13 to 17, who are all brainstorming. And this is the real strength of Amity. We have universities across the country, we have universities across the world. And when we set up these missions like the quantum mission, Dr. Silmurthy, I was so happy when you announced on the launch that when you analyze that across our Amity universities, how many scientists are working in the field of quantum, you came up with that. I think over 65 of our colleagues were working. And is that correct, Dr. Silmurthy?
Yes.
All right. And I think in the field of science, in the field of innovation, when people can work together, that is when real exponential growth happens. So, to all the young students who are here, you are the future of our country. Our country will become one of the greatest nations. And today, if all of us, everyone who is sitting on stage, if all of us believe in this, it is because we have trust in you as the youth of our nation that you will work extremely, extremely hard. You will learn from the leaders of today and you will transform our country. So, with that, Dr. Lamurthy, and to everyone, my best wishes for the whole seminar, and to all our guests who have come, our deepest, deepest gratitude for what you are doing for our nation. Thank you.
Thank you, sir. And we also request you to launch our website. You wanted the website to be there for the ABC Quantum Mission.
Absolutely. Dr. Lamurthy, I think, it is, last time I had given you a very generous funding for your quantum mission, but I think in that, if you can kindly add, you tell how many fellowships, let's say 30 fellowships for PhD and postdoc fellows in the field of quantum science and quantum technologies that you can do. Yes, please work on attracting the most brilliant young minds in this field, and let's bring them to Amity across our campuses, across the world where we have. And my request to all the speakers who have come today, please help us in this mission. We have a lot to do.
Thank you, Chancellor, sir, for this very generous fellowship which you have announced, and also initial seed money of 20 crores for the quantum mission. We will implement with all these stakeholders who are sitting here on the dais, off the dais, as well as who is online. We will now make a strategic plan, come out with the milestones, definable quantitative milestones, what is to be achieved, responsibilities of the teams we will identify. So we will do next week and report back to you that how are we going to do this, and then you will have one strategic group meeting with all the important stakeholders, and then we will move ahead with this full vigor. And this fellowship which we have announced, we will make the framework. How do we identify, bring the best students, doctoral and postdoctoral fellowships? We will identify the best one, and we will also mentor them. They get mentored by these people as co-supervisors, and the part of the work can be done there as a part of the internship. They will move there. So thank you so much, and we would request you to launch the website. So Chancellor, sir, you can just type your keyboard.
Yes.
Let's clap for Chancellor launching the website of our quantum mission. In the home page, and this is available. I would request all of you to look into the website, which gives who are all the faculty, what is the profile, what they are doing. So every information, what is the infrastructure available, the MTech defense technology, what are capacity building programs which are now going to be launched and is being launched, and these are all available, including now the fellowship which has been announced. We will put them to doctoral, postdoctoral, news, activities of Amity Group, and the partnership with all of you. We will put them in the end. This event also will be there on the website. We'll keep on updating. This will be a dynamic website. very interactive website. So thank you so much, Chancellor, for launching this, and with your blessings and blessings of our Honorable Founder President, who has sent a message just now. He wanted, he's seen the program Founder President at Chauhan, and he wanted all the photographs of people present here, so that he would like to see it again and then see how you people can contribute to the quantum mission, which our Chancellor has just launched now. And thank you so much, Founder President. And we will ensure that your vision for our nation to make the country the knowledge superpower and the general superpower, we will contribute through this Amity quantum mission as well. Thank you so much, Founder President, as well, for your kind message of blessings to all of us. So with this, I once again thank Chancellor. Let's give a big clap to Chancellor and Founder President. And this will be a very impactful mission of Amity. I am very, very confident with all the support and assurance that's been given by our people stakeholders who have joined us from DRDO, CDAC, CDOT, and also the other industries and startups who are here. And we will really make a big, significant contribution from Amity to the national quantum mission. Thank you so much.
Thank you, sir, for sharing your visionary thoughts and inspiring us on the way ahead.
It is a privilege to have our founder sir's blessings with us always. Our founder president, Sir Dr. Ashok K. Chauhan, is an exemplary leader with multiple national and global campuses situated in major metropolitan areas in New York, Romania, London, China, South Africa, and beyond. Sir's visionary leadership has brought Amity University to the pinnacle of success. Under his unwavering guidance, today's youth are empowered to shape their own future. Driven by his dreams, he believes in striking a balance between vision and implementation, a philosophy that has revolutionized Amity into a world-class institution. We are deeply honored for his blessings, and we thank him for all his wisdom and expertise. May we have a huge round of applause. We now come to a moment of heartfelt gratitude. We are deeply honored to have our esteemed dignitaries with us today. Their presence, insights, and experiences have truly enriched this symposium and made it a platform of inspiration and knowledge. We sincerely thank them for their valuable time and present them with a token of appreciation. I request Dr. Selvamurthy sir to kindly step forward to felicitate our guests. Let's have a huge round of applause. May I request Dr. Pranendu Chaturvedi sir to kindly step forward to receive the felicitation.
Thank you for your valuable time and thoughtful insights.
Dr. L. Venkata Subramanian sir kindly step forward to receive the felicitation.
Thank you for contributing your time and expertise to build our community.
Let's have a huge round of applause for him. May I request Mr. Ajay Gupta sir to kindly step forward to receive the felicitation. We now have Mr. Atul Gupta sir receiving the felicitation.
grateful for your time, perspective, and continued support.
Let's have a huge round of applause. May I now request Dr. Abhishek Tiwari sir to kindly step forward to receive the felicitation.
Thank you for sharing your knowledge and inspiring us with your insights, sir. Let's give him a big round of applause.
Founder President has sent a message for all of you. Please announce at the convenient. Founder President has put the whole program on Amity YouTube channel. You know, the whole program online is available now on our YouTube channel. Everybody from India and abroad can access it all the time. So let's give a big clap to Founder President. So the whole program is being watched by the whole world. Thank you so much, Founder, for this message.
As this inspiring inaugural session draws to a close, we carry forward not just ideas but a shared vision of innovation and impact.
I want to thank Dr. Just Gopal Bhushan, can you, and also Natasha, and Sneha, Vaibhav, just Goodwill, Vaibhav, Anuranjana, Monica Kaushik, please come. Because I want to present these are the people who made this inaugural as well as the whole program. People, Wangbhai, please, Wangbhai. Amod from JCB, please come. Okay. Ashish Mani, where is he? Please come. So let's have a big photograph with him, with these stalwarts who will drive this as well. So I would request all the speakers to be with them.
Thank you all for your presence. Let us now move ahead with the same enthusiasm into the session that follows. Our next session starts at 12:15. We request everyone to reach by 12 p.m. positively and be ready for the engaging panel session. Be ready.
Honorable Chancellor, and very esteemed guests on the dais, and guests in the audience, and my colleagues and students. It's really a great day for Amity University. The one side, the commitment and announcement what our Honorable Chancellor made, that quantum mission last year, and we have completed the 1 year, and I'm sure during this symposium and what all the activities, achievement and focus area have been of the Amity University one side, but at the same time how the industry is moving with the quantum mission and what the quantum technology, quantum sciences are playing role. And I was at the symposium where Dr. Ramurthy ji has shared about the Amity University has been recognized for contribution in space science. And this was the mission of our Honorable Founder President when we were having the signal processing and integrated network conference, when the chairman of ISRO was the chief guest, and Honorable Founder President committed at that time that Amity University will be the largest private university contributor in the R&D in space science and technology. And I think our top leadership, whether Honorable Founder President or Honorable Chancellor, they have always focused what is important for the nation and how we focus in those disciplines, whether for the teaching learning programs, student development, or whether it's the research and innovation. And I think that vision has guided all of us in the Amity University group, Amity Universe, whether it's the schools or whether it's the universities, higher education institutions across the globe, that how do we focus in those areas. And Dr. Ramurthy, I'm sure he has already talked about what has been our R&D ecosystem, what achievement we have done in last year. Our Honorable Chancellor has committed that we will have the best of the infrastructure in the quantum technology and quantum science. We have already introduced one side the MTech quantum technologies, but also we are having the minors in the quantum science and quantum technology for the student, where we are giving the boundless choice to the student, that in case any student want to specialize, maybe learn and have the feel of what the quantum science or quantum technologies are there, so they can learn the few courses, and if they have the interest, so maybe the future they can pursue the interdisciplinary degree at the master's level, and maybe then pursue the research in interdisciplinary research, which is very important. It's not just the one discipline today matters, it is a multiple discipline to solve the societal or the industry problems. And as in the this space symposium was being talked about, whether it's the AI, whether it's a quantum, whether it's the other discipline, they all need to work together and to explore how the applications of these fields to find the solutions for future defense, capabilities of the university, because the future wars are not going to be the machines or something. I think that has to be linked to the space. And I think today is when we are having the completing the 1 year of our quantum missions commitment, the announcement by our Honorable Chancellor. And I think this is going to bring out a lot of new learnings for Amity universities, which will also forge the new partnership and collaboration. So the commitment of our chancellor, that how we contribute the highest in this area to contribute to the nation building and make India a Viksit Bharat. I'm extremely thankful to all the distinguished guests, whether it's Dr. Purnendu Chaturvedi ji, scientist ji, DRDO, or Dr. L. Venkata Subramaniam ji, CEO of Qubit Force, and the former IBM India Quantum Head, or Mr. Atul Kumar Gupta ji, a scientist ji and head COE, Quantum Technology, or Dr. Shantu Sardar, Director DYSLQT, DRDO, was present online, and Dr. Abhishek Tiwari ji, Associate Professor and Scientist F, and our Honorable Chancellor. And this whole the seminar symposium has been under the leadership of Dr. Silvamurthy ji for last many weeks. He and with the team from MIT has been working. So thank you so very much, and look forward to further deliberation. Thank you.
Thank you, madam, for this wonderful message, and your contribution so far has been fantastic in terms of academics, MTech, minor track, and also electives, domain electives, and also now the research and innovation. And she is controlling 40,000 students here. This campus alone, 40,000 students. And so thank you so much for your best wishes for the successful outcome of the program. Now, over to you.
We also express our heartfelt gratitude, ma'am, for sharing your profound insights and knowledge with us. We are truly grateful for your guidance on the way ahead.
We now move forward with the next segment of today's event, the panel discussion on Industry Academia Government Partnership for Leadership in Quantum Technologies. In a field as transformative as quantum technology, no single pillar can stand alone. It is the synergy between industry driving innovation, academia nurturing research, and government enabling policy and infrastructure that will define India's leadership in this domain.
To guide this thought-provoking conversation, we have with us Dr. V. Selvamurthy, President of ASTIF, whose vast experience and visionary leadership make him the perfect moderator for this session. Now, I would also like to take a moment to welcome our panelists for the day. Professor M.S. Prasad, Director AISST, please give him a huge round of applause. Dr. Anindita Banerjee, Senior Quantum Technologist, CDAC Pune, please put your hands together for her. Dr. Harish Sahu, Scientist F, SAG, DRDO. Dr. Abhijit Mitra, Associate Professor, IIIT Delhi. Please put a huge round of applause for him. Mr. Anurun Jain, Senior Principal Security Architect, NXP Semiconductors. Ms. Sudipta Paul Chaudhary, CMO, QNU Labs. And Mr. Animesh Aryan, CEO, Tagbit Labs. This discussion promises to bring together diverse perspectives, insightful experiences, and forward-looking ideas that will shape the quantum ecosystem of tomorrow. I now invite Dr. Selvamurthy, sir, to kindly take over the proceedings. Over to you, sir.
Thank you so much. What are your names? Just introduce yourself, both of you.
I am Srishti from BTech Computer Science and Business Systems.
I'm Sneha Rawat from BTech Information Technology.
Great, let's give a big clap to our young compatriots. You are doing a great job. Keeping blessings to you to do very well in your studies and make a mark on that. Good luck. Now I welcome you all for this very important panel discussion. The inaugural session has already set the tone, the keynote for the whole deliberations of the symposium. But this panel is going to look at the roadmap as well as some strategies, plans for the country, and how do we make India a leadership role in quantum science and technology. Because we have been publishing very well in terms of publication. We are third in the world. Filing patents, we are very good. We are ninth in patents. Now we are moving to 7. Even Global Innovation Index, we are low. From 81 to 38, we have jumped. That's not good enough. So that means we need more products. We need more technologies. We need more materials. So now it is the time for us to deliver product, technology, processes in quantum technology. So this panel is going to look at, I have academia, I have industry, I have government, CDAC, CDOT, and I have DRDO as well as MIT in this panel. And we have very distinguished panelists on the floor as well, not just only on the dais. So we are all going to sit together, even though we have lost some time. But let us spend an hour, open up our mind, heart, and soul to see this big mission of how do we make India the number one in the world. What should be our intellectual capital, what we have, and what infrastructure we need to build, industry, and what are the role of government to facilitate, catalyze, and provide the necessary resources, infrastructure, policies, and then ultimately the industry to develop the product, and the academia to seed futuristic technologies, because we have the young brains, intellectual brains here. They are creative, innovative, disruptive, and they think divergent, lateral. So how do we bring this pool available today, the talent pool available, and then come out with some good plans and strategies? So that is the purpose of this panel. I have very distinguished panel who has been introduced. So now I would reflect on what are the issues. Maybe I have also given some points for them to discuss and deliberate, but I would ask, because they already have received the points in which we want to discuss. So I would now request, I will start with Professor M.S. Prasad to give his thoughts. He was a DRDO in strategic program. M.S. Prasad is now the director of Amity Institute of Space Science and Technology. Amity Space Mission, he and Shivani Verma and their colleagues, along with other colleagues, they are driving this. And he has also given a blueprint for also the quantum technology MTech mission and minor track. So now, which has now gone through board of studies, and now J.K. Roy has taken over that with his input. So we are now, so he is in deep with this technology, and he's also looking at how do we use quantum technologies in space, the applications. He's looking at that also. So he's a great scientist. We adore him. We appreciate him quite a lot. So I would request you to reflect on those points. You can sit here and I would request all the people, because we are all very.
Thank you, sir. I would like to start
Just 5 minutes each, so that everybody is heard, and then we will start deliberating on those issues which I have circulated to you as well. Prasad, move it.
It's all right. I can hear.
No, I think sit down.
Okay. I can talk. I think it speaks. Good afternoon, everybody, and thank you very much, sir, for giving a time to open up the panel discussion. I'd like to start with a very famous line. I heard it twice. Richard Feynman said, "Nobody understands quantum mechanics." And one of my known professor of Yale University giving a talk at Texas A&M University around 40 years back said the same thing. Nobody knows what is quantum computing or mechanics, but I am adding so many people into the crowd of people who do not know quantum mechanics. I would like to say that please do not take the quantum computing or technology as a buzzword of the science. We in our country needs to work on this diligently. Do not get carried away by Chinese did this and so and this. We require the quantum sensor. You recently know that atomic clock failed and we had a problem in the satellite. And it is proven that quantum designed atomic clock will not fail for another 10 years, 20 years, 30 years till the time the quantum superposition or teleportation system is maintained. I would like all of us as an academia and the researcher to work on as a social impact quantum sensors. We require very precise sensors. I'm not talking about only because I work in a space domain where it is required too much. Some of us are working on designing quantum gyroscope and quantum sensors which will give me precision trajectory computation for Earth to Mars movement. I am requesting work on how can I optimize a system using quantum computation technique. Couple of my colleagues are working in this. That is the today's requirement. Drug discovery. We still work on drug discovery based on age-old data analysis technique. We calculate mean, average, or maybe second moment or third moment and say this drug is good. No. Use QBO, or I should not go into that detail. Use quantum optimization technique and you find it will give you an eye-opening result. That is what my request would be. Diagnostic. Our diagnostic system today is also based on a human being touching your pulse as well as having an X-ray and all sorts of images. One of our colleagues is working on astronaut health monitoring using quantum technology, and the results are phenomenal. My humble request would be please put an effort on this. Quantum material, graphene. Dr. Chaturvedi showed you a picture of graphene. Look at the mesh of the graphene. Can we think of putting the quantum dots and quantum material in that sense? I am not a material expert. Advantage, my satellite weight reduces. Lot many things can be done by the quantum materials which can be developed. My request would be that we should work into these particular directions. We miss the chance of developing an operating system. I'm sorry to put this word. None of us developed an operating system, and a young boy sitting somewhere in California Institute or somewhere, I forgot, he developed what is known as became the Linux and some operating system. We missed the bus and we became, something like repairing the computer or some writing some junk of the software. No. My request is please move up, and we have opportunity available to us. MIT has got the biggest quantum mission which is going on, supported not only by Honorable Chancellor Sir, even Founder Sir, as you heard, Dr. Sarvamurthy Sir. Under his guidance also a lot of research potential is existing. Any help required for developers or anybody who is working in the company and requires some study to be done, please approach us. We are always there to help. I think that is more than.
Prasad. Let's
Thank
give
you.
a big clap to Dr. M.S. Prasad. He has wonderfully brought out some of the opportunities available not only in space and other sectors where quantum technologies, particularly for navigation as well as communication, quantum communication in space. So thank you. Now I will move on to look at what are the emerging opportunities. So I would start with Dr. Anindita Banerjee, and she works with CDAC Pune, and I just had a brief interaction with her, and she has been part of Amity. Now she is in CDAC. She's a Kathak dancer as well, and she was in Amity International School for 1 year with our. So welcome, Anindita, and now she is in a very critical position there in the CDAC, and particularly to develop new technologies, which she will mention, and also capacity building. How do you promote academia to be a leader in academics, thereby churning out the future leaders in quantum science and technology? I would request Dr. Mrs. Banerjee to reflect on.
Thank you, sir. Since the beginning, it's an honor to share the panel with you. And my esteemed colleagues and, of course, many known faces are there. Hello to everyone. So I would start by saying, sir, I beg to differ, but I think we can say that we understand quantum mechanics, okay, because we are building products. We cannot start with something which we know nothing about, right? It was that time. And this sentence what I'm saying is from, I heard it about some 15, 16 years back when I was taking a school on quantum information from IMSC Chennai, right? And he was the first professor, and I felt like, yeah, interesting, So you will understand this technology better if you believe in it, and also the maths is going to tell you all about it. So if there is some concepts like superposition, entanglement, it's quite evident. You have to look into the maths, the matrices, and then appreciate the physics, and then build technology devices on top of it. Okay, so my journey started something about 18 years back. So we brought out the first quantum communication working prototype, QRNG, and they have been now deployed for R&D purposes with strategic agencies. Now I'm facing competition with my own products. Now I have moved from terrestrial QKD to aerial QKD, where we are mounting quantum entanglement on aerial quantum system, aerial devices like drones. And we have done a short video on mobile QKD, and now we'll be putting it, we are on the end stage of our project. We'll be putting it on the drone and we'll come out with some results. We have now recently, I have moved from quantum communication to making a working prototype of 5-qubit superconducting based quantum computer. What is interesting is how the first revolution, quantum physics, we are using lasers, we are using superconductivity. These are all results of first revolution of quantum, right? So we are using that to actually manipulate the qubit, the quantum entity, the electron, the photons. And that is how we are bringing products which is under the second quantum revolution. So, it's very interesting. The cryogenics is very interesting, and then it requires talent, it needs capacity building, and you have all disciplines coming into it. Quantum doesn't belong to one discipline, it belongs to all: mechanical, electrical, electronic, computer science, physics, mathematics. I do have, interns coming from MSc in physics, MSc in mathematics. So when, he was exploring, but when a student from maths background comes, and he actually learns superposition and entanglement from the matrices, and then he sees in lab that how we are manipulating the qubits, he can relate. And that gives a lot of confidence, and that also paves way for further development of technology. Now, coming from, so I cannot say government, because see, I actually am a technologist and I have worked with industry, academia, now government. But what I see is a lot of motivation, a lot of encouragement. So that there are a lot of good developments happening at CDOT, CDAC on quantum computing. You will see a lot of announcements. So what it means is, what you have to carry in mind is the government is encouraging. There's money they would want to come to put it on table, so that they want they want things on table. Prototype like TRL 5-4. Now, there are certain applications for which you do not need a hardware. For example, quantum computing algorithms. You just need your brain, you just need a workstation, right? So maybe you can start with that. You can play around with, implementing the Grovers, the Shores, the basic, so you start with David, what do you say? Query call complexity problem. That was the first quantum algorithm. Now, coming to that point, people often ask me that why an exascale comparison between a quantum computer and an exascale computing, because in CDAC we have exascale. So why do you want to jump to exascale, to quantum, invest money in that? Why not in exascale? So one sentence, see, exascale means 10 to the power 18 operations per second, right? If you're using a quantum computer or quantum states, you are able to manipulate different states at the same time, which means a 60-qubit quantum computer, you can actually process 10 to the power 18 states at the same time. So that is the scale you're talking about. And there are a lot of cryptographic algorithms which are based on computational security. Okay. Now, if you have a quantum computer coming in, those cryptographic algorithms can be broken in few seconds. And there are research papers on that. And that is what makes it very interesting. Because whenever the technology changes, it is actually cryptography which paves way for, same happened with, we started with Skytail, then you have superposition, transposition based algorithm, then you had Bomb and Enigma, right? Now we are going towards quantum computing, and the first attack is going to be on the cryptography. The entire thing stands on that. So that becomes very interesting. So, I'll be, sir, I do not know what more to say, but I'll be happy to answer questions. Yeah. So see, as sir said, I never had plans for this career. I became passionate, and what drove me was the happiness the knowledge gives you. And when you're able to study, you're able to experiment, observe that. So I wanted to bring that to the students. So we have designed two educational platforms. One is called CK Quantum and another is Quantum Entanglement Testbed, which is Quantum Pragyan. I am also working with AICTE on the minor technology course. So the CK Quantum platform, it helps you experience the quantum superposition, generation of photon states from spontaneous parametric down conversion, which is a nonlinear process, and that is how you generate photons. And then you operate on them. So it helps you characterize the qubits. It helps you do some applications on top of that. There are some good experiments because when I started learning quantum, I used to do these kind of experiments in Quantum Lab and SM Bose Institute. So that was the motivation and that was some background I had. What are the experiments we should be doing on table, right? So I'm trying to bring that to the academia. So these two are the educational platforms which I was talking about.
Thank you, Dr. Anindita. Let's give a big clap to Anindita for the wonderful job she's doing. We'll see that. And we like to look forward to explore the possibilities of working with you, and not only in the academics, but also in the research domain. And now I would move on to the next speaker, next panelist, Dr. Harish Sahu, who is one of my own former DRDO colleague from Scientific Analysis Group. And the SAG is a very sensitive lab for us. And so he hails from that. And he is already working in this domain of quantum technology. So how would you reflect on the security, how these quantum technologies can come into, whether it's quantum communication, key distribution, and how you feel as a DRDO scientist that what are all the opportunities available? Because I want my youngsters, the students as well, to understand, appreciate that this is the canvas of opportunities. Over to you.
Good afternoon, everyone. So from the morning, we are listening about this quantum technologies, and if you have heard, then it was told in the morning that Richard Feynman has given the idea to develop a quantum computer in 1982. So that time he has given the idea that we should have a quantum computer based on quantum phenomena like superposition and entanglement. Am I audible to everyone? Yeah. So the idea was given in 1982, but there was no quantum computing development from industry or government till 1994 when Peter Shor has given this breakthrough algorithm which can break various public key crypto systems which are being used. So after that, people like countries like US or big companies, they started to let's have a quantum computer and lead in this domain and break the code of adversary countries. So the basic idea was there that we should have a quantum computer to break the codes of adversary countries and have an advantage in that domain. So people started developing quantum computer. So 1996, this algorithm was given, and in 1998, a 2-qubit quantum computer was developed. And then the progress is happening. In India also, we are having a quantum computer. So the main application of the quantum computer is that we should be able to break the adversaries' encryption codes. So the primary applications from defense point of view, if you see, to have a advanced quantum computer with more logical qubits, can we break the codes of adversaries? And while at the same time, we should have efficient quantum codes like quantum key distribution or public key cryptography, so that our codes cannot be broken by adversary countries. So in that direction, many agencies are working. But in India also, we should have our own post-quantum cryptographic codes and QKD products. So in that directions, our industry is working very fine. And I am sure that we will be leader in this quantum computing and quantum communication in future. So now that we have this quantum computer for both the purpose, one purpose is that we should have it to break the codes of adversary countries. And at the same direction, we should have quantum key distribution and post-quantum cryptographic algorithms. So our codes are safe and that cannot be broken by quantum computer, latest quantum computer. So that thing is one application. But the second application, which Sir also mentioned, that we can have this quantum simulation that will make things faster. So see that if we drink this coffee, so this coffee's molecule effect on the brain, we cannot simulate efficiently or precisely using the best available supercomputer of today, which are based on classical computers. So that cannot be done precisely for a single coffee molecule, very simple molecule which have hundreds of atoms or particles, that we cannot simulate its effect on brain precisely. But if we have a quantum computer with hundred or thousands of logical qubits, then we can precisely simulate the effect. So that will enable us to do various kinds of simulation, like we can have efficient batteries, we can have efficient drug design or this vaccine designs. So that the precise simulation of those things can be done in a real time, maybe in some minutes or seconds with quantum computer. That will have wide applications on healthcare and other industries as well. And also in defense, we, as sir also mentioned, that we will be having this precise sensing devices which can detect submarines or their planes, quantum sensing radars we can have. So that will have wide applications in defense. And also civilian also will have effect, like we can solve this optimization problem which are everywhere. So the optimization problem which are hard for classical computers, that can be solved faster using quantum computer. So we can think of in that direction. And in the quantum domain, if you want to work, then you don't have to change your domain. Maybe you are from maths, or maybe you are from physics or computer or IT or electronics. There is a scope for everyone. But like suppose someone is from electronics, then they can do this devices thing. If somebody is from maths, then they can design algorithms or they can have this simulator kind of thing. If you are from computer, then you can do many things. So there is something for everyone in this quantum technologies. Just you need to plug in your domain into that quantum technology and application. So every student can pursue and think of what applications they have in this quantum technologies. And if they are interested in defense technologies applications, then DRDO is welcome and can give them projects or internship or whatever they want. In that, if they have something which promises defense applications, they can submit the proposal and DRDO gives grant and projects in that domain.
Thank you, Doctor. Sahu, let's give a big clap to Sahu. So he has also thrown up the opportunities available in national security, which the DRDO is developing technology. Because defense technologies, as we keep normally telling, it falls into 4 quadrants: sense, deny, reach, destroy. You name any defense technology, it's all. Sense, how do we use quantum sensing? Even sensing which you can't do by radars, which you can't do by other IR sensors or acoustic sensors, you can do it by quantum sensing. You can go much beyond the capability of sensing. Sensing enemy what he is doing, and also getting into that computer, breaking the code, getting into that quantum. Again, we can go to their computers and see the system. So like this, we have a lot of opportunities which he has spelled out. Now we move on to the next panelist, Dr. Abjit Mitra. He is assistant professor at IIIT. So I have a panelist from the academia, and Prasad from academia. Now Abjit, over to you.
Thank you so much, Dr. Selvam sir. First of all, I am very much inspired seeing your energy to conduct such a nice workshop and bringing everybody together under the common platform. So thank you very much for your kind invitation and giving me this opportunity. So from the academic perspective, firstly, I want to just mention or set up a goal, right? That we want to be a quantum nation, right? What does it requires to be a quantum nation? The master upon 3 verticals, the triad, right? That is quantum sensing, quantum communication, and also quantum computing, right? So now, presently, where are we right now? Okay, so for example, in terms of quantum computers, there are some startups where they have shown, okay, 50 qubit quantum computers are there, right? In terms of quantum communication, recently, I think QNU labs have recently shown a link about 1,000 kilometers, right? So these are first shot towards that goal, okay? But how far we have to go and what are the tools that we need to have, right? That is the main thing here, okay? So for example, right now, what has been demonstrated is that on QKD over fiber is based on trusted nodes, okay? That is, you need to have repeaters every 200 kilometers, for example, right? But then we would like to have this technology maybe across thousands of kilometers, or maybe as much as distance we can increase and reduce the number of trusted nodes. Okay, because just to tell you what trusted node is, trusted node is that, for example, the my bank account, okay, that password I share with say 10 people versus that password I share with 2 people. Okay, so which one is more secure? The password sharing with just 2 people, right? Because there are 2 points of attack on my bank account, right? So you need to then develop technologies around it, right? So now where does academia, industry, government come into the picture, right? So academia, each of these verticals have got their own, thinking cap, okay, and their constraints. Industry is driven by generating the revenue, okay, and providing support to its manpower or the human resource, okay, and to grow steadily because they are really number driven, all right. Academia is not exactly financially driven, okay, but it's more about generating new knowledge, right? So we need to find out wherever these two come together, okay. We need to find the synergy points, and there I feel that the academic professors, they need to interface with the industry, see where what their challenges are, so that we can develop the next short solution to increase their capability, right? That is from the research point of view. Then the other part is also regarding the human resource, right? How are you going to train the human resource so that you can provide enough manpower to the industry so that they can grow? Okay. For that, you need to have some very strong courses. And today, what I saw that Amity has launched all these programs. So it's really incredible to see that, because in Triple ITD also I've been teaching quantum communication course for last 2 to 3 years, and Shobit there sitting in the crowd, he has been our TA. He's now working in IBM, but he has been my teaching assistant as well in the course, right? So these are the state of the art courses you have to also develop in terms of curriculum, right? But in terms, if you want to quantify the numbers, okay, academia will play a role in technology readiness level from 0 to 3 or 4. Okay, maximum 0 to 3 or 4 means 0 means that an idea has come up, and proof of concept. Okay, that's where the academia will hover, right? But then it will be given to a lab. Okay, for example, CDAC, CDOT is there. We want to interface with them to further take the proof of concept to field trials. Okay, then when the field trial is done, and when we are around that board that okay, this technology is going to work on the field, then we can go towards patenting and standardization. I think one of the points which has been not yet discussed very importantly is that you need to standardize your technology. If you don't understand standardization, it is just like that. For example, there are plug points. Okay, each plug point has got 3 pins. One is earthing, one is positive, one is negative. But the diameters of those 3 pins are standardized so that the industry can make these equipments very quickly. So all these things are very much important, and where academia will again play a role while working with the R&D labs. And then the standards can be adopted by the industry, okay, and then taken forward for a wider market, right? So I think in my lab, what we are focusing on is that first of all, quantum has to be integrated with the classical infrastructure. It can, so typically, you have fibers, but you cannot have dedicated fibers for QTD all the time. So where you have to integrate the quantum technology with the optical fiber standards. For example, in the access network, we have passive optical networks. Okay. So on that standards, if you integrate quantum QKD, how will those standards get affected? Then you have data center networks. Okay. In data center network, how are you going to integrate QKD? Which QKD you want to integrate? There are so many QKD technologies, right? There's a DV QKD, there's CV QKD, there's twin field QKD, right? There's Eckert 91. Okay, which technology where you have to deploy, and the main holy grail at the end of the day is to move towards quantum internet. Okay, that is not everywhere you can deploy a 100-qubit quantum computer. Let's be real about it. Okay, because why? The cryogenics are very demanding. Okay, so on field you'll have a 50-qubit maximum quantum computers, and they need to be integrated over an optical fiber infrastructure to have a coordinated distributed computing capability. And that's what a quantum internet will facilitate at the end of the day. That's the holy grail. Where we are developing different quantum technologies, we have to come together and make that entire quantum network come into the picture that can support distributed quantum computing. So that's the main requirement, and why we should now start doing it. Okay, we have to learn from history. Okay, internet came out of DARPA. Okay, internet came out from DARPA. It was a defense project. Okay, DARPA is a US based defense agency, right? Now see, we are using internet all over the world. Similarly, we are at the very much starting or the inception point of the quantum network. Okay, but we should start doing these things. Without doing these things, we will not go on to the learning curve, and we will not be able to move ahead. So I feel that National Quantum Mission has taken the very important step to bring all these verticals together, but we have to keep on interfacing, keep on talking with each other. Okay, improve our courses for the manpower, engage in a meaningful research where the outcome is a proof of concept, right? And then we can keep on going out to the standardization vertical and have a full-fledged quantum industry and quantum nation. So that's my vision.
Thank you, Dr.
Thank you.
That's a great vision for the academics, what we can do in both in capacity building as well as taking the ideas, how do you translate them up to a TRL level 2, 3, 4 maximum, and then how do we transfer it to a national lab or to an industry to handhold to further translate them into a deliverable. It's fantastic, and I congratulate all the work that you are doing. Now we move on to the next panelist, Arun Jain. He is Senior Principal Security Architect from NXP Semiconductors. And this is a very important area where he is working on automobiles. How do we integrate with the existing systems? So over to you. Can you share with us how do we integrate the industries, academia, and all stakeholders together, government, and then bring new fast development and technologies? Over to you.
First of all, thank you, Dr. Mukherjee, for having me part of this esteemed panel. And thank you for inviting me for this symposium. I was delighted to see that, so far, of course, I knew that NQM is there, but now today I know that AQM is also there. And it is also great to see that you mentioned that the MIT is planning to start the semiconductor mission, because I come from the semiconductor industry, and India is a lot to do in this space. So thank you very much for your thought leadership in these two deep tech space. So I'll give some glimpse of what do we do in the quantum space from the lens of the semiconductor industry and why we are doing it, and then I'll talk about the collaboration aspect. So as I come from a semiconductor industry, when we build chips, we are building chips not for today, but even the chips which are going to be used in 2 decades from now, because we take about roughly 1-2 years to build the chips. Then the OEM will take another 2-3 years to build the complete system. Let's say I'm building a chip for automotive application, then the car makers will take 2-3 years to build a car, and then the car will be sold in the market for next 5 to 7 years, and thereafter the car will be used by the end consumer for next 10 years. That means what we are building now is gonna stay with the end consumer for next 2 decades or more. And that is why it is extremely important for the player like us to integrate the post-quantum cryptography, the security technologies that are needed for preventing the quantum threats. So we have been working in this area for last a decade or so. As we all know that NIST has published the algorithm FIPS 203, 204, 205, 2024. So, and we are one of the authors of those algorithms as well. So we have been, so all the products that we are building now, they are already quantum threat resistant, and our products go in variety of applications: automotive, smart home, smart factories, the transport system, government ID cards, Aadhaar systems, e-passports, and all those things which require the higher level of security. And that is why we have been integrating this quantum technology in the domain of the VLSI. Now, this also gives a lot of opportunities for the youngsters to play in, because as of now,
this majorly the PQC area is the theory part is more majorly being taken care by the NIST, but lot of deployment needs to happen at the product level, at the system level, and this deployment is going to be a very long journey and a very complex journey. And whatever the implementation of that algorithm that is going to happen for, let's say, for the server market, that's not going to fit into the tiny IoT products. And that is why there's a lot of innovation opportunities for academia, for research labs to come up with an implementation which are suitable for the use case. As an example, let's say if the bank is servicing 1 lakh transactions per minute so far, now it needs to migrate to the post-quantum world. It integrates the PQC. Roughly the throughput of that PQC and implementation is half of what the classic crypto gives. So now suddenly with that update, they're able to serve only 50% of the transactions. And now they have to procure the hell lot of the hardware to restore their previous capacity. So there's a lot of innovation needed in this area. Of course, the people like us in the semiconductor world have been working on this topic, but unlike the semiconductor space, where India is almost playing a catch-up role, quantum space, the plane is, everybody is almost at the nascent stage. So we have a very good opportunity to be a leader in this space, pick up these topics, do a lot of innovation, and innovation happens in our university where the people of 15 to 18 to 30 years of age are there, and this is the population that reside in India, and that is why we need to channelize that the energy to the right direction. And I think this symposium is perfect example of doing such thing. I think from the collaboration perspective, I think from a government, we have already seen the NQM and the NSM, National Semiconductor Mission, putting a lot of emphasis on these topics. As a next level, I think we also need to do a bit more in terms of the mandating the requirement of these PQC in the systems. We already see government across the globe, be it US, China, Korea, Australia, which are migrating to the PQC world. India, there have been few task force who have submitted some reports, where they are given some guidance, but still there is a lack of the mandate, maybe a law enactment of law, or maybe some official orders to move the critical infrastructure, be it defense, not just defense, the telecom, the transport, the power, the water system, move this to the PQC world. So I think that is one of the government aspect that is lacking. And again, US is leading in this aspect. We see presidential orders in this area in US, and Europe also is playing a big role in this. From academic perspective, I think there's a lot of opportunities for research in this area. We have seen the algorithms came out, but the process of algorithm, if I can just quickly summarize, NIST has been doing this competition where they invite the researchers to submit the proposal of the complex math problems that can become the basis of the standards for the crypto algorithms. This was done for AES 25 years back. Now this was done for 26 by NIST in 2016. When they started this competition, they thought they will be able to complete in 4 years. They could not do it. They could not converge it by 2020. They took it to the 2024, and that too 130. When the 132 submission came from the different research groups across the globe, they used to do the screening and then publish it for rest of the researchers to do the crypto analysis and break it. And even till last moments of that standardization phase, the crypto algorithm which was submitted, kept on getting eliminated because somebody or other was able to break it. So these algorithms have come in, but they are yet to be time tested. We have gained confidence in classic crypto algorithms in last 20 years of research with the research work. That time testing is yet to happen with the new algorithm. So I think academia, mathematicians, cryptographers have a lot they can do they can do a lot of work in this area. Then from a startup perspective as well, we can, have lot of strategies and, work in the implementation phase, because lot of implementation is going to happen for the industry, and industry is yet to, on a larger scale, yet to wake up to, adapt to this space. So I think we need a lot of manpower which can come from the university, but also deployment will be done by the, expert in this domain. So I think a lot of space for startups to play. And industry wise, I think we have seen a lot of industries to start waking up, moving to the PQC, but there's still a lot to be done. We have seen in India, at least, it's a very, thin presence as of
Thank
now.
you, Dr. Arun. I'll come back to you on this. So see, students, so many opportunities available. Industry is waiting, whether it's transportation sector, communication, telecommunication sector, or it is defense. Everywhere you need quantum to enrich, speed up your actions. So quantum is almost all pervasive. So please cheer up, prepare yourself. Startup, is mentioned, startup opportunity. Now we move on to, thank you Arun for bringing this very beautifully. We move on to Ms. Sudipta, and she is working on quantum key distribution as well as in the quantum random number generation, which are necessary for generating the keys. And over to you, share your thoughts. That how do you feel all integration is the need of the hour, which Arun also brought out. That we have to work together. Academia is working separately, industry. How do we bring a forum or a mechanism? Can Amity play a role, because we work with industry, we work with academia, and we work with various DRDO labs, space lab, atomic energy. We have formal MOUs with them. So how do you think, Sudipta, that we can do this integration part?
Thank you so much, Dr. Selvamurthy, and my fellow speakers. And I think you have been patiently listening. It's not an easy job from the morning to listen and of course gathering your key takeaways out of it. So before I get into the questions, sir, I just would like to educate that there is still a myth. People still don't know what is the difference between quantum computing and quantum communication, or quantum communication or quantum sensing, or quantum sensing or quantum material. We have definitely improved from last year, because when we started our journey in 2016, people didn't think that quantum someone will work on quantum. People actually took the SAS wave, people took the AI wave, people took the internet wave. But look, we did not really invent internet, but we became the IT services, the leader, if you see, right? We also did not really work on the SAS but today we have so many unicorns in SAS. So India has a very, very rich potential. India has the brilliance. India has also the ability. But the problem that we are all having is we are working in silos. I would definitely like to give a point and of course a credit to government and National Quantum Mission, because it's a technical orchestrator and it is also the technical architecture where it is providing the industry, academia, all the researchers, the scientists, and also at the same time the startups to come along and work together. Now, when it comes to QNO Labs is not just working on QKD, which is powered by quantum physics, also the QRND, the random number generation, which you can come to our lab, and every week we have 2 or 3 industry visits coming from various universities, whether they are from BE, they are from PG, they are from army colleges. They come, they see the lab, they see the true random number generation, they truly see how QKD works, they see how the free space QKD works, right? If you have to really work on the satellite security, how do you really do it? You see it, experience it in our lab. So that's a tremendous way. Like when I was in Ericsson, we had a particular day called bringing the future of leaders. So we used to call all the students from 7, 10, 12, because that's a very, nimble age, and they are also shaping up their mindset. They are taking the right decision with help of their friends, mostly with their friends, not with their parents, because they are also moving to the team. So if we are not really helping them to take the right decision, being in the right field, being the tomorrow's leaders, we are failing. Right, and this is where I really like to give credit to Amity, the way you are bringing everyone. And I actually interacted with few of the school students. They are in 10 and 12. That's a tremendous and a very thought-provoking, forward-thinking vision that you have. And I think this is where we collide, we overlap with Unilab vision also, right? We stand tall. We didn't go with the consensus. We went with the conviction. So we work with quantum physics. We also work with advanced mathematics. Now, I would like to defer what Mr. Arun Jain had said. India is already a leader when it comes to world-class quantum communication. We are coming under top 3 countries. And this is something to be, proud moment. Each Indian should feel proud. The second thing is we have hardly invested 6% of what US has invested. But we have made technology scalable, affordable, and we are not here to generate revenue. Of course, the business has to generate revenue, but here we are standing for the good of the people. That's the mission. That's the ethos that Unilabs has, right? Because we really want to make sure that we don't want to depend on a foreign technology. We want to build something sovereign and indigenous so that our data stays here. Because today, all those countries, US, UK, China, they are actually trying to break the data, break the communication that India has. You have seen there are so many examples. Mythos AI, you know that, right? So what we are actually doing is cybersecurity. If you all know what is the true meaning of cybersecurity, true meaning of cybersecurity is that you should protect from the attack. But here what is happening is there is a cloud level attack, there is a ransomware attack, there is a phishing, there is a spoofing. You just only buy that point-based solution and you stay quiet. But you don't know what is happening. Your data is getting secretly stored right now. There are instances 2024 when 4 banks in US where the adversaries attacked. They stayed with they're still there, they're still found. But it took 267 days for the banks to identify there is an interception that has happened. If you really need to understand that their interception has to be alerted, that is where quantum physics works, because it's a very much in the phenomenon of the light theory or the photon theory, the quantum physics or the from which we actually do the quantum key. So if India has to be the leader and sustain this leadership, India has to build their hardware, which is based on quantum physics, post-quantum cryptography, which is based on advanced mathematics. But because this is post-quantum cryptography, is also based on advanced physics, advanced mathematics, quantum computer can break it. You just have a window of 4 to 6 years maximum. Now, whether we should wait and watch, that is not a good strategy. If a leader has to win, the leader has to start now, right? So India has already started National Quantum Mission Task Force. We are part of the task force. We have created this 120-page document last month, and we have made a forensic comparison of the same report, 10-page, and you can go to QMU Labs, come to our white papers and read about it. 2028, that has been mandated that we must be getting compliant, and the cryptographic discovery has to start now. Which are the critical sector? BFSI, for example, healthcare. Your data coming from the government, because that's the national security. Government is the biggest consumer of this technology to secure the digital infrastructure, and that is what QNU's method, QNU's ethos. Now, collaboration part, we provide QNU Academy, where we are already we have tied up with SRM. Different, the branch of SRM universities, VTU, under which we have 200 universities, Visheshwaraya Technological University under Karnataka. And we are already developing faculty development program in quantum technology, both physics and also the advanced mathematics. It's a 40 hours faculty development program. We also give the same program to the students, right? And we are also working with setting up their quantum research lab. And I'm very, eager to talk when Amity said that they are creating a quantum lab. Why not we can collaborate? And then there is a second way where you can showcase your dedication and inspiration. That's Spark Summer Internship that we do every summer. We just completed. It's a 3 to 6 months internship that we give it to the students. It's not just for students, it's for the scientists, it's for the global remote way you can work. You can have PG, you can have UG. You just need to ensure that you have some specific skill set and we got more than 2,000 application across Germany, Austria, India, and all the IITs and IIMs. They want to work with us. So it's a tremendous opportunity that we really believe that if we are not democratizing the technology and nurturing the talent, 91,000 quantum engineers we have per year who are coming out. But there is a brain drain. They are going to either Europe or going to US because of better grant opportunity. Of course, US things have scenario has changed. Let's talk about some other countries where we can find better opportunities. But why not India? India does have those grants, does have those internship opportunities. Yes.
You are asking a $1 billion question.
Yes, yes.
Not related to what you are saying.
No, so we have to think, sir. We have to think. People think when it comes to any innovation, they think it is a Western country always. But why not India? The things have changed. I think that the mindset has changed, and the Pune Lab itself is an example. So this is where I want to end, sir.
Thank you, Sudipta. Let's give a big clap to Sudipta. She spoke from her heart, not just only from the brain. So she wants to see India growing and becoming number one. She's not satisfied with number 3 position. So how do we make it happen? That is where there's a great opportunity available, Sudipta. Now I move on to another industrial person, very, very important person who we are already interacting, dialoguing with, Mr. Animesh Aryan. He is the CEO of the QQ Bit Labs. And he has already established some facilities in solid state physics laboratory for the quantum communication, working with the DRDO. And his lab, we are looking at how do we create some facility here for quantum communication, both research lab, practical lab. Over to you, Animesh. How we can, industry can work with academia, that you focus on that, and then how would we amplify the output of industry through this partnership?
So, good afternoon, everyone. I think this we're just before the lunch, and usually I end up having something before the lunch. It's hard, but thank you so much, Dr. Murthy and Dr. Gopal. As a company, right, we started way back in 2018 when quantum was just something in the labs, in the research labs mostly, right? And our journey started with DRDO, and we grew along with DRDO, right? So as we speak, we have commercially deployable systems to any distance, whether you make it 1,000, 2,000, 3,000. It's just a matter of numbers with the current architecture. It's all about ensuring that that we have the best quantum safe infra in place, right? Now we have so many young people. I want to make very clear, what do you say, conclusions here and points. Because when we talk about academy, there are two broad streams that we must work. One part is that the science part, which is the research, right, where academia can be involved in doing some joint projects and making early funds, because the risks are very high, and often the government wants an academic partnership in place, right? So that that early developments from proof of idea level to a proof of concept level can be done. That is one set of arrangement. Right? We can have problem statements because we do a lot of things which require a lot of activities, and we go back to the drawing board and we say, okay, this doesn't work, right? So there are a lot of iterations of research required, right? And as a company, we have a very clear mandate that we want to work in the applied research, right? We're not into the fundamental research, so we want to use something and be able to build it. Now, as far as the quantum tech is concerned, it's an engineering challenge, right? How better you can do the engineering, right? And as we see so many people here, the second vertical, which is very relevant, is actually be able to create the workforce which is going to do that job for you, right? And that will not happen only with physicists, because getting physicists to work together is also very hard. So you can have a very a complex system, but when you want to make a product, it is the engineers who make things work, and the engineers are going to actually and because quantum is very, very interdisciplinary, you need people from electronics, you need people from software, cryptography, maths, of course, quantum is the bedrock. But to be able to build something itself is a very, very huge challenge. So when we started out way back in 2020, we were doing early prototypes to be now, Dr. Sandhu has already displayed the products, that these are very compact systems, not can be used for scaling the solutions. So academic partnership is of two broad categories that we see that is required. One is to be able to create the talent, which requires obviously a lot of hardware, infra in place, right? I'm very glad to see that MIT has started with an idea that yes, we can go this way. And if you look at the mandate for ANRF, the Anusandhan National Research Foundation, it's all about being able to where private universities are also now going to work and do the early research part, right? With the skill development, obviously AICT has launched along with INCU in place that what is the kind of electives can be offered at the undergrad level, and then what can be also done. Let's say you want to have full quantum course. So I believe that MIT must have like a MTech program which actually gives something on the quantum technology, which can be catered into, let's say, quantum communication, quantum sensing, quantum communication. But I would agree with Mr. one thing, that as a country we have come a long way. Of course, when we go to his question, that lot of semiconductors, right, are actually we do not have the local footprint, right, and this is a more of a marathon because all of this, you cannot start at T0 and be looking at indigenous components, which is like 100%. That is not possible. If the math doesn't work. But as far as our work is concerned with respect to quantum communication, we have been able to develop a lot of things until we have C-dot here, and and I think that there were three people when we started out the quantum communication journey. Right? That is how there was we started the QNU and then C-dot. But now I think this is going to be extremely critical because you have to ask the question: are we as a country digitally sovereign? And when we actually look at what exactly we do, is that we have no technology in the last 30-40 years which is inherent to India, which means that somebody actually has got a plug and will pull it out, and we are sitting ducks. If you look at the recent episode of Naira, I think it is the petrol pump, the petrol company, and Microsoft denied access to their email accounts of nowhere. And now you have one of the best example I see, and I actually draw inspiration from is Zoho. Right? Today we have switched all the government back, email accounts have switched to, Zoho. So I believe that as a country, we actually progress better when something is denied. Look at ISRO, because people denied giving the space technology to us, and then we have these space programs. And I think that look at how many private companies are now working on the space programs. And as a company, we are now also, we have a space program of launching our quantum payloads because currently there is no quantum, kind of payload certification or compliance for the quantum source. So we are working with a private satellite company, and therefore I would be very interested to see that how we can actually have a joint partnership because space is very complex. Right from the engineering challenge, it's a multitude of problem, right? So I believe that there are multiple things which can be done with academia, where there are some mandates which are independent of us, right? There are things you can do R&D which does not require industry per se, but there are overlaps which is basically on applied research which can be taken. As a country, we have been producing a lot of papers, right? Not products. So from papers, we have to now switch to products, and that is going to be the what you call it, the foundation of making India a product nation. Whether it is quantum or space, it doesn't matter. But this is the blueprint which is required, that we focus on products, at least 30% of what we focus on papers, right? So that is how we can evolve. And then of course with the partnership with respect to the talent creation, right? And because there's a lot of opportunities, we have quantum mission where skill development is required, and there are so many startups coming up. There is a good market for every one of you. When you're able to prove your, metal, we're able to prove your, effectiveness in developing something. And that I think is required where you can create a center of excellence, which could be a 5-year plan, but we have to start it somewhere.
Thank you, Animesh. Let's give a big clap to Animesh. An industrialist with whom we are working, and his vision, how we can bring in academia industry partnership so that industry flourishes ultimately to bring products, technology, and processes. Prasad, you wanted to say a short intervention?
Yeah. We are there working in a space domain, and we got couple of problems from European Space Agency as well as JPL. And with my colleague, one of the colleagues is sitting here, one is little busy. We have developed couple of algorithms for doing, as I said, interplanetary travel, trajectory optimization. Also, a space situation aware. It's a very big problem when you look into the space debris and the satellite going on how many conjunctions we get a large number. That algorithm we have already proven. Most of my algorithms are written in Q sharp. I tell you the reason, because I can do it on my desktop. But I would request Madam Anindita and Suyukta Madam and gentlemen from NXP. You see, one of the practical things you have to make is please try and increase the coherence time. And a spooky action of Einstein needs to be for a longer period. I have designed a satellite constellation quantum network, but it is not having time. The 1 millisecond, 5 millisecond of a spooky, the entanglement is not going to solve the problem. Quantum encryption we can do later. Sir knows one of the encryption I developed about 30 years back, and I think Pentagon is still trying to break it. So we have to work on quantum encryption, not mapping of classical encryption of quantum domain.
Thank you, Prasad. And we will work it.
One second. Hardware. Madam, try and make it in QNU lab and other works on a normal temperature. Put it on a chiplet form. Use radioisotope characteristics to design a desktop, quantum computer. Let it be 2 qubits. Doesn't matter. My student can use it. It will not cost a fortune. My humble request is that one small problem I request all of you to help us. My colleague has got from government, large number of satellites. I can't tell the organization where I am supposed to find out the disaster done by somebody else. Mark the disaster and what type of disaster. I have trying to put the image 8 by 8 into quantum domain mapping. I am finding difficulty using NILQ and other algorithms. Try and come up with that. That's a very big problem.
Yes, sir. No, sir. I think you have raised a very valid point. And thank you for being so straightforward.
I'm going to talk to you who have not you.
Yeah. So coming to one of the case studies, when it comes to the satellite communication, securing satellite communication. Last year, I cannot take the name for NDA reasons, of course, but we worked with one of the global full stack satellite company. They were sending 2 international payload from SpaceX. So we secured the satellite communication last year, precisely sometime in August. So all our products are already in deployment. So you take drone security, you take satellite security. We have created a quantum security dome, which we say in Hindi quantum suraksha kavach, right? But for the international world, it's like Israel had made their dome, Iron Dome. We made our quantum security dome. It has 4 layers. It has the terrestrial QKD and also your cloud-based, security, quantum say VPN. Then we have for the, the drone security, drone to communicate with the ground station, all and so that no jamming happens. All the commands go properly. Then we have the next layer, that is satellite. And then all of these have been put together in a product called Q Shield, Quantum Shield. But sir, on the hardware side, I am making a note. I am not that technical person, but I will definitely take it back to my innovation and engineering team, and I will see that. Yeah.
Now, I will
connect
you. Thank you, Sunita. Our Madam Vice Chancellor wants to say, then I'll ask Preeti from SSPL, because we need to discuss another 5-6 minutes from panel itself. may I request to start the discussion from the floor?
Yeah, I have since morning I have been attending only the symposium and the first symposium, which were the space and defense technologies. The point where we say that, okay, we, see that so many satellites to be launched, but we look at the components from where those components are coming, maybe from the neighboring country. So when we look at because for the quantum technology, quantum materials, quantum communication, when we talk about, it's very important. It was said that if we have the product based startups, which should be funded, but I think we are not having that many the product based innovations happening, or the product development are happening. So this symposium, I would suggest, maybe as a Amity University will take further lead. Our Honorable Chancellor just now during the inaugural session have announced the 30 fellowships also for the research and the master's program. Can the industry help us work with Amity University that we identify the problems where the product is needed? Through the research and innovation, the products are developed, and where the industry be the partner. So, Dr. Silva Murthy ji, one thing I would like to suggest, we have the strong industry research advisory board for Amity universities for our quantum technology, quantum materials, quantum science cluster, and we work only on those problems where the master students, the bachelor students, the PhD students, plus our researchers and scientists work in that space, so that what Honorable Founder President says, the outcome based. So in the research also the outcome is very important. Industry is looking for. So let's have the outcome based, the collaborations, and therefore the advisory board becomes a very important. So I invite all of you to be the partner with Amity University.
I would request Animation Sudipta to reflect from industry side. So how do we build this advisory group so that this is one way to integrate industry with academia and government? So Animation.
Yeah. Thank you, ma'am. I think that, that's a good suggestion that you've given with respect to creating. I think that more than that, I think the mindset has to change, which is basically that, are you ready to fail? Especially when you start with some idea, right? One of the most common things which is going to happen is that may not work out. And then obviously it requires money to do and start all over again, right? I believe that what should be a step is that we have certain open problems where we need academia to be stepping in, right? And so that, when we work together, the collaborative risk is a little lower. It helps you, it helps us, right? That is where we can start with. And let's say, especially on the early design part, because when we start rapid prototyping, or let's say we start towards the product development, that's a different course. But as far as it is concerned with respect to the designing part, because systems engineering is something which is very essential for every product development, right? Whether we talk about terrestrial network, software, or even space, this is where we need a lot of designs also in place, right? These are the things where, we can start. And obviously you also need a lot of resources to do that, right? So the moment we are able to kind of chip in that, okay, these are the things which we can work, then definitely, and then dedicate people to work on that part.
Yes.
Right? That is where I believe that some program like this can definitely, start, and then having the skilled, manpower, which I told at the MTech programs, because when people spend more than a year, is the time when they start actually giving, output. Right? Before that, it is too premature to do any, kind of very small internship.
Internships are very good for the students' learning.
Yeah.
But if you want to have sustainable work in particular area, you need to have continuity of that problem solving.
Yes.
And that has to be worked out where the team, under the guidance of the faculty, maybe the student team will keep on changing. Okay, that's the floating population, they completed their program, they've left. So maybe some student will get the interest to start their own venture.
Right.
But I think we need to identify the problem and make a milestone for 3 years, 4 years or something, so that we review the progress, how we are progressing. Maybe the student teams are changing, but the faculty team is not changing. That is the very important, and industry team is not changing. So we need to work on the team-based, the problem-based, collaborative work.
Yeah. Well, second thing, I think this is just a suggestion. You take it or leave it, but I believe that you can't be doing both, which means that if people are also teaching extensively, they will not be able to focus just on the research part. So that is something a trade-off. You have to figure out, okay, when there is a dedicated group which you want to create, they have to be working on problem statements defined and not into just teaching part, because that actually dilutes the effort, the effort which goes into building something like this. Because we everywhere, anybody will look at NIST or any other places, they are good researchers, they may not be good, lecturers.
Thank you, Animesh. We will discuss this. Now, I would request Preeti from SSPL, from the floor, to also reflect, because they are working. There's a big lab, quantum lab they have developed. And over to you, your reflections of whatever you heard. What is the strategy by which India can assume leadership role in quantum science and technology?
Yeah, thank you very much, sir, and a very nice panel discussion it was. So, first of all, the most important thing, what I have understood, because I am working in the quantum sciences area and working on a particular project wherein I am developing indigenous technology that is the heart of quantum sensors. We call them microfabric, they are the atomic sources, and we call them microfabricated alkali vapor cells. So these are the technologies. Whenever this quantum sensors work has been taken up, be in USA or in Europe projects, they first develop this main component for that. That particular component is not available globally. Only their ultimate end products, be its chip scale clock or be its chip scale magnetometer, they are available. So from there, one thing is clear that along with the major system that we are planning, that we are designing for the defense systems, for the defense labs, or for the space applications, the most important part are the components that are also their design, their fabrication must be indigenized, so that the ultimate goal of making that quantum ecosystem in India, the landscape of quantum, that can only be fulfilled. If still we are dependent on the components on outside countries and seeing the today's scenario, then even if the complete system design we have, we are not ITAR free. And if we are not ITAR free, that means that indigenization is not there. So I am very proudly say that being a SSPL person, we work on the complete system also, as well as the indigenized components that are required to develop that system, we are working on it. And if any of you will be there during the valedictory function, I would like to show one or two slides also over which SSPL is working in this area. Thank you very much.
Thank you, Preeti. We should now conclude because we have a lot of news. We will discuss over lunch. And I must thank all the panelists, very distinguished panelists, for wonderful exposition. And they have given new thought for us to ruminate and also look at new trajectories in which how do we integrate together. And there are useful suggestions came that how do we create an advisory group where government like CDAC, CDOT, and also we bring in academia, industries, and create a group, and which I'm sure Amity we will take that initiative, so that this becomes a model for to be replicated elsewhere as well. So I thank all the panelists. I wish they have more time to discuss. I thought we could have more discussion from floor, but then we will have it in the afternoon afterline session as well. Now I would like to thank all the participants from the floor who asked, gave some good suggestions. We will continue the dialogue during the lunchtime as well. So let's give a big clap to our panelists once again. Those who ask questions and suggestions from there. So we are now looking at how do we create the human resource, how do we create innovative, disruptive technologies, and also how do we integrate them, ultimately focusing on the products, systems of systems, when you talk about DRDO and other deliverables. So we will work together and let us make India the number one in the world in quantum technology, not number 3 or number 2, we are number 1. Thank you so much. Now I hand it over to them to give the word of thanks.
Thank you, sir, for taking us through this session. We extend our sincere gratitude to our respected moderator for guiding the session with such insight and grace, and to all the esteemed panelists for their valuable inputs. Your perspectives have truly enriched this session and set a meaningful tone for the discussions ahead. We now come to a moment of heartfelt gratitude. We are deeply honored to have our esteemed dignitaries with us today. Their presence, insights, and experiences have truly enriched this discussion and made it a platform of inspiration and knowledge. We sincerely thank them for their valuable time and present them with a token of appreciation. May I request the dignitaries to kindly join us for the felicitation ceremony, and I request Dr. Selgamurthy sir to please felicitate the panelists.
Would request the Honorable Vice Chancellor to come to we'll come to the floor.
Mr. Animesh Arya.
May we please request you, sir, to kindly step forward to receive the felicitation?
So please stand.
Mr. Animesh Aryan.
Founder President has said yet another message. So he has been listening to our conversation in the panel as well. Yes, wish good luck to every one of us to move forward, and his blessing, support is there for the whole program. Thank you, Founder President.
We thank you, sir, for your presence and wisdom that you've shared with us today.
Professor M.S. Prasad, sir. Dr. Anindita Banerjee, ma'am.
We thank you, ma'am, for your valuable time and thoughtful insights. Let's have a huge round of applause for her.
Dr. Harish Sahu, sir.
It has been an honor to have you with us, sir. Thank you for your valuable contribution. Let's have a huge round of applause for him.
Dr. Abhijit Mitra.
We truly appreciate your time and the impact of your words on this gathering. Let's have a huge round of applause for sir.
Mr. Arun Jain.
Thank you for your valuable time and thoughtful insights. It has truly enriched today's session. Let's have a huge round of applause for sir.
Ms. Sudipta Paul Chaudhary.
Thank you for sharing your knowledge and inspiring us with your insights, ma'am. Let's have a huge round of applause for her. I invite all the panelists for a group photograph. I request all the panelists to please join us for the group photograph. Um, Thank you for our esteemed panelists for joining us for this panel session.
We look forward to welcoming you again at F3 MDP Hall for exquisite demonstration session.
Join back here at 3 p.m. positively. Thank you.
Join us for Cascade demonstration session at F3 MDP at 3 p.m. please.
currently a Qiskit developer at IBM India Research Labs. He brings strong expertise in computer science and applied mathematics with hands-on experience in quantum cryptanalysis and graph-based machine learning. Having worked closely with leading researchers and contributed to quantum-focused projects, he represents the new wave of innovators shaping the quantum ecosystem. May I now invite Sir to kindly come forward and take us through the Qiskit demonstration drive. Over to you, sir.
Yeah, hi guys. So I'm Shobit and I recently joined IBM and yeah, so I'll be talking without the mic. So first of all, how many of you have experience with how many of you have experience with Python and quantum computing? And you're all first years? Is that correct? Okay, cool. So basic Python you're all aware of. And basic DSA as well, hopefully. Okay, no, that's fine. So how many of you know what an open source ecosystem is, open source development is? Okay, so what we'll do today is we'll look at IBM's open source Qiskit or open source software stack called Qiskit. It's essentially an hardware agnostic software stack used for the compilation of quantum programs. Now, what does that mean? That's a lot of jargon. If you were a quantum developer, if you were an algorithms engineer, right, you have some quantum algorithm. You can develop an algorithm in theory, but how do you actually run it on a system? So the running an algorithm part, right? In traditional computer science, what happens is you write some code in C++ or Python, you give it to a compiler, it compiles it and runs it on your computer. In a similar fashion, we have Qiskit, which is a compiler font for quantum programs. So every quantum computer is going to have a set of gates or a set of operations that's native to it. In your traditional computer science, you have gates like NOT gates, AND gates, OR gates, right? So every high level program you write gets compiled into those before actually being run. In a similar fashion, you have specialized gates for quantum computers, which are essentially matrices in maths. And you whatever high level algorithm you have is going to be a very large matrix, and it's going to be decomposed into a number of small matrices. But we're not going to get into the math of it, we're going to focus on the software side of it. A little bit of introduction on what Qiskit is first of all. So it's an Apache 2 licensed software. That means it's open source. You can download it to your local computer and you can play with it, you can run it, you can write code for it. And it started in 2017, so almost 10 years now, about 9 years running. It's vendor agnostic. What does that mean? It does not matter what type of hardware you're using. You can be using superconducting qubits or ion traps or whatever hardware you have. This is a compiler that works for all of them. Right now, the beauty of it is it's very fast because the underlying code is written in Rust. For those of you not aware, Rust is a language which is just as fast as C++, but provides much better memory safety. But the good thing is it has a Python wrapper on top. So for a user, you don't need to play with an obscure language that you've never dealt with. You can just write code in Python and run it. So we're currently in the 2-point release cycle for Qiskit, which will soon have a fault tolerance as well, which is we're currently in the NISC era, right? Which is Noida intermediate scale computers. We'll soon move to fault tolerant computers, which provide you with better error rates, and you can actually run quantum algorithms on it. We're still running quantum algorithms, but with a lot of heuristics to minimize the errors. Soon everybody can write their own quantum programs without having to deal with errors. So the agenda for today's workshop is we'll quickly run through this presentation to have a small deep dive in what Qiskit provides and what are the things you can do with it, followed by a small hands-on session so that you can learn the very basics of Qiskit. So Qiskit largely provides you these modules present here. We'll primarily look at the quantum info and the synthesis module. So quantum info, as the name suggests, is the more math-oriented module, which is quantum information, and synthesis is synthesizing whatever algorithms you have to whatever the quantum computer requires, right? These are the two modules we'll look into. This is the general overview of what Qiskit looks like. So at the very bottom, which is the backend, you have Rust code, which is all inside Rust crates. So crates are what libraries are to Python. So crates are to Rust. In those crates, you have whatever underlying algorithms exist, and then you expose that using Python and C to the user. Now, the thing is, for first years, if you want to get into quantum, this is probably a very good way to get into it because you have a language that you can work with and you don't have to deal with all the math behind it, right? So I urge all of you to go to Qiskit's repository online and just look at open issues and see if you can try and solve something. Unless you get your hands dirty with it, it will be very hard for you to get in this domain. Right? So this is the general overview, or this is the general structure of Qiskit. And this is the structure we're concerned with for today. So we'll be using whatever is underlying in Qiskit using the accelerate crate. So this is a much more cleaner architecture and a module-wise architecture of what all there is in Qiskit. So this also represents the general lifetime of how you create quantum circuits as a user. So say for example, you have some quantum algorithm and you want to run it. You start off with creating a quantum circuit. The quantum circuit is going to build your algorithm, but at a very high level, right? So similar to how you write code in Python. So it's going to hold a very high level algorithm for you, and then you send it to the compiler, which for us is called the pass manager. So there is a sequence of passes that you go over your quantum circuit to modify it, after which you get something known as a DAG, which is a directed acyclic graph. Don't worry about it, you'll learn about it in your next semester, probably in DSA. But after compiling, you then send it over to primitives, which is just the backend that you want to execute your circuit under, followed by whatever result you get in post-processing. Right? So let's start with Qiskit Quantum Info. So it provides a number of different data structures to store your data, be it states, operators, or channels. These are all related more tightly to quantum information than to CS. So let's think of these as black boxes for now that you can use to come up with your own algorithm. The next module is synthesis. So now that you have your black box, right, you give that to the quantum compiler that breaks it down to some basis sets. Now, in quantum computers, we have qubits, similar to how you have bits in a regular computer, right? So what a qubit is a quantum bit, right? So these bits have individual gates acting upon them, known as 1 and 2 qubit gates. As the name suggests, 1 qubit gate will act on a single qubit, 2 qubit gates acts on 2 qubits. So whatever high level algorithm you have now, you decompose it into 1 and 2 level, 1 and 2 qubit gates, which can then be applied to whatever hardware you're dealing with. Then you have a plethora of different tools that Qiskit provides. For example, the random state vector, random unitary. So if you're working with randomized algorithms, these are probably things you should look at. And so the best practices is probably something you can skip for now, but I'd urge you guys to go over the repository and learn more about it. So these things are more deeply tied with quantum mechanics and quantum computing. Right. So again, as we stated earlier, so this is what the general life cycle of a quantum program is. You start with a quantum circuit, which is a problem encoding, as you can see on the top, the first row, the user side row. The problem encoding is a quantum circuit and set of operators, which is essentially an algorithm that you run. The algorithm is compiled for whatever backend you're using. And once you get those results, you post-process them classically. Right. So maybe this is a good time for us to move on to the hands-on session now that you have a basic idea of how Qiskit works. So give me a second, I'll switch the laptops for now. So I hope you have the notebook installed. How many of you don't have the notebook yet? Okay. I'll assume that you all have it then. You don't have it? Okay. You guys have this notebook or not? If not, I'll probably add the link for you guys. Okay, give me a second. Is the link at the top visible? Okay, I'll give you guys a minute. Go to this link and download the Python notebook available here. Then you can run all these programs for yourselves. How many of you do have the notebook? Please raise your hands. Okay. Yeah, the Jupyter. Yeah. Yeah. Sorry? Yeah, so the link, yeah, you can download it from there. So if anybody is facing any difficulties, please feel free to ask me for help. Does anybody need any help or can we move along now? And if you're still trying to access the notebook, yeah, exactly. Just download the notebook. If you have the notebook. Yeah. Sorry? No, it won't exact same. Right, so let's start at 2:55. I'll give you guys 3 more minutes to set the notebooks up. Please feel free to call me for help. Yeah. 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 Yeah, that's fine. If they just get the I'll begin. Guys, so I'll help you guys download the notebook as well. So just give me a second. So open whatever browser you have, okay, and go to this link. So Arif is a co-worker of mine. On his GitHub page, you will find follow demo Qiskit right here. Right? Go here and simply go to the basic architecture demo IPNB. And then from here you can download it. Right? So I'll repeat once again. Go to this link here, github.com/rf-3 and go to the follow along demo Qiskit. Yeah, AARYAV, RF, ARAV dash 3. Yeah, so the username here at the top left. Go here and then from there you can go to follow along demo Qiskit, wherein you'll have the first notebook. Basic architecture demo.ipinb. Does everybody have it now? Okay, cool. I guess we can proceed then. So if you don't have a Jupyter environment set up, that's also fine. You can just go to Google Colab and upload your notebook there as well. Okay, so now that we've talked a lot about Qiskit, let's see how it actually works. So within the book, there are a few dependencies that you can install. You can just run it, and these are just some version checks. Okay, so finally we are moving on to some real quantum problem, right? Now, quantum computers have a plethora of different applications. One of them is ground state estimation. So you must be familiar with the chemistry that you've studied in school, right? That you have different molecules and each electron within that molecule has some ground state energy, right? Now, this is of particular use to the industry for several reasons. Say, for example, drug discovery or materials discovery, things like that. So, why do we want? Now, this problem is also very hard to do using classical computers or even supercomputers sometimes. So, that's where quantum computers come in. Quantum computers provide a very natural way for us to solve these problems. So, what we'll do is we'll abstract away the actual problem for now, but we'll solve a ground state energy problem using IBM's simulator for the timing because it's a very small problem and you can run it locally on your system. So this will give you an idea on how to use Qiskit. So this is more related to chemistry. We start off by defining something known as a Hamiltonian. A Hamiltonian dictates how some chemistry or chemical system will evolve over time. So we start off by defining a Hamiltonian, and this is just some basic Python that you're running here. So as you can see, we're using one of the representations we just went over in quantum info, which is called a sparse polyhedron. So now that you have defined your Hamiltonian, you're going to essentially plug it into the circuit here. So this is called an evolution circuit. The point of this circuit is to simulate whatever chemistry related structure you're hosting and get get some results which then you'll use for post processing and get the ground state energy of the atom or molecule, whatever you're working with. right? So here you're assigning some parameters or the time evolution parameter specifically on how far along do you want to evolve or quote unquote see what the ground state energy is at say some specific time. So we add this parameter here, which is the time step t, which is equal to 0.7, and you can see here in the circuit that the time step comes here. Right, so are you guys able to follow along for the timing? I hope you're running it locally as well. Okay, so yeah. Now, how do you see the evolution of a quantum circuit or a quantum state? Qiskit provides something known as a state vector. You use that state vector, and what you do is whatever circuit you've created, right? You pass it within that state vector to see how the circuit is changing. So this is something a lot of people in quantum information use to see the nature and the behavior of their quantum algorithm or circuits. And this is just a very nice way to draw. So this looks very archaic, right? It's not very easy to read either. So you also have a ton of different ways to format and read your results better. Then you have multiple ways. So now that you have the state vector, right, you want to the ground state energy estimation, as the name suggests, requires you to estimate something. So the state vector estimator is something that does that for you. You take the state vector, you put it inside the estimator, and then you can use it to estimate the ground state energy of whatever molecule that you're working with. This is what we do next. Now, this is where the fun part, which is more relevant to you guys, starts. You've seen this entire algorithm run, and you've seen how you can solve some quantum computing problem, right? But what's actually happening on the inside, right? You've seen a very abstract level problem, but how do you actually run it on a quantum system? So underneath a quantum system, what happens is you have something known as a directed acyclic graph. Why do we call it a directed acyclic graph? So first of all, in computer science, graphs are essentially a data structure which has nodes and edges. These nodes hold data and the edges are sort of connections between these nodes. So as you can see, this is a graph. Why do we call it directed? As you can see, there are arrows between these nodes that tell you what is the exact order of operations. If you see in the circuit, you see that the first operation that you see is this giant red box, which is called a Hadamard gate, the edge gate, followed by an operation that's acting in two qubits at the same time, which is called a CNOT gate. In a similar fashion, you can see here in the directed acyclic graph, the first operation that you have is that blue node called the Hadamard gate, followed by the control NOT gate, the CX gate, and so on and so forth. Why do we use this representation? This makes the compilation process very easy for us. So that's why we work with DAG, and this is where traditional data structures and algorithms come in, right? So quantum has a lot of things and you can do a lot with it, but to run a quantum computer, you still need classical computers, you still need classical algorithms. Right? So now we have a DAG, we can play with it. So let's just print all the nodes that the DAG has. Yeah, so as you can see here, we have the H node, the CX node, as we noted in the diagram right above, the polyevolution operator, which is the giant operator we created. The barrier is just a cosmetic, nothing too fancy, and then the measure operations. Now, what you can do is you can also remove or add or maybe change operators within the DAG. We do this specifically as a part of the compilation process. Here we're going to do a very simple thing. We're just going to remove the barrier operation. So when we do that, as you can see here versus here, there is a barrier node here, which is no longer here. So this enables us to perform a lot of powerful compilation techniques within the directed acyclic graph. And now that we create the new circuit here, we can see that the barrier is missing from here as well, as opposed to here. No, we haven't measured yet. Cool, right? Now the first step is complete. You have your quantum algorithm, you can compile it, but how do you actually run it, right? So say for example, you're a quantum computing company, you have your own quantum computer. you want to define a target or essentially a backend on which you want to run your computer. So how do you do that? You create a target object. Now, what target is essentially a representation of the backend you're going to use. It holds all the properties about the backend, the different kinds of gates you can apply, the different kinds of error rates it has. So what we're doing here is we are creating a 4-qubit target that is a quantum computer with 4 qubits, and we're adding some properties. So for example, we're adding some properties for the Rx gate, for the RZ gate here. So what this says is that, okay, the amount of time that this operation is going to take is 25 e to the power minus 9, and the error per operation is 1 e to the power minus 4, right? So since this is a local simulation, we can make anything, right? But naturally, the simulatable limit traditionally is around 32 to 34 qubits, and for IBM's actual systems, you can go up to 150 something ish qubits. So the qubits here hold, so these qubits are what you process the quantum data on. You apply gates on these qubits, which is how you create your own algorithm. Now, naturally, the more number of qubits you have, the better of an algorithm you can come up with. The only issue is the qubits themselves have some connectivity constraints. So for example, we saw a 2-qubit operation, right, which is an operation that happens from the first qubit to the second qubit. But that may not be the case. So for example, there could be 2 qubits, say the 0th qubit and the second qubit, which are not connected. So how do you apply operations between them? So it's important to have such a target data structure for your work, for your case, because that sort of tells you on, okay, what are some permissible operations? How do you actually want to come up with the quantum algorithm to make it efficient, to make it simulatable, stuff like that. So what here we are doing here is we are explicitly defining the computer that we are going to run our algorithm on, right? So once we have this, you can see simply printing target is going to give you the the location of where the exactly, right. So with every qubit that you add, right, the number of states you can handle grows with the power of 2. So for example, you have 2 qubits. The total number of states you can handle is 2 to the power 2, which is 4 exactly. Now this is immediately clear that it's an exponential growth. So if you have 10 qubits, you can have 2 to the power 10 different states, which is 1,000 states. Now if you have 100 qubits, you have almost a million or a billion states, right? So the it grows exponentially, and with an additional single qubit, the power of the quantum computer increases, which is why it is also very hard to simulate them classically, which is why we cannot go beyond, say, 30 or 32 qubits, right? So that's why we need actual hardware, and we cannot just work with simulations. Yeah, they all happen at the same time because that's inherent to the nature of quantum mechanics, right? So that's the principle on which these quantum computers have been built. Right, then we can further print the operations that the target can do. Yeah. Yeah, exactly. So with these gates, you can come up with your own algorithms, and there are, in fact, there has been a lot of research going on in quantum computing as well. So what the general trend is, yeah, exactly. But those, yeah, exactly, exactly. So what these gates are more native to quantum computing. So for example, the Hadamard gate is one gate that lets you use the concept of superposition. That's not something you'd find in classical computing, right? So they have a different set of gates altogether, right? Okay, so now we've defined target, and we can also see the operations that we can do on our own defined backend, and we can also see the error rates time that we'd require for each operation by printing their parameters. Now, for the constraints that we have for the circuit we are using, it's called we talked about qubit connectivity, right? So it may not be the case that you can apply some 2-qubit operation on both the 0 and the 1 qubit at the same time. So this is called the coupling map. As you can see, when we print the coupling map here, we see, okay, we can have 2-qubit operations on the 0 and the first qubit, the first and the second qubit, and the second and the third, not between the 0 and the second qubit, and so on and so forth, right? So you need to have the coupling map in mind as well whenever you're actually compiling your algorithm for your specific use case. So that's a lot of things, right? But so what IBM does is, within Qiskit, you have something known as the pass manager, which essentially takes care of everything for you. So what the pass manager does is it's going to take in your abstracted circuit and it's going to spit out some optimized circuit compiled for your backend. Right. So let's see here. What we have is we have this function called generate preset pass manager, which essentially gives you an object that can then compile whatever quantum circuit you have. Based on the optimization level, the circuit will shrink to a smaller size. Why do we want smaller circuits? Because they're less prone to error and we can run them more efficiently, more quickly, and the actual output will be a lot nicer and have a lot less noise. That means it will actually mean a lot more than just random noise. Yeah, so we define the circuit right above, right? This is our circuit, the first object that we defined, this here, circuit, and we applied these operations as follows. So we applied the Hadamard gate. So this is where the circuit is being defined, followed by the operations that we are applying on it. So we are applying a very simple Hadamard gate followed by a controlled NOT gate. So this is just a simple controlled NOT gate, similar to what you have in classical computing, followed by the evolution operator. Right? Yeah. So now that we have a circuit ready, we have a target ready. Now we can finally move on to the actual compilation process. So these are different types of compilers that we are essentially making here while defining the optimization levels. So naturally, optimization level 0 means it's going to be the least optimized, with optimization level 3 being the most optimized. So let's run these and see what happens. So this transpile function here, right? This transpile is what it's doing is it's taking the circuit and it's taking the backend information in target. Essentially what it's doing is it's seeing, okay, these are the operations the quantum computer supports, these are the operations the user wants to do, how do I interchange them, right? So you end up with a new circuit, and in the following cell block you can see how different optimization levels sort of change the circuit. So for example, at optimization level 1, the depth of the circuit is 36. Optimization level 3, it's 24. A lower depth is better because that means we're going to use a quantum computer for a shorter amount of time and have lesser errors. So this is how different optimization levels sort of affect your circuit and algorithm. Yeah, so the depth and the size are essentially telling the number of operations that you have to do. So the larger the depth and the size, the more operations you have to do on the quantum circuit, which means if your algorithm is running for a longer time, since quantum circuits are a very sensitive system, right? They're very prone to error. So the longer you run a circuit, the more likely it is that the information on it gets destroyed, right? So for example, in optimization level 1, the depth is 36. So that means let's assume that for a single layer, that is one of those 36 layers, you need to run the quantum circuit for 36 seconds, for 1 second. That means for the entire circuit, it's 36 seconds. Similarly, let's assume for the circuit with the depth of 24, you want to run it for 24 seconds. Now, as you reduce the number of time, right, you would have a lot lesser errors, which means whatever computation you're doing has a lot more meaning. You're not losing information because, again, quantum computing systems are very sensitive to noise. So this is a visual representation on how the circuit looks after compilation. So remember how we defined these operations, right? That the target has either the RZ gate, the RX gate, or the control NOT gates. These are the only gates that are being now used within the compiled circuit. So we have changed the circuit from our original large abstract version to a hardware compatible compiled version now. Now this is obviously not as optimized. You can also put in the directed acyclic graph for it. If you were to print the optimized circuit, you can see how it's a lot smaller we had for the T1 level. Now that you have the circuit, you can go ahead and run it on backends. For the purpose of this demonstration, we'll be using a fake backend, and you can try running this for yourself. But in a similar fashion, you can go to IBM's cloud platform, and everybody who creates an account there has 10 minutes of free access to access IBM's quantum computers through cloud and run this on real hardware. So that is real quantum computers, right? So it's not some technology that's distant in the future. You can access it right now and run whatever algorithms you have, and you can play with it and experiment with it, right? So how many of you actually got a chance to run the code along? That's fine. So I guess we can take some questions now, and I'll keep the link open for you guys in case you want to download the notebook, right? So yeah, feel free to ask any questions. So that's an end-to-end Qiskit software stack and how you can use it for your own quantum algorithms and compilation to run your algorithms on real hardware. Yeah. Yeah. Yeah, exactly. So there are a range of things you can do. So within the GitHub repositories, there are a ton of open issues. Before actually starting some proper projects, I'd urge everybody to just go and look at them, sort of understand how large code bases work, right? The thing with open source software is it is supposed to be very robust because you have a lot of people working and you have some maintainers who maintain all the code. There are like thousands and thousands of lines of code, right? So it's very organized. You can go to the GitHub page, you can look at open issues and see what you can do, and that's probably the best way for you to learn about both quantum computing and quantum compilation. Just pick up issues, start doing it, and once you feel that you're comfortable with the open source environment, when you're comfortable with development, you can probably pick up a bigger problem statement and you can do that as a project. Right? So just go to the GitHub. They have contribution guidelines as well. So they'll explicitly tell you how you can go about contributing to Qiskit. Yeah, okay. So I'll show you guys once again. So you have to go to this GitHub link right here. So just write github.com/this username, rf-3. On there, you will find the follow along demo Qiskit repository. Within that repository, when you open it, you'll have the basic architecture demo notebook. You can click on this and then download it from here. So this entire notebook is available for you. And yeah, I guess that's it. So do you have any questions? All right, good. And feel free to reach out to me if you have any questions or if you want to learn more about computing and compilation in general. Right. Thank you. Are you going back? Yeah, I have a meeting. I think it's in 15 minutes or so. 3:30? Yeah. Okay. How was the session? Good. So how did you find, I got the feedback. How did you find the session? You put some feedback. What did you learn? If we could have something that has a dignity, for the discussion, I guess that's for not there is the lunch. I'm sorry. They will break the lunch now or what? Yeah. So the one was
achievement of quantum technology. So let's thank our idea. So let's see how this so please thank my students, children.
IBM, we have several business units. Right?
So please, put your hands together for Mr. Shobit also.
So how did you find them? It's good news. They are very practical. You will take it forward. Speak them more often.
May we have everyone's attention?
Thank you, Shobit sir, for that insightful and hands-on demonstration, making quantum computing not just understandable but truly exciting for all of us.
We now come to a moment of heartfelt gratitude. It was an honor to have Sir today with us. His presence, insights, and experiences have truly enriched this session and made it a platform of inspiration and knowledge. May I request Professor Dr. Natasha Hastir ma'am and Dr. Selvamurthy sir to kindly step forward to felicitate Shobit sir. May I request Shobit sir to kindly step forward to receive the felicitation. Let's have a huge round of applause for sir.
We now move to an exciting and intellectually vibrant segment of today's program, Quantum Leap, presentations by student. This session celebrates the curiosity, creativity, and research potential of young minds who are stepping into the fascinating world of quantum technologies. It is here that ideas take shape, questions challenge conventions, and the future quietly begins to unfold.
To lead this session, we have with us Professor Dr. Moinuddin Sir, Professor at Jamia Millia Islamia, a senior academician and researcher with extensive expertise in physics, particularly in quantum mechanics, condensed matter physics, and advanced materials. He has contributed significantly to teaching, research, and mentoring, and his work includes numerous publications in reputed journals, and he has actively guided postgraduate and doctoral scholars while contributing to academic collaborations and scientific outreach initiatives. May I now request Sir to kindly deliver the opening remarks? I also welcome him on the stage.
Good afternoon. Am I audible? Respected Dr. Salamurthy sir, Dr. Gopal Bhushan sir, distinguished guests, respected faculty members, dear researchers and students. It is my pleasure to welcome you all on this symposium, Recent Advances in Quantum Science and Technology, here at Amity University. Today's gathering under the theme Quantum Leap, reflects the rapid progress in this field. quantum science and technology has moved beyond the theoretical curiosity. Now it has become a driving force for the futuristic technologies like quantum communication, secure communication, quantum computing, precision sensing, and advanced materials. So, whatever was available previously in the laboratory, now it has moved out to the laboratory, and now it is the reality. We have seen many systems demonstrated openly to the for field demonstration. So, uh, this field is very important. The importance of this field can be seen by the fact that last few years you see the Nobel Prize winners starting from 22, 23 and 25. All the Nobel Prizes are swept away by the quantum communication technologies. So, this field is very important. I congratulate Amity University to start to have a lead in this, starting this symposium, taking a lead, because most of the colleges or universities still they have not initiated this. But you are at advanced stage to start this kind of technology. So I congratulate sir. Uh, Now. I would say that in this session, I want to encourage all the students to take a part, ask as many questions as you can, try to explore new perspectives. So, with these few opening remarks, I again congratulate and welcome you all for this important session. Thank you so much, and wish you good luck.
Thank you, sir, for introducing the session theme with your great words of wisdom. We are also privileged to have Professor Dr. Ashish Mani, sir, as the session co-chair, who will be moderating and guiding the session proceedings. I invite you, sir, to the dais.
Joining us virtually, we have Dr. Ritajit Majumdar. He is a research scientist at IBM India, working at the intersection of quantum computing, algorithms, and advanced computational technologies. His research focuses on developing scalable quantum algorithms and exploring practical applications for quantum systems. He has contributed to cutting edge research in quantum information science and actively engages with academia and industry through collaborations and knowledge sharing platforms. We warmly welcome you, sir, and thank you for joining us today. I would now like to invite you to briefly address the gathering. Over to you, sir.
Yeah. Thanks a lot. Thanks a lot for having me. Let me share my screen first. I hope this is visible, right?
Sir, it is visible.
Okay. Yeah. So without wasting time on anything, let me jump on very quickly to the topic that I wanted to discuss. So I want to very quickly give you a state of the art that, as you all know, that IBM kind of built the first quantum computer, is the leading R&D in quantum computing. So I want to give you a very quick update on what it's about and what is the state of the art, what is coming in the next few years. So the mission of IBM has always been to bring useful quantum computing to the world. So when I say useful quantum computing, what it means is that first it should have some proper application area. I know Shobit has been talking a bit about different applications in, say, biochemistry, drug discovery, chemistry, all of those stuffs. So we want some practical applications and not some just theoretical research is coming out of this. And at the same time, we want a scale, because as you all understand that it's takes a lot of effort and a lot of money, to be honest, to build a quantum computer. And it makes sense to use a quantum computer only when you are actually doing something which is beyond what a classical computer can do today. Just like example, if I ask you to do, say, add 2 and 3, you can do that by hand, by in your mind. You don't need a very powerful supercomputer to do that, right? So if I give you a slightly complicated calculation, maybe you'll use your calculator. And today we have calculators in our mobile phones and everything. So you'll use the calculator. If we have even more difficult computational problems, you will write some codes and you will run it on a computer and say you have really strong or really powerful machine learning, image processing, or different kind of things that even your desktop or laptop cannot handle. That's when you would want to go for GPUs and HPCs and everything. So the way we like to think of quantum computers is that it's another method, it's another tool for doing numerical studies, and we want to use that tool at a regime where these existing tools do not work. So some of the key milestones in bringing useful quantum computing to the world has been in 2023, we established quantum utility. 2026, this year, we expect to demonstrate quantum advantage. And finally, 2029, we are going to deliver the first large-scale fault-tolerant quantum computing. I'll give you a very brief overview of each of these without going into technical detail. So quantum utility, here we basically showed that you can solve a physics problem. Again, for the lack of time, I won't go into the technical details of this problem that we were solving. It's basically a 2D transverse field Ising model for those interested. And we were calculating some properties of that system. What we showed is that 127 qubit, if you remember something that Shobit just said, that 32 qubit is what we can simulate on a laptop that we have today. And I'm talking of 127 qubits, which is way beyond what we can simulate. What we showed is that even in a quantum computer that we have today, which is noisy, and we do not have error correction. So if there is an error, we don't know how to correct it yet. I mean, theoretically, we know the hardware is not yet at the point where we can correct it. But even on a noisy quantum computer, we were able to obtain accurate results at this scale, at a scale where brute force classical computer is failing. And there are many other clever researchers in the world who came up with different types of approximate quantum computing techniques. But these computing techniques are now basically fighting or trying to get as good as what a quantum computer can do. So this is what we call as quantum utility, that if I give you a problem to solve, the scale where we want to solve, then quantum computers are reliable computational devices where you can expect to get accurate results even on a noisy scenario beyond what you can do classically. And what happened after this paper came out in around, I think, November or something of 2023. And before that, you would see that people were kind of playing around. The number of qubits that they used for their problems was around 13, which you can very easily solve on your own laptop. And even what we show is that you could have done that in a 1981 PC as well. You don't need most advanced devices that we have today. But today, even from 2024, 2026, we are here today, but even from 2024, the average number of qubits that all the users are using throughout the world today is 115. So we are on average, this is the state of the art where we are regularly, not only IBM, different institutes, different academic institutes, different R&Ds are running experiments at a scale which is beyond what a classical computer can do. And this is coming from every different domain that we can think of. You can think of high energy physics, you can think of many body physics, you can think of optimization, you can think of chemistry, optimization again. So all of these you can think in every domain we are today able to do this. Coming to India, yeah, I made this when around 2 months back when I made this, I kind of kept this that India is yet to make this huge list of such experiments. But today I can be very happy to say that with BITS Goa, we have a paper on high energy physics, which is perhaps the largest experiment done all over the world till today. Which, I mean, this utility paper that I talked about used close to 3,000 gates, and here we used close to 18,000 gates. And you can see that the results that we are obtaining here is pretty accurate. This is the quantum result, this is the classical result. and you can see the amount of time that classical methods like tensor network or Pauli propagation is another newer methods they take versus the Heron device, the quantum computer which is coming to India sometimes maybe this year or early next year in Amravati. You can see the amount of time it takes. So we are already pushing the boundaries of what classical computers can do. And I want all of you, now that you are getting started, or some of you have maybe already got started, to remember that this is the state of the art. And once you are mastering this, the research kind of thing that you want to do should be at this scale to be at par with what is happening internationally. This year, what we are going to demonstrate is quantum advantage. So I already talked about utility. Utility means is that if I give you a quantum circuit, you cannot run it on a classical computer because of the scale, and you can get reliable results from a quantum computer. But you can also argue that, okay, there are other methods like tensor network, Pauli propagation, they are still giving you results. So advantage is when we can definitely say that no, a quantum circuit is a quantum computer is the best platform to run a quantum circuit and not any other platform. This is what we are thriving for this year. And we expect certain kind of problems like sampling, which is around, say, optimizations and others. Expectation values, these are around all these Hamiltonian simulation, high energy physics, etc., etc. And variational, which is mostly around chemistry and biochemistry. These are kind of the domains that we expect are going to show advantage. And as I said, that we predict that quantum advantage will be found by end of 2026, but only if we work together. So when I say if we work together, what I mean is that there are so many academicians with domain expertise, right? So the expertise of the domain is required from academia, and the expertise of hardware, software, tools is required from industry. So once we come together, we should be able to attain advantage. None of us can do that alone if we try to do. And finally, I'll just end with this, that as we are looking forward to 2029, we are expecting to deliver fault tolerant quantum computers. So I said that quantum computers today are noisy, and if there is noise, we want to correct the errors. And what we have shown over the last 1 or 2 years is that such efficient error correcting codes exist. We can do computation on those error correcting codes, and decoding is also possible reliably. And this is the roadmap. Last year, we already showed a 2 logical qubit system called Loon. This is not available for use to the external users. This year, we are going for what we call Kookaburra with 12 logical qubits. Then we will have a modular structure where multiple 12 logical qubits come together and talk to each other and create this. And finally, all of them coming together, not only 2, many more of them in Starling, together with this magic state factory, all of these coming together in 2028. In 2029, this will be available for the users to use. So this is the current state of the art. As you see, the IBM Quantum System 2, this is from IBM Poughkeepsie. The IBM Quantum System 2 is already there. The IBM Starling that I showed you for 2029 is under development, and so is IBM Blue Jay, which is going to be a much, much larger scale fault tolerant quantum computer, which we project to come sometimes after 2033. So I hope this gives you a broad idea of what we are doing, what we have done, where we are going with this. And I really hope to see some good experiments and everything coming from the attendees of this conference. Thank you.
Thank you, sir, for your insightful words and for inspiring us. We are also honored to have Professor Dr. Neelkant Kundu joining us online. An assistant professor at IIT Delhi, he specializes in quantum physics, quantum information, and related interdisciplinary domains. His research interests include quantum correlations, open quantum systems, and quantum technologies. With publications in leading international journals, he is actively involved in teaching, supervising research scholars, and contributing to the advancement of quantum science education and research in India. A warm welcome to you as well, sir. I would now like to invite you, sir, to briefly address the gathering.
Yeah, hello everyone. Thank you for this kind invitation. I hope you can hear me.
Yes, sir, you're audible.
Okay, yeah. So I will just briefly go through my slides. So My research is on the applications of quantum technologies for next generation wireless communications, and basically my research area is 6G wireless communication and how quantum technologies can improve the performance of future telecommunication networks. So, since we don't have much time, so this slide is basically showing that as we move from 5G to 6G, we require extremely high data rates, low latency, and for this, we require new physical layer technologies, novel signal processing algorithms, and quantum information technology is an emerging technology which can help us to achieve some of these requirements. So here, this quantum communication technology is what can help us in security, apart from quantum computing and quantum sensing, also which can improve the performance of future telecommunication networks. So I'll just briefly go through that all the information technology which we are using these days is the result of the first quantum revolution, which used the average or the bulk properties of quantum mechanics. For the transistors, lasers, and optical fiber, they are based on the average properties of quantum mechanics. And now what the second quantum revolution is taking place. So what we are talking right now is the second quantum revolution, where we are reaching the Moore's law. So now we want to engineer single photons, single electrons, atoms, and molecules to develop new technologies which have better performance than the classical counterparts. So basically, if we work at this nanoscale and we harness these quantum properties, then we can have very high performance as compared to the classical communication, computing, and sensing technologies. So, in communication, quantum communications can be helpful for security, for improving the data security. Computing can be used where we can use quantum algorithms for solving complex optimization problems in 6G and beyond. And also, quantum sensing can help us in better timing synchronization to improve the localization accuracy of GPS. And this quantum enhanced localization, quantum radar, and LiDAR are some of the technologies for telecommunication. So this is how quantum enabled future network will look like. So it will be a 3D network where the core network will have this some of the quantum computing capabilities, and the access network will be connected to quantum base station using terahertz and optical fiber optics or free space optical links for quantum communications. So this will ultimately lead to the development of this quantum internet, which will be an upgrade of the current classical internet. So the quantum internet will basically add an additional quantum layer of the current internet and help us in improving the secure communication for network quantum computing, for improved sensing, timing, and GPS performance. And it will have this new devices like quantum switches, quantum repeaters, and quantum computers also. And even our mobile phones are expected to have some quantum technology capabilities for improving the security of the data which we are transmitting. So I hope the audience is well aware of this, the difference between bits and qubits. So by using this superposition and entanglement property, it can help us to provide truly random numbers which have a lot of application in cryptography, in quantum key distribution to secure our communication using this no cloning theorem, and to enhance the computing power for certain computational problems. And also, quantum computing is being explored to improve the performance of machine learning algorithms for which uses this entanglement properties for high dimensional Hilbert space feature extraction. So, QKD is basically helpful to improve or overcome this computational security of the current RSA algorithm. So, as we know, this Shor's factoring algorithm, when it runs on a like a fault tolerant quantum computer, it can break our current encryption scheme. So that's why we require algorithms or cryptography which are secure against quantum computers, and quantum key distribution is one of the technologies which can help us. So basically, currently the industry is looking into two possible solutions. One is this post-quantum cryptography, which is basically a software-based solution, and the quantum key distribution, which is a hardware-based solution. And it basically QKD can provide unconditional information theoretic security using the laws of quantum physics, and PQC is a near-term solution which replaces our current computational problems with a much harder problem for which no quantum algorithm is known for now. But this it's not a foolproof algorithm, because in the future there might be some algorithm which can break these PQC algorithms as well. So without going into detail of this discrete and continuous variable, so basically QKD has a lot of applications in healthcare, government, banking, for smart grid national pipelines, and it can be easily integrated with our TCP/IP model. So basically, QKD will be an additional hardware layer which will distribute the keys using the principles of quantum mechanics, and then these symmetric keys can be used for higher layer encryption algorithms like the IPsec or MACsec, TLS, SSL, and HTTPS or SSH. So, and this is how the QKD network is going to look like in the future, and it will be an important add-on for improving the security of our telecommunication networks. And these are so. In the interest of time, I think we can stop here. But yeah, so we have also been working in how quantum machine learning can be used for solving wireless communications problems and signal processing application like human speech emotion recognition. These are some of our recent works. And also we have been working to develop the basic system modeling and analysis of Rydberg atom based quantum radar and analyzing its performance compared to the classical radar. So yeah, so these are some of the challenges which we need to overcome. So I hope as we move into this, our India's national quantum mission is under way, and by the end of this quantum mission, some of these challenges will be overcome, and India will be in the leading position of emerging quantum technologies. So yeah, I just want to acknowledge the funding agencies, and these are my relevant publications which you can go through if you want to have more details. And yeah, finally, thank you for your attention, and yeah, I'm open to questions.
Thank you, sir, for your valuable time and insightful remarks. We now move forward to the heart of this session, the student presentations. We have 4 groups presenting their work today, each bringing forward unique perspectives and innovative ideas in the domain of quantum technologies. The first presenter of the day is Dhruvi Shah from Integrated BTech and MTech from Space Science Institute, AISST. The topic of her presentation is AI-driven autonomous satellite mega constellation synthesis and quantum enhanced multi-tier collision risk mitigation. Over to you, Dhruvi. Let's have a huge round of applause for her.
Hi, good afternoon, everyone. My name is Dhruvi Shah. I am from Amity Institute of Space Science and Technology, and I am going to present my work on quantum enhanced multi-tier collision risk mitigation and satellite constellation synthesis. We'll be going through all these topics throughout our presentation.
Can we have all the other presenters on the dais, please? Let's give them a huge round of applause, everyone.
No problem. So while we are talking about the constellation, mega constellation design or satellite constellation synthesis and collision risk mitigation. So one of the most important problem that we face is the traditional low Earth orbit designing. It's like fundamentally broken for the modern era, because in the modern era we have thousands of satellites in the low Earth orbit or the medium Earth orbit, but while they are all in their orbits, there is a risk of collision, a risk that they might collide with each other or with the debris that are there in the space. So, because of which the static and single objective, non adaptive traditional methods are not applicable in the today's problem. Moreover, there is a risk of O-N2 conjunction problem, that is the quadruple time multiplying of the computation. Next are objectives. Keeping in mind the problems that we face, our objective is to revolutionize the low Earth orbit mega constellation designing. So here we introduce an AI-driven method for mega constellation design and a quantum-driven method for risk mitigation of collision. We also face some research gaps as the recent or the current research do not unify the collision avoidance and the designing of the constellation. So this is our workflow. This workflow has been divided into two sections. First section is the AI-driven model for satellite constellation generation, and the second is the HQTCS, that is the hypergraph quantum temporal collision avoidance system, which is a multi-tier collision mitigation system. As you can see in this workflow, we start with graph generation for the AI model, and then we go for a graph neural network model. Then we optimize the model for intra-satellite collision. Then we move forward to the quantum-inspired collision avoidance system, where we have multi-tier, that is intra-external and debris collision avoidance system. Moving forward to our AI model. So this is our, we design a graph neural network which uses the k nearest neighbor graph construction on the Earth's central inertial positions. As you can see in this image, this is a demonstration of the k nearest neighbor satellite graph. And we also use self-loop to ensure that each satellite receives its own features and the weighted aggregate of its spatial neighbors during message passing. We have a 3-layer graph neural network, which is followed by batch normalization and dropout for regularization. Next, we move on to our hypergraph quantum temporal collision avoidance system. It is a 3-tier collision avoidance analysis. First tier is the intra-satellite screening, that is, this model evaluates all the satellite of the constellation for internal collision. Second is the external satellite conjunction, in which all the satellites are evaluated with respect to the other satellites in the orbit. Then we have the debris collision avoidance, in which all the satellites are evaluated with respect to the debris in their path. Next, we go for hypergraph risk representation. Why we use hypergraph? Because we are considering thousands of satellites at a time, and multiple satellites can have a risk of collision at a single time or at a given moment. Because of which we are going for hypergraph and not a single or secluded satellite maneuver at a time. Next, we go for our quantum enhanced maneuver planning. Why we use quantum here? Because we are planning maneuvers for multiple satellites at a time. Multiple satellites can also have a risk of colliding with themselves while maneuvering, because of which we are using quantum over the graph, over the hypergraph representation that we saw in the previous slide. So what are our why do we use it, and what are the benefits of using quantum? So it optimizes the maneuver. It also reduces the cost by using quantum Hamiltonian encoding. It also reduces the fuel consumption, as fuel is a very important factor while we are in a satellite, while our satellite is in the orbit. We also use quantum here because it transforms the discrete maneuvering planning into a variational quantum problem, and it reduces the time of maneuver planning from months that our traditional methods take months to plan a single maneuver, while our quantum enhanced method plan multiple maneuver within seconds. Now we get to the results of the models. So here you can see in the first image, this is a 3D representation of 1456 satellites designed by the graph neural network. On the other side, you can see two matrices. First is the graph neural network matrix. It shows that our model has very well created or generated the orbits of the satellites, that are 1456 satellites. Next, you can see is the quantum temporal collision avoidance systems matrices, where you can see the assessment time of the entire process with external and debris collision mitigation was 23.5 seconds, which is way less than the traditional methods for a single satellite. And here you can see below there is a table which shows us the 6 or 7 satellite or the orbit parameters. Yeah, 2 minutes. Where we see the orbit parameters of the 10 satellites out of the total number of satellites. Here you can see is the collision assessment risk estimation by NASA, the HQTCS data here. And then there are three graphs. First is the total loss graph, which shows that in the beginning the loss for 500 epochs was not acceptable, but after that for the next 4500 epochs, the loss has degraded significantly, which shows the model is good to its results. Then we have the next graph that shows the orange line, that is the orbit's mean square error, and the green line, that is the safety binary coupling error. And the last graph shows the average safety prediction. Then here you can see the maneuver, the executed maneuver and the threats. In the conclusion, I would like to say that our model has very well designed a high precision collision free constellation generation. Thank you.
The next presenters are Swayam Kohli and Vishwas Kesarwani from BTech Information Technology. Their topic is performance investigation of quantum key distribution system through free space optics.
Good afternoon, everyone. Today, I, Swam, and Vishwas are presenting the study Performance Investigation of Quantum Key Distribution System through Free Space Optics, with a focus on how environmental conditions affect the performance of quantum key distribution systems. So, this study investigates the feasibility of secure communication in dynamic scenarios like vehicular networks. Moving with the introduction.
So now, what are the key outlines? Not waste time, let's move to introductions. What is quantum communication? The main question is that. So quantum communication is a principle of quantum mechanics such as superposition, entanglement to transmit information securely. Now coming to what is QKD. QKD stands for quantum key distribution. QKD is a technique used to securely generate and share encryption key using quantum states. In this process, one user encodes bits into photon perception properties such as polarization and the other user measure them. Core principle, no cloning theorem, which means unknown quantum states cannot be copied. Security. So if any attacker tries to intercept the transmission, it introduces errors which is known as QBR, which stands for quantum bit error rate. If QBR exceeds a threshold, the key is discarded. Need of QKD in vehicular communication. The challenges for vehicles are like modern vehicles exchange critical data like location, speed, braking signals, authentications. Current encryption techniques like RSA and ECC is vulnerable to future quantum attacks. This creates serious risks such as remote hijacking, fake traffic signal commands. Now, why we combine FSO plus QKD for vehicles? Because free space optics uses laser-based communication through air instead of optical fibers. Fiber is not practical for mobile environment like vehicles. FSO allows flexible deployment in vehicle, infrastructure and even drones. Working principle of QKD. QKD uses core quantum principles such as no cloning theorem, which I have told earlier, superposition, measurement, disturbance. QKD workflow. There are two users commonly called Alice and Bob. Alice sends photons encoded with specific quantum states and Bob measures these photons using randomly chosen bases. After transmission, they compare a subset of their data to detect errors. But there is another method to transmit information through FSO channel. But if in FSO channel, if eavesdrops is present, then the quantum states get disturbed, which increases QBR, quantum bit error rate. Now coming to the BB84 protocol, which is the most widely used QKD protocol. It used two types of bases, rectilinear basis, diagonal basis. Each basis represent bit using different polarization states. As you can see in the table, there are rectilinear bit with bit values 0 and 1. 0 represent horizontal and 1 represent vertical. And diagonal represents 0 and 1 has bit value and it has 135 degree for 0 and 45 degree for 1. So if the sender and receiver use matching bases, the bit is valid, otherwise it is discarded. If an attacker measure in the wrong basis, it introduces error. These errors are later detected through QBR analysis. Another protocol considered in this study is COW protocol or coherent one-way protocol. Instead of polarization, it encodes information using time slots. Pulse is first slots represent 0, as you can see in the figure. DM1 is uses 0 has slots. Pulse in second slot represent 1. It is easier to implement and support higher key generation rates, making it suitable for practical systems. With this theoretical background, I now hand it over to Swam to explain the system model and represent result of the study.
So moving to system model, this study utilizes a QKD-enabled free space optic architecture tailored for vehicular environments comprising three main components. That is the quantum source, which is used for photon key distribution. Then coming to the key distribution, which uses polarization encoding. And the last is vehicle mobility model, which is used for simulating real-world movement. Then we use the communication channels, which includes Li-Fi VLC for short-range links, FSO links for long-range communication. The atmospheric attenuation impacts performance significantly, modeled as 0.14 for clear conditions, 0.42 for rain, 0.6 for fog. Moving to the system flow and adaptation. In this system, Secure communication between vehicles is achieved using quantum key distribution over a FSO channel. The process begins with a quantum source generating entangled photons, followed by polarization based encoding and decoding for secure key exchange. To simulate realistic vehicle movement, tools like Sumo and MATLAB Simulink are used. For short range communication, Li-Fi or visible light communication enables high speed data transfer, while the FSO channel handles long range links and models real world conditions like clean air, rain, and fog. The generated quantum key is then transmitted and processed to the system. To ensure reliability and security, four key mechanisms are applied, that are error correction, privacy amplification, adaptive power regulation, and beam steering. Then moving to the results, the study has found out that the study has come up with simulation setup and the resulting error performance. On the left, the table summarizes key system parameters. The data rate is set to 1 Gbps with a sequence length of 1024 bits, and the optical components such as 700 nm laser and polarization settings are used for encoding. The FSO channel operates over a range of 200 to 700 meters and models real weather conditions like clean air, rain, and fog with different attenuation values. These parameters ensure a realistic vehicular communication environment. On the right, the graph shows QBR as a function of channel loss for different QKD protocols. At low channel loss, all protocols maintain low error rates. However, beyond around 25 dB, the QBR increases sharply. Importantly, 884 BB84 consistently shows the lowest QBR, indicating better reliability. This matters because higher QBR directly reduces the ability to generate secure keys, limiting overall communication security. Then from at the left graph, we can see at loss channel loss, BB84 achieves the highest key rate, reaching around 56 kbs at 10 dB. However, as channel loss increases, the key rate drops rapidly for all protocols. This happens because more bits are lost during transmission and a large portion must be discarded during error correction and privacy amplification. So there is a clear trade-off between communication distance and key generation rate. On the right, the graph shows performance under different weather conditions. Clear weather provides the highest key rate, rain shows moderate performance, and fog performs the worst. This is due to the increased atmospheric attenuation, especially in fog, which significantly degrades the signal. Then, to understand the results physically, we look at the received power behavior. From these plots, as the FSO range increases, the received power consistently decreases. This degradation is the most severe in fog, followed by rain, while clear weather condition maintains the strongest signal. Device angle also plays a role, where misalignment at 45 degrees result in additional power loss compared to 0 degrees. This behavior follows the attenuation relation. Loss is equals to alpha into D. For example, at a distance of 0.3 km, fog with an attenuation coefficient of 0.6 results in 0.18 dB. This increased attenuation directly reduces the received power, which in turn leads to higher QBR and ultimately a low secure key rate. So this ties the previous results together by linking channel condition to system performance. To conclude, this study shows the BB84 performs best among protocols. Secure communication is maintained up to 29 dB loss. Weather, especially fog, significantly affects performance. Range varies from around 280 meters in fog to 650 meters in clear condition. Overall, QKD over FSO is feasible for vehicular communication, but requires adaptive mechanisms to handle environmental variations. These are the key references that form the foundation of this work. These works provide the theoretical basis for the system and analysis presented here. Thank you.
Can I ask just one question? Like, can you hear me?
Yes.
Yeah, so why is the secret key rate of BB84 higher than the PLOB bound?
Can you please repeat once again?
So why is the secret key rate of BB84 higher than the PLOB bound? So PLOB bound is the upper bound, right?
Sir, we have seen that QKD is more reliable than the other two protocols in compared to transmission of data because it is more secure than other two protocols. That's why we are showing with due to QBR we are measuring the error rate of that.
No, but the secret period cannot be higher than the plot bound. That is the ultimate upper bound. How you are plotting the plot bound?
So we are using the
Minus log to
performance
1 minus eta, right?
Yes, sir.
The plot bound is minus log to 1 minus eta, where eta is channel transmittance. So that is the upper bound. Have you read that paper, the plot bound paper?
No, sir.
Yeah, actually the results are not consistent because the secret period cannot beat the plot bound. You need to check the simulations.
Okay.
Okay. Okay. Thank you.
Yes, sir.
Thank you, sir.
Please give them a huge round of applause. For the next presentation, we have Prateek Singh and Iranpreet Singh from BTech Information Technology. Their topic is Quantum FSO Fiber System using BB84 QKD protocols.
ये वाला था। Good afternoon, respected chairs, esteemed guests, and my fellow researchers. Today, I, Iranpreet Singh, along with my teammate Prateek Singh, are going to present this work on simulation investigation of a quantum FSO fiber system using the BB84 QDK protocol under severe weather conditions. As we stand at the threshold of 6G and post quantum communication, two questions are certain. How do we transmit the data at enormous speed? And second, how do we guarantee that no eavesdroppers can ever intercept it? Quantum key distribution and the BB84 QDK protocol are offer a physics guaranteed answer. But deploying it in the real world over free space of in optical link subjects to fog, rain, and haze is a formidable engineering challenge. That is precisely the challenge that we tackle in this work. So first, why quantum FSO? Quantum free space optical communication is a secure high bandwidth communication technology that uses laser beams to transmit quantum encrypted data through the air rather than through fiber optic cables. It enables ultra secure communications like QDK between ground, stations, aircrafts, and satellites. Further, Prateek.
Good afternoon, everyone. I am Prateek Singh, and in this work, we will present the BB84 quantum key distribution protocols. Now, let's move how it works. As we can see in the diagram, first, Alice encodes bits into photon using different bases. Then the photons are transmitted through the FSO channel. Next, Bob measures them using random bases. After that, they compare bases and keep only matching results. Finally, this matching bit forms the secret key. As we can see in the figure, first of all, we will transmit a photon of any digit from Alice encodes, and that will create a secret key to the last. Moving to the next slide, we have proposed the system architecture. Alice generates random bits and encodes them into photon, while Bob selects random bases to measure them. The photons are transmitted and both compare their bases publicly to form a secret key. The system also evaluates performance under different weather conditions using the Q factor. If the quality is high, a secure key is generated. Otherwise, the process is repeated. Now passing it to Iranpreet.
Now we will talk on the impact of atmospheric conditions on FSO signal quality. First, we will talk about the attenuation coefficients and models that we have used here. Here, fog is the worst offender, as the tiny droplets that massively scatter the light. It gives reference to Kim model. For the second one, rain causes moderate damage with large droplets that reflect or refract the beam, giving reference to cruise model. Third is haze, which is mildest, only 4.2 decibel per kilometer. It gives reference to Beer-Lambert plus Kim model. We have used these formulas, attenuation for rain and then for fog attenuation as well. We have taken OSNR, which is signal power divided by noise power. Signal quality is measured through OSNR, simply the ratio of signal power to noise power in decibels. Here we have calculated Q factor calculation and representation. The Q factor is used to measure the quality of a signal. A higher Q factor means better signal quality and low error. Here in the first graph, you can see a low power graph where the clear air, haze and rain are above the Q factor line, but our fog is under the Q factor line. In the second graph, it is a high power graph where clear air, haze and rain are falling above the Q factor limit in all distances, but considerably the fog just cruises down at 12 kilometers. Here we can see rectilinear and circular eye diagrams. Here we have rectilinear has given much better results, as a wide open eye means clean signal and a closed or messy eye means poor quality. Going to next slide.
Now in these slides, we will further move to fiber range and polarization comparison. We can see that we have taken different weather as clean air, haze, rain, fog, and we have also calculated rectilinear signal in circular phase and in rectilinear. Now we will find the key findings from it. Maximum 15 kilometer fiber achieved under clear range, that is best among all of them. Fog limits fiber range to 10 kilometer. Rectilinear polarization consistently outperforms circular polarization. Eye pattern is formed which Iranpreet has still. Now moving to the next slide, OSNR versus FSO range. As we can see, we have taken in x-axis FSO range and in y-axis OSNR in dB. As the distance increases, OSNR decreases in all weather conditions. Clear air performs the best, while the fog shows the maximum degradation. Haze and rain have moderate impact. This indicates that weather, especially fog, significantly affects system performance, particularly at longer distance. We have also the key observation and conclusion of this PPT is the system works well up to 550 meter in all weather conditions. However, in fog, the signal become weak after 400 meters. So we may need extra techniques like error correction or relay nodes to maintain good performance. Moving to next slide. Here we have Stokes parameter analysis. What is Stokes parameter analysis? Stokes parameter analysis are used to describe the polarization of a signal. Here also we have taken on x-axis different weathers and on y-axis we have taken Stokes parameter. Now the conclusion of this graph is fog affects performance even at shorter distance. Clear air shows the least degradation, confirming that atmospheric turbulence is dominant impact factor. Here is comparison of all this, and in this the work we have done is the range we have taken, the rate we have taken, the protocol what we have used, the Stokes what we have done. This work uniquely evaluates rectilinear and circular polarization with Stokes parameter.
For the conclusion, in conclusion, this work demonstrates a BB84 QDK system integrated over hybrid FSO fiber link can maintain reliable, high quality transmission at 1 Gbps even under challenging atmospheric conditions. By evaluating Stokes parameters, OSNR, received power and QBER across rectilinear and circular polarization states, we have provided a comprehensive performance blueprint for designing future quantum communication networks. Thank you.
Any questions? No, so let's proceed with the next speaker.
Next, we have Arjit Tomar from MTech Computer Science and Engineering, ASET. The topic of his presentation is Novel Quantum Linear System Solver with Preconditioning for Quantum Computer.
afternoon, everyone. My name is Arjit Tomar, and I am from the MTech Computer Science Engineering first year students. So today I am going to share my knowledge and study work on a novel quantum solver for a system of linear equation with preconditioning. Basically, in this study, I have compared one traditional algorithm is called HHL algorithm in quantum computer algorithm, and one is a advanced algorithm in the same field is VQLS algorithm. And in the end, I have worked on the problem and overcome with the preconditioning VQLS approach to solve the limitation of the both algorithms together. So before going to a main agenda or main study work, I just want to give you a brief introduction about the problem, why we need to address this problem. So here we all have know about the system of linear equation we have done in the 12th and 10th in the standards. So in this we are finding a unknown variable from the linear equations with the help of our tools and set of algorithms. One of the most important and traditional algorithm is a Gauss elimination method, which takes a big O of n cube complexity to solve these linear equations. So we have done this with the help of pen and paper, but we need to know why we need to focus on these kind of problems. So here is the big problem of matrix. It is a 256 cross 256 matrix problem. It contains approximate 65,000 elements in the matrix. To solve these type of problems, we need advanced computers and calculators to finding a solution. But today we have applications like internet, web graphs on Google, social networks like Facebook, Instagram, and LinkedIn. Those all are having a matrix size of 10 to the power 9 cross 10 to the power 9 matrix size of problems. So these problems are containing 10 to the power 18 elements in the matrix. So today's classical computers and supercomputers are good to solve till 10 to the power 5 matrix. But if n is greater than 10 to the power 5, then supercomputers are not possibly solve these kind of problems. So here we need something better and faster to solve these type of problems today. So we have our quantum computers here. As we all know, and our previous guide, previous faculties and other give you information about the quantum computers. So I am not going in a deep. Just give you an introduction that why it is important. So quantum computers are their ability to achieve a exponential speed as compared to classical computers and supercomputers with the help of parallel processing capabilities. They are efficient to solve problems like optimization, simulations, and large systems of linear equations. Those are not possible for classical computers and today's supercomputers also. So we have a quantum computers, but we need a perfect algorithms to run and solve these problems on a quantum computers. So here, first breakthrough get in a 2009, where three MIT researchers propose a algorithm is called HHL algorithms. So HHL algorithm basically a first algorithm to solve these linear equations on a quantum computers. Here we are not able to give our direct inputs like matrix and vectors in a quantum computers like a classical computer. So we have to build a quantum state to perform any operations on a quantum computers. So here HHL algorithms work in four stages. First is a state preparation where we encode a vector B into a quantum states. Then in the next phase we are working on a quantum phase estimation where we find eigenvalues of a matrix to solve a linear equations. Next step is we inverse the eigenvalues to perform a unitary operators on a quantum computer to solve the matrix problems. In the last, we reconstruct the solution. Same happen with the solution that quantum computers give us a quantum state, not a perfect vector to understand. So here in the fourth step, we simply rebuild the quantum state in a classical vectors to understand the result. Here you can see the quantum circuit for a HHL algorithm. In this, we are using a three type of qubits. First is a input qubit, which is we encode a vector B. Second is a register qubits. They are help to performing a operations or a quantum gates on a linear equations. Last one is a ancilla qubit. It performs a rotational part of the quantum circuit where our quantum operations are reversible. So we cannot get a direct answer after performing a single operation. So first we perform a phase estimation part, then we reverse the quantum phase estimation with the help of a ancilla qubit, and in the end we measure the output in a X quantum states. HHL faced some challenges in to solve our linear equations on our current hardwares. Those are big issues and for today's quantum computers only. So some of these are important. Here is a condition number. First is a condition number. If our matrix is ill conditioned with a large k number, so our algorithm directly depend on a condition number with the complexity of log n into a k square. Here condition number directly effect on a HHL algorithm speed and it decrease the accuracy also. Next bottleneck is a noisy hardwares. Because today we do not have a perfect quantum computers, we can't run proper HHL algorithm and get accurate answers like a classical computers. So here we do not have a perfect quantum computers. Because of the noisy hardwares, we get our next challenges are deep quantum circuits where HHL requires a big quantum circuits to run the algorithm and solve the linear equations. To overcome these challenges, we get our advanced algorithm is called a VQLS algorithm. It is a variational quantum linear solver, and we can say is hybrid quantum classical algorithm designed to solve our linear equations Ax equals to b. Here we are using a machine learning or classical approach with a quantum computer to solve a linear equations on a current quantum hardwares. You can see in the diagram that how we can train our VQLS algorithm to run and solve the linear equation. Here we are following the 5 steps. Basically, first step is a classical approach where we are initialize a parameter called theta. Theta is a error measurement unit between our desired output and our observation output. In first step, we just guess the theta, and then in the next step, after the guessing the theta, we run the circuit on the current theta. Then in the third step, we calculate the loss or error based on the target task. In the fourth step, we classically optimize with the help of machine learning optimizers like ADAM, SPSA to calculate a new better theta values. And in the end, fifth step, we just simply repeat the repeat the 2 to 4 steps. Here is the quantum circuit for HH for VQLS algorithm where we are performing first we solve with the guess theta, then we calculate the theta again and again run the circuit with the new theta value, and at the end when we get a minimum error, then we measure the output. So these are the advantage of VQLS and limitations. So the one of the most important limitation is a condition number with a ill matrix. Here condition number not directly impact the VQLS algorithm, but impact indirectly when because ill condition metrics require more optimization steps and more circuit execution that increase the time of processing. In over this, so overcome with this condition number problem, I have worked on it and get a preconditioning VQLS algorithm. I have used a ILU preconditioning technique that is work with a VQLS algorithm. In this, I am using a incomplete LU factorization that is approximately like a exact solution to preconditioning the our problem. I am calling is a hybrid ILU preconditioning VQLS pipelining where instead of using a AX equals to B, we use a modified problem with preconditioning. In this process, we use two stages of pipelining. First is a classically approach where we compute the ILU and transform our problem. And next we perform the VQLS algorithm. Here is the matrix which I have I have taken and the condition number is 6.9612. Matrix is here, you can see. I have used a IBM processor, quantum processor unit hardware to run on a real quantum hardware. I have used a IBM Fizz quantum processing unit which is open for all to work and implement your programs. Here is the results of the problem. In this, we get a related error of the problem after the implementing on a real hardware is ILU get a 2.164 into 10 to the power minus 5 where HHL is 9.354 into 10 to the power minus 5. IPU qubits used in ILU VQLS is 3 and HHL takes 8 qubit to solve this problem. Where is the one of the important phase is a quantum depth because we have a noisy hardware, so quantum depth is a most important. ILU takes a 21 gates and HHL takes a 9453 gates. Time processing unit is 18 seconds for ILU VQLS and 517 seconds for HHL algorithm. And one of the most important thing is a condition number. You can see in the last that after preconditioning VQLS get a one condition number and HHL get a run on a 6.9612 condition number. So thank you.
Thank you to all the student groups for their insightful and thought-provoking presentations. We now come to a moment of heartfelt gratitude. We are deeply honored to have our esteemed dignitaries with us. We sincerely thank them for their valuable time and present them with a token of appreciation. To reflect on these ideas and share their perspectives, I now request our esteemed experts to offer their concluding remarks, which will be moderated by our session co-chair, Professor Dr. Ashish Mani, sir.
So first of all, I will request the chair, Professor Mohideen, to share his feedback on the presentations.
This is very interesting symposium on the state-of-the-art technology, which is conducted by Amity University, and we are fortunate to listen the different experts working in this field today. So I hope this symposium will be very useful for the faculty members as well as the students. And I also expect that this symposium will go outside the Amity also. You will invite other institute students and faculty members so that it will become a big event. Still, today it's a big event. You have almost invited all the experts working in the field. And I again congratulate Amity University to have an initiative on this technology, and I wish you good luck. Thank you. Thank you so much.
Thank you very much, sir. Dr. Majumdar from IBM, are you there? Dr. Kundu from IIT Delhi.
Yeah, I'm here. So, yeah, thank you for this opportunity. I had a great experience there, and I appreciate all the students who are working on this emerging quantum technologies. And yeah, I congratulate all of them, and yeah, best wishes to all the students working in this domain. Yeah, thank you for having me here.
Thank you very much, sir. From the audience, if anyone wants to give their feedback or ask any questions from our students. Okay, thank you very much.
May I now request the dignitaries to kindly join us for the felicitation ceremony. And may I request Dr. Selvamurthy sir to please come forward to felicitate sir and Manoj Kumar Pandey sir. Professor Dr. Moinuddin sir, we sincerely appreciate your presence and insights. Please give him a huge round of applause.
We now request our guests to join us on stage. Dr. Preeti V. Shah, Mr. Siddhartha Sood sir, Dr. Selvamurthy sir, Dr. Manoj Kumar Pandey sir, Dr. J.K. Rai sir. With this, we conclude the Quantum Leap presentation by students session, and we now begin with the valedictory session. And as we approach the concluding segment of this remarkable event, we now take a moment to reflect, celebrate, and carry forward the ideas and inspiration gathered here today. We are honored to welcome Professor Chandradeep Tandon sir, Additional Pro Vice Chancellor, Amity University, Uttar Pradesh. It is our privilege to invite a distinguished leader whose work exemplifies the seamless translation of the next generation technologies into scalable, outcome-oriented solutions around the world. He has been instrumental, currently serving as the CTO for the distribution sector at IBM Consulting. He has been at the forefront of driving impactful industry solutions across global enterprises. May I now request Mr. Siddhartha Sood sir to kindly address the gathering. Let's have a huge round of applause for him.
Respected sir, uh, respected sir, faculty members, all the distinguished guests who have come in, and fellow students, right? It's my pleasure actually to come here and see the progress that Amity is making in the field of quantum. As I was thinking about what I'm going to talk to you, one thing was very important and very close to me, which is technology keeps shifting and keeps evolving, right? And in today's world, there is no important technology than quantum computing in terms of how it's going to shape us. I am from IBM, and quantum being a very large spectrum of the work that is being done, what I do is to take the technology to our clients. My job is to make sure that I go and work with the clients in order to help them understand what the technology can do. And because it's still nascent, because we are still in the era of quantum utility, as some of my colleagues already told you, there's also a responsibility to make them understand how we can solve some of their biggest problems through quantum, either now or in near future. But IBM is not just about quantum. IBM has made big bets in technology for a long, long time. In the 1960s, and I want to go back to the history because, and why I want to do that is because nothing comes easy. And that's what I want you to take back as I finish the talk, right? So back in 1960s, a bit in the history, IBM launched its efforts on System 360, which we today call as the IBM mainframe. It took about 5 years to be built. It took about 3 years to stabilize in the market. And then it became the unprecedented computing leader in the market. Till today, there are about 70% transactions, banking transactions that run, 70 credit card, 90% credit card transactions that run on an IBM mainframe. And it's a phenomenal technology that has stood the test of time. What it tells us is that when you are building something big, like quantum, example in the mainframe era, you need the patience, you need the engineering, and you need the business conviction to be able to do it. And it takes time. Another example in the more recent is our own story around hybrid cloud and AI together. When IBM was talking about hybrid cloud and IBM acquired Red Hat, everyone said that no, hybrid cloud is not going to be the future. The future is public cloud. Every enterprise is going to rip off their data center and go to the public cloud. They said IBM is acquiring Red Hat. That's not the right acquisition to make, and it's not something that we do, and all of that. That was done into 2019. And if you look at today, if you look at 7 years down the line, what you see here is that everybody is talking about hybrid cloud. The world is hybrid. The world is hybrid multi-cloud. It's not public cloud. And that is conviction. And what I'm trying to tell you is something that I heard very recently our CEO talking with analysts, right? So this is not something that I have made it up. It is something that our CEO and the market believes in. So with that, why I'm telling you all these stories is because when you look at quantum, it's not going to be a single day journey. It's a lifetime journey for some of us, right? For some of us who have seen quantum grow from 2015, where it became quantum experience, where IBM was able to get quantum out of the lab into the hands of people through cloud, to its evolution into quantum utility, what you see today, to the amalgamation of classical and quantum computing, like I was talking to Sir about, and the work that he's doing. It's heartening to see that there are avenues and ways in which we can try to solve problems with quantum better than classical today. So we have already pivoted, right? We have already started pivoting. We have already started creating value. And once we start creating this value, we now going to get moved into what is called as the quantum advantage, the age of quantum in terms of solving real problems. But that's again not going to be easy. At one point in time, IBM was in the hardware race. It was all about more qubits and more qubits and more qubits. They pivoted back in 2023 in what they call as better qubits, better computation, more gates. There's also the whole Qiskit movement that is going on in terms of how do you build better algorithms, how do you are able to run them better. So all of this is where the technology is moving, and IBM has a very transparent roadmap in terms of till 2030 or 2033, how can you build a better fault tolerant quantum computer. Now I was talking whether is that a convincing roadmap to some of our dignitaries. Well, that's for time to tell. But at least the roadmap has conviction in terms of steps that you can achieve in order to reach the end goal. At the end of the day, what I want to leave you with is the fact that there are organizations in the world that are trying to make it real. Now, why is it important to you as a student, right? Shobit was here from IBM. He spoke about Qiskit and how can you start running programs on Qiskit that actually run on the real quantum hardware or on simulators. We saw some of the work that the students presented. And it tells me that there is a lot of potential in us today start learning quantum. Some of us may not be from quantum background, some of us may not be from physics background, but the fundamentals are imbibed in all of us as we stand here today. It's a vast field. There is going to be something for everyone to contribute. And as I was talking to some of the other dignitaries also, the bar of entry in quantum is reducing. Right? You can be a student and you can enter and start learning. You can be a PhD researcher, you can be an MTech researcher, you can actually be a working professional. Even in IBM, there is a focus on having more and more people learn quantum, not just the folks that are actually in research. So with that, I want to inspire you. I want to make sure that you understand that there is a lot of work that is happening within quantum, and sky is the limit in terms of how you can contribute, learn, and make yourself a name in quantum. So thank you. Yes, so I think I must add that I had a wonderful discussion with Sir Murthy Sir, Nitasha ma'am, on how IBM and MIT can work together, collaborate together on the field of quantum, and we are going to take that forward. Thank you, ma'am.
Thank you, sir, for sharing your valuable insights and vision on the future technology. With deep expertise in secure communication systems and strategic technology development, Dr. Preeti V. Shah, Scientist F at DRDO, has contributed significantly to mission critical systems supporting national security and strengthening indigenous technological capabilities. Thank you so much. Welcome, ma'am.
This is just this first slide. Already. So I am Dr. Preeti Misha. I'm scientist in solid state physics laboratory. Hello. Hello. Yeah, so I'm Dr. Preeti Visha, scientist with one of the DRDO labs, solid state physics laboratory. And we are working in the area of different kind of semiconductors, starting from the basic semiconductors to advanced semiconductors to the futuristic semiconductors, then the semiconductors followed by the devices, then followed by their testings. After testing, the proper systems where our small devices, which are actually the heart of all the systems which you can think of, be it in defense, be it in space, be it in civil life, anywhere these systems, wherever they are, we make the heart and the key components of those systems. So today I am really glad to be here. First of all, respected Silvamurthy sir and the whole organization team, I want to congratulate you for this wonderful one-day symposium on recent advances in the quantum area. And I just hope that this would be a wonderful chapter in the quantum journey of India. So basically, before moving forward or जब तक ये PPT open होता है, two quantum questions I want to ask. The first is, how many of you are in the superposition state? This is for everybody who are on the round table, who are sitting there. Entangled, all are, I have already seen. But सुपरपोजिशन स्टेट में कितने लोग हैं? आज तो मॉर्निंग में बहुत ही अच्छे से सुपरपोजिशन समझाया गया है. Thank you. So nobody is in superposition state. That's also wonderful because I am assuming that the result has come and we all are awake, fully awake. Okay, that's wonderful. So because it is a valedictory function, right? So we have at least arrived, we have already arrived at the last stage of this symposium. And normally, yeah. So, okay. So normally, whenever we are at the closing stage, there is a recap, the whole day, what we have learned and what we have seen, and plus some takeaways. So I am just showing few slides. It will be a kind of recap and just a, interaction with you. So let us see. One more question I want to ask, because we are hearing from our dignitaries, from our wonderful speakers since morning about the different verticals of the quantum technology. This we have understood that it is a huge spectrum of quantum and it is a multidisciplinary field. And as Siddharth ji has pointed out, that now the bar has been lowered down and a lot of people can enter into this area. So just I want to know before I move forward that what is the core element of these quantum technologies? Any core element which you can think of. I'm not talking about the verticals, that is absolutely fine. In those QKDs, in those communication, what is that thing that is giving so much impact to this quantum? So basically, the quantum technology is harnessing the fundamental behavior of your atoms, your molecules, your photons. And on this, how they are going to revolutionize to measure the smallest signal to compute, as Sir has told, or to communicate in QKD. All right, and how it is able to exhibit the superposition discussed. Second, how it is entangled and how it is showing the interference. These are the fundamental principles over which the whole vertical of quantum is laid down. So let us quickly see that how the quantum technology is going to revolutionize. You can see this is a autonomous vehicle. We know how it will move. It requires GPS, right? Everybody? At least raise hands. Yes, you know that GPS is there for the autonomous vehicle driving. Great. So suppose we are going for any family trip, or maybe because I am from DRDO, so my soldiers are there in a war scenario where there is no GPS. There this quantum sensors will step in. They will step in. There will be, atomic clocks. There will be atomic magnetometers. There will be atomic gyroscopes or accelerometers where they are actually exploiting their basic atomic properties and use them in your clock. So even if the GPS is not coming from the satellite, the atom, they have a fixed energy levels, okay? Some microwaves are coming. You have a particular frequency. There will be some tuning will take place and resonance happens. As this resonance happens, a signal will come. This signal can be exploited in a vast field of these quantum sensors. It could be clock also, so this will become your clock signal, tick, 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 or it can be your magnetometer signal, it can be your position or velocity signal. So this is how our small atoms are creating or revolutionizing this quantum sensor or this complete quantum field. Now the question, one more very interesting thing. If suppose you can make these atoms in a smallest possible devices and with your latest laser technologies and your quantum phenomena, if they all get mixed, then you are going to have miniaturized version of these fences. Because this is a world where you need everything portable. Everything should be battery operated. It should have small power. It should have small size. Everything should like this. Swap should be very, very less. So for that, miniaturization is important. And these things can bring that miniaturization possible. So as a defense person, I would say that I am able to give my soldiers on the wrist the watches or on their bags those watches where they can have, even if the satellite is not there, GPS is not there, they can work in the war scenario. So it is a race. The global race is going on. We have understood since morning that in all the areas, US is trying to establish its supremacy in the using these processors, be it IBM or the Google. Then China, we know, you must have heard, 12,000 kilometers quantum communication network they have established between the two major cities, 17 provinces. Europe is trying to understand much more navigation systems. So that means what I mean to say and why I am bringing it, I am just bringing the point of Siddharthji, what he was telling on text on the screen, that if you will see that till 2025, you can see the global effort is around $60.4 billion. And if we'll go to the next slide, in 2034, 25% increase of this. So this all is for you all, that this is not only a science and technology. There is a big roadmap which tells that how the money is going to invest it. And many of you are going to have your startups in this area if you are able to acquire these skills into it, right? So let's assume this is a quantum enabled war field. What exactly you need for it? Tell me just one single thing. What exactly you need for it? Okay, quantum sensors you need, quantum communication you need. quantum in cryptography you need, all these things you need. That is absolutely fine. But other than this, what exactly? Suppose in this war scenario which is right now going on, can you believe that the other countries to whom you are dependent upon will provide you these things? No, they are not going to do that. So the important thing is indigenization. Indigenization of all these things which you are seeing on the screen is must required to become independent, indigenous, and to have our own quantum ecosystem in India. The indigenization is important, and it should be started with the design level. The design, then the components, then the device, and then your complete system. So then only with this indigenization in the quantum area, that is very much required. So India has already, we have already heard about National Quantum Missions, which has actually laid the foundation for this. Then we have DRDO, ISRO and other organizations. We have rising startups which are already doing this work very proficiently and will take some more time to start. And in this way, we can actually develop the ecosystem in India. But one thing is important, then starting from school till the industry, starting from startups till the product development agencies, every layer need to be strengthened. Every layer, and where the work for academia, the work for DRDO organizations like DRDO, ISRO, and your industry comes. And from here, I am proudly saying that DRDO initiative of DIA COE initiative has this main goal only, that how we can bring all these three agencies together, can align the goals which can help us in indigenizing these kind of latest futuristic technologies. So in particularly my lab, these are the some efforts which we have done. So we have recently inaugurated, Secretary Sir inaugurated QTRC, Quantum Technology Research Center at Metcalfe House, wherein we have facilities for the quantum sensors, for the quantum communication, and some work for the quantum computing is also going to start. So all the students who wants to learn, who want to see some optical characterization measurements or communication systems, how the algorithms are being run, they are most welcome. The faculties are also most welcome. They can come and have a look. So as I was mentioning in my afternoon discussion, that these are the one of the indigenized component which at SSPL we are making to miniaturize the quantum sensors are these microfabricated alkali vapor cells, which are going to be the heart of all the quantum sensors. We talk about clock, and I would like to mention that all these things are being carried out here in India at SSPL, most of the things, or even if we are acquiring the services for anything, they are also in India. So our efforts are totally indigenous, and we actually welcome everybody to come join us, align with our goals. And this is my last slide, just to tell that how we, academia and industry, can help each other to, be on the roadmap of quantum. So we have DIA COE, we have CARS, we have other projects, we have interns. Now we have paid interns, just now that also has been opened up. And then there are some technology funded projects are there, other projects are also there. So there are various things through which this skilled manpower, because that is also one of the very important thing, can be generated. Thank you very much.
Thank you, ma'am, for inspiring words and your invaluable contributions to national technological advancements. Joining us virtually, we have Dr. Vishal Saraswat, sir, who leads research and innovation in cybersecurity at Bosch Global Software Technologies, with a focus on quantum safe cryptography and resilient digital systems. We request you, sir, to share your thoughts with us. Over to you, sir. Let's give a huge round of applause to him.
Hey, thank you for inviting me, and apologies. I have another event in Chennai where I have to be, so I'm joining online. So I've been seeing at least just before I joined, just before this panel, and I saw some of the student presentations, and I see that great, or at least I see a start of a great adventure. So throughout the day, possibly you have heard a lot about quantum computing. Just now, our colleague from DRDO, they spoke about quantum sensing. And that's one thing that we are also doing a lot at Bosch. Like when we talk about quantum, generally people think of quantum computing at most. Sometimes they think of quantum communications. But when we talk about quantum technologies, it's a lot talking about something to look into quantum materials, quantum devices. They are a huge field. And frankly, if you think of it, and if you want to think what is something that you will have in your hand in your lifetime, I would bet quantum sensors would be something that you would possibly see in practice soon enough. You will not have a quantum computer unless you access through, of course, IBM's Qiskit or something. But quantum sensors are something which are almost here, and they are going into production, and people are already seeing the benefits of the prototypes that are out there. So at Bosch, we are making quantum sensors for medical devices like your pacemakers, glucose monitors, and we are making quantum sensors which could go into navigation systems. We are making quantum sensors which should go even in your machines which are used for mining, for oil exploration, or even exploration in Arctic below the ice. So that's something that's happening. So our DRDO colleague, they did not mention another use case, but a lot of other colleagues have heard from quantum-enabled radars. So quantum sensors, they can make our radar technologies much more precise, much more. They can detect stealth. They can detect at much lower altitudes. So those are coming up. So when you are thinking of picking up research in quantum, that is another topic that to look into: quantum materials, quantum devices, and quantum sensors, which somehow get overlooked at, but I think they are going to be of much more immediate use. I personally am a post-quantum cryptographer, and work with what happens when quantum computers are actually real, right? So I've been working in this world for 20 years now. I should have shared the slides. I'm using the slides, but I don't think I've shared those with you. Let me share the slides, just a sec. So hopefully you can see my screen now. Can somebody just give a heads up, hands up, or thumbs up or something? Is the screen visible? Yeah, great. Okay. Yeah. So, yeah, of course, I'm not going to go over some of the slides which you have throughout the day. You have possibly seen a lot about quantum computing. I'm sure many of my colleagues, they would have spoken about how quantum computing is already like improving a lot of kind of mostly simulation kind of problems, right? quantum simulation is one of the biggest promises from quantum computing, and then all kinds of optimization kind of problems, they can be solved much more efficiently. Uh, and they will have applications in anywhere from, like, let's say, traffic optimization, financial modeling, or climate modeling. You will have much better predictions on your weather, etc. Of course, in pharmaceuticals and bioengineering. Right? And of course, quantum cryptography promises to solve all security problems. But what I focus on is post-quantum cryptography. Because I have only 10 minutes, I won't speak about other topics. I'll talk a little bit about post-quantum crypto. So when we talk about post-quantum crypto, we are talking about cryptography that is going to run on your classical computers, on your smartwatches, on your phones, on your, or like even your pacemakers and glucose monitors, whatnot. It should run on that and yet protect against attackers who have access to quantum computers. So an attacker who could rent, let's say IBM makes a huge quantum computer, a cryptographically relevant quantum computer. I can possibly rent a day's worth of time and break the security that you are using today. So how to protect against such a scenario? So that's where post-quantum cryptography comes into picture, and that's where I work. And fortunately, there are many techniques available, and some of the techniques as old as modern cryptography, which are secure, or which are conjectured to be secure against quantum computers. And we implement such techniques to protect many of our applications and many of our products from a possible future attack. So, and guarantee your confidentiality, privacy, integrity, and authenticity. So, maybe through the day you might have heard this term, harvest not decrypt later, which is a huge threat to your current secrets, and that's where this post-quantum crypto comes into picture. And post-quantum crypto is very relevant in any scenario where you have secrets which you want to ensure that they remain secure and they remain secret, let's say from 15 years from now or more. So, of course, the companies were like, next 5 years, but even if you don't believe it, you can still believe that in about 10 years from now, very likely there will be cryptographically relevant quantum computers, and certainly 15 to 20 years from now, that's a pretty sure scenario when quantum computers will be there to break our current cybersecurity. And why worry now? Well, and one thing, if nothing, even if you don't believe quantum computers will become real, the various regulations in the countries, in various markets, they will force you to implement post-quantum cryptography, so you should worry about it. Okay. And yeah, then of course, you also have to worry about, do you really have secrets which you want to ensure, which you want to keep them secret for next 15 years or next 20 years. So you look at those scenarios, that do I really need post-quantum security? Well, maybe for your general day-to-day discussions, you possibly may not need, or let's say you do some online transaction, you go ahead and go to your bank, transfer some money to some friend. Maybe in such scenarios you don't need such security, maybe. And if somebody comes to know that you transferred some money to somebody, it may not matter to you. But in many use cases, it may matter. If you are transferring this money to for some nefarious, for some illegal work, then you might be worried, right? You may not do. And then sometimes there might be a statute of limitations legally, but still it may hurt you, right? Or sometimes, let's say you are doing something that it may not matter in a legal sense, but let's say you are having an extramarital affair. Then you may not want anybody to know even after 10 years or 15 years or 20 years, right? Many times people have to take some sort of hard decisions, business decisions, and in those times they may not want those to come out, right? So in general, you have to do analysis what kind of secrets you want to ensure that they remain secret after a few years, and you take such decisions. Or important is when you are talking about authentication, when you want to ensure who did this message come from or who you are talking to online, etc. And this becomes very important in many to your bank or when you are connecting to your email. How does the server know that it's you, right? And how does your computer know that you are connected to the right servers? That's where authentication comes. And when you talk about authentication, many times for your general day-to-day work, you may not need post-quantum security because the servers, they can easily change their certificates over a long period of time or quickly. Right? But when you are talking about products, like when you buy some product online or not even online, like you purchase your car, this car is going to be with you for a few years, right? 10, 15 years. Generally, a lifetime of a car could be anywhere between 15 to 30 years, right? So these come with various credentials which last for a long time. Satellites, they have a long life and they have authentication credentials which should be flashed onto the device during manufacturing, and they will be there throughout their lives. Manufacturing plants are machinery which have a very long lifetime. Critical infrastructure like your power plants, etc., they have a long life and they have authentication credentials which have to be there throughout the life. In such cases, you may be worried about post-quantum security, and for various use cases like when a car starts, how do you know the car was not tampered with when it was sitting in the garage? So at that time a boot check is done, and for that we need, right? And so on. So yeah, in general, a lot of use cases for which post-quantum security becomes important, and that's where we work. We implement at Bosch. We have various products here. So with this, I think I've taken more than 10 minutes and I should stop. But if you guys have any questions, anything to discuss, we can talk about that.
Dr. Vishalji, thank you so much. We will invite you separately for another presentation here in the campus. So that your area is very important. You have already produced many products and secure communication, post-quantum cryptography. These are all very important area for privacy, keeping all your information encrypted and saved properly. So this is very, very important, and we'll invite you. And thank you so much. Let's give a big clap to Dr. Vishal. Thank you so much.
Thank you.
Thank you, sir, for your insightful address and for highlighting the importance of secure and future-ready technologies. Continuing further, we now have an important academic segment. I invite Professor Dr. J.K. Rai, Head of Department Electronics and Communication Engineering, to introduce the postgraduate degree in quantum technologies, highlighting new opportunities in this emerging field. Please welcome, sir, with a huge round of applause.
Students will finish definitely by 5:30. Don't worry, because we have to catch cabs and we have to go, and we'll close quickly here.
Yes, so good evening, everyone, respected dignitaries on the dais and off the dais. Not more than 3 minutes from my side. Okay, great. So you have heard few words throughout the day today. One of them was National Quantum Mission, which Government of India has started so that India becomes a national global hub for quantum science and technology. Along with this, the AICT and DST came together to launch a program, MTech Quantum Technologies, to cater to the requirements. We also have MET Quantum Mission, which Dr. Selva Murthy sir was telling, and he has talked many of the times. So, to cater to the requirement of this quantum technology, MET is starting a new program which is MTech Quantum Technologies. This program takes the input from all leading corporates and experts. Some of them were present today also in the sessions from IBM and CDEC, but it includes the inputs from TCS and IIC Bangalore, IIT Bombay, IIT Delhi, all those places. So this is not just a simple program on quantum technologies. This is a program which can cater to the need of this quantum technologies in the field of sensing, communication, computing, materials, and the objective of this program is to train the students who can not only get trained in the field, but they can contribute to the growth of quantum technologies. And like it has been told, and even in this valedictory session by our experts, that this is a kind of interdisciplinary field, so any BTech graduates can come into the program or walk into the program. So we have kept it open for all branches of engineering, this program, and we will train them accordingly. So I will not take much time. Thank you, everyone.
Thank you, sir, for that informative introduction. It is my honor to introduce Dr. Manoj Kumar Pandey, sir, HOI ASET, to formally conclude today's event. Over to you, sir. Let's have a huge round of applause for him.
He said 5 minutes, sir. 5 minutes, sir.
Thank you very much. So now, last 5 minutes, students and my faculty colleagues, it is quite difficult to sum up that task is given to me. The last row student who was sitting here, just last 5 minutes, your attention is required. If you sum up all these sessions that happened, and as per my understanding of the quantum technology computing is, it is just the next level of artificial intelligence. Now just visualize a scenario when artificial intelligence was doing a lot of tasks, and it is really the advanced stage of what we were right now expecting from the technology. It has a huge potential. AI have a huge potential of providing us the solution of every problem that we may think about in the world. But it has certain limitations. What are the limitations? Because AI is purely dependent upon the data. From that, the data will come to perceive the data, to capture the data. Second thing is to communicate the data. Third thing is to process the data. And next, fourth is, since we are dealing with the data across all the sessions, to protect the data. So these are the 4 stages when we were really using for helping the AI, the system. So now, to convert in the quantum, come to the quantum now. Quantum sensor to perceive the data now. We are moving the up stage. Quantum communication to communicate the data. Quantum encryption, decryption that you must have heard about. And third is computing, quantum computing. This is now converted into these 4 pillars. Now, Word was thinking about the conventional computer are having somewhere stuck. They have a limited power because it depends on the classical physics. These are called the classical computers. We need something different. Ab kya kare? What to do? Because our classical computer are based on 2 states only. Either 0 or 1, either true or false or something like that. But Word is not like that. Word is uncertain. Word is in between as well. फिर हमें याद आई एक साइंटिस्ट की, श्रॉडिंजर. ये वर्ड सुना आपने?
superposition theorem, entanglement, that every word came from Schrodinger's superposition equation, Schrodinger's equation. Einstein and Schrodinger has a fight among them. Their philosophy is fighting. Einstein says it's a particle. Schrodinger says it's a wave. It's a both. It depends upon how we, at what time you observe it. If you are observing it as a particle, it will behave as a particle. If you are observing it at a wave, it will be wave. अब क्या हुआ problem? जय हम देखना. What way we see the word, it is like that. So, my request to all my colleagues and students is to learn the quantum computing, quantum physics, quantum word was already there. You should be highly spiritual. कितने लोग हैं spiritual यहाँ पे? Highly spiritual तभी quantum कर सकते हैं, otherwise नहीं. Because quantum computing is, you must heard about Schrodinger's cat theory. सुना किसी ने? Schrodinger's cat theory is uncertainty. If you put a cat inside a box and put some poison there or decaying atomic things and a clock, based on the clock the atom decays and the poison releases, then the various type of possibilities happens with the cat. If you observe from outside, there are a lot of stages. जिंदा भी हो सकते, नहीं भी हो सकती, आधी मरी, कल मरी, all these things will be there. एग्जैक्ट कब पता चलेगा आपको? जब आप उसको ऑब्जर्व करेंगे, खोलेंगे जब डब्बे को. हम अभी तक कंप्यूटर में क्या कर रहे थे? डब्बे खोल 01 yes no, but there are other stages also available, and these stages are superposition in nature. What she has just told me about, just introduced about. Superposition means your one stage is similar to other stage, similar other stage. That is number one. Second is, we are talking about everything is happening in a quantum manner, and it is photons. So photon is the basic fundamental of the quantum computing. Now photon, if passes from a system, it get entangled. System क्या है वो बाद में बात करेंगे. But if it passes from one system, it get entangled. What does entangle means? If one photon spin in this way, other photon will spin another way, because quantum is that quantum number, spintronics, spin, magnetic field. It means without any link, they can also communicate. It means one photon can communicate to other photon without any connection. So faster communication is there. Fastest communication is there. And then we are talking about the processing speed. The processing speed automatically will increase because we are following the superposition things. So this all is the quantum, and then quantum is having a lot of possibility, and government has given a lot of emphasis. We are talking about qubit, quantum bit now. This bit will not do. हमें quantum bit का भी देखना पड़ेगा. Quantum bit is.
We'll give a lecture.
So just to sum it up, now the things time is there when we have to think about how we can leverage the utility facilities of the quantum in the holistic way. If we do not catch it, everyone have the quantum awareness among us. If you do not catch it, we will be lagging behind. China has already reached 200 qubit capacity, and we are right now talking about 6 qubit or 10 qubit. So that we have to come into. So these are the power and capability and potential of the quantum. So thank you very much.
Thank you, Dr. Pandey. Sorry that I will just take 2 minutes to thank Dr. Pandey and also to all of you. See, first of all, the most enjoyable session was student session. Let's give a clap to our students. Brilliant. You are the best. And all other speakers who came from industry, academia, and also government. So let's give a big clap to all the speakers who came, cheered, and also shared some of their thoughts. We will make a proceedings of this, and we will bring out the highlights of this, what happened, so that it gets circulated, not several pages, maybe 2 pages so that everybody will read. We will circulate to all the participants. Then we will have individual strategic planning meetings to chalk out how do we create working groups, consortia. All this we'll ultimately develop this. So and we'll prepare a big roadmap. And thank you very much. I want to thank Founder President Dr. Chauhan ji and also Dr. Atul Chauhan ji, the Chancellor, Vice Chancellor Dr. Balvinder Shukla, and all those who are connected, and my own colleagues, Dr. Gopal Bhushan, and from our side, Nitasha, and Sneha Nair, and Vaibhav, and all those people who are connected with this, Goodwill, and Devendra Kumar, everyone, let's give a big clap. And then all the faculties of Nitasha's group, just can you get up? So that now let's clap for them because they're on the ground, they were working for it. And so thank you to everyone and let us work together. We will make India the #1 in quantum technology. Best wishes. Just felicitation of the students. Just two more minutes. Just read out the names, please. Ask them to come, everybody together.
I would like all the guests to please come forward for the felicitation. Mr. Siddharth Sood.
May I request Professor Dr. Gopal Bhushan, sir? We thank you, sir, for your time and expertise to make this session meaningful.
Dr. Preeti Vishal, ma'am.
We thank ma'am because she added great depth to the discussion, and we thank her for a valuable time. Let's give ma'am a huge round of applause. Thank you, ma'am.
I would like all the dignitaries to please present a token of appreciation to our students who have presented.
We thank you, sir. It has been an honor to have you with us. Thank you for your valuable contribution.
I would like to call all the student presentations here, please.
Group 1.
Dhruti Shah, Swayam Kohli, Vishwas Kesarwani, Iranpreet Singh, Prateek Singh, and Arjit Tomar.